Hi, students. This lecture is over chapter 15, which covers thermodynamics. So thermodynamics is the final chapter of the theory of thermal physics. It is a chapter where we will unveil the real main workhorse laws of physics or laws of thermodynamics. We know there are four laws of thermodynamics. We call them the zeroth law, the first law, the second law, and the third law. And I've already given you the zeroth and the first law, and the third law. The primary laws of thermodynamics for this particular chapter will be the first and the second. Now, so thermodynamics started off as an energetics theory. So let's just kind of remind ourselves where we are in thermodynamics. Let's review a little bit of where we left off and then where we're going. So thermodynamics or thermophysics is a theory governing phenomena involving heat or temperature and heat for the most part. It relies on four laws of thermodynamics. We refer to these as the zeroth law of thermodynamics. The first law of thermodynamics. The second law of thermodynamics. And the third law of thermodynamics. So all phenomena that deal with temperature and heat and any kind of phenomenology related to that is fundamentally based on these four laws of thermodynamics. Now we've seen two of them so far. I've given you the zeroth and I've given you the third. Now, primarily chapter 15, which is over thermodynamics itself, will give you the first and the second. Now, as I said before, we have to do the study of thermal physics a little differently than we did mechanics. In mechanics, we were able to actually look at things moving around. We were able to look at objects in motion. You can see objects moving around, and Galileo studied how the mathematical relationships of their movement, and then it was Newton who brought to the humankind the laws of physics for the very first time. And so in that sense, that we are able to then understand through the laws of physics why bodies move, and then we're able to employ an energy concept afterward. Here in thermal physics, we have to do things backwards out of necessity, because the players, the constituents, or the objects that are moving are actually atoms and molecules, which we cannot see, which we didn't even know of their existence until 1830. And I talked about the experiment by Robert Brown, the botanist Robert Brown, in the chapter 14 lecture. We did not even know until 1830 that atoms even existed. So the objects the constituents that are moving around, that have energy, that basically that manifests itself as thermal systems is based upon atoms and molecules and their motion. So we're forced, because we started this theory of thermal physics in the 1700s. We're forced to go with an energy theory first. And so thermodynamics, the chapter we're about to study, is really a chapter that is a chapter of energy transformation, and it entirely relied on what we're going to refer to as the first and second laws of thermodynamics. And those are the only laws of thermodynamics that even existed for many, many years. And then I think it was Rudolf Clausius, one of the great thermodynamicists, as I've said the story before, but he kind of made an unhappy discovery. He said, guys, we have these first and second laws of thermodynamics. Well, we're taking temperatures, and taking a temperature is actually relying on a concept called thermal equilibrium. The concept of thermal equilibrium is a law of thermodynamics. I mean, that is a behavior that's always true, that has normal, and it does not have a more fundamental cause. Well, what do we do? Do we call it the third law? Well, that doesn't make any sense. When you order laws of physics, you order them in accordance of dependence. So for instance, if you look at mechanics, the first law of motion is the law of inertia. So you have to know about mass. Mass is a measure of inertia. Well, you learn about acceleration, what Galileo's kinematics. Well, then you take inertia, which you learned about, or mass, you learned about in the first law of thermodynamics, the first law of motion. You multiply that by the acceleration, you get the force. So the second law of physics gives you the concept of a force, which depends on the concept of inertia, which you got from the first law of physics. So you have to have the first law of motion before you can talk about the second law of motion. And then, of course, with the third law of motion, that's the action and reaction. That is, that is a relationship of action, reaction, force couples. So you have to know about forces before you can talk about their relationship. So the third law must come after the second law. So the laws of motion are ordered in accordance of their precedence, as we saw. So when you order laws, that's the way it is. So the first law and the second law are ordered this way. Well, whatever we call this law that talks about the thermal equilibrium, it has to precede. It is the most basic thing you can do in a thermal system, is take a temperature. So it must precede what's already there. What do? We already have this out in the literature called the first law and the second law. We can't just tell everybody to erase their books, and every time you see first law, make it second law, and every time you see second law, make it third law. What do? Well, we have to insert what is called the zeroth law. That's all we really can do, is say, well, we got to precede one. Well, how do you precede one? Well, zero. And then later on, we talk about the third law, which is, but again, tells you the greatness of Sir Isaac Newton. Sir Isaac Newton was all by himself and got all three laws of motion correct and in the right order, and all the laws of motion. He didn't miss anything. Here's this group of brilliant thermodynamics physicists, of the likes of Maxwell and Boltzmann and Clausius and Gibbs, people of that nature. They missed a law. And so it kind of just tells you how amazing Sir Isaac Newton was. All right. And so let's remind ourselves what the zeroth law and the third law are, and then we're going to focus everything on the first and second laws. All right. So let's remind ourselves what those are again. So going back to, I guess, in chapter 12, we mentioned the zeroth law. In fact, I mentioned both the zeroth and the third law in chapter 12. So chapter 12, we talked about the zeroth law of thermodynamics. Again, this is just a review. We talked about this, but let's be complete. Thermodynamics is this huge word. All right, so what the zeroth law of thermodynamics essentially says, it is the way how you can take a temperature. And it says if system A and system B are in thermal equilibrium with each other, we'll just say thermal equilibrium, and system A is in thermal equilibrium with another system C, okay, then A is, I'm sorry, then B is in thermal equilibrium with C. Kind of like the transitive property in algebra. You guys remember the transitive property in mathematics? So if system A and system B are in thermal equilibrium, you have systems A, B, and C, and system A is in thermal equilibrium with another system C, then that implies that system B is in thermal equilibrium with system C. Thermal equilibrium is a general concept. All right, and so it is our way, you know, this law allows us to take a temperature. Most basic thing we can do in a thermal system. That is the most tangible measurement you can make in a thermal system, is just taking a temperature. All right, and all the great thermodynamics physicists missed that. I mean, that they missed the most basic thing in front of them, is that this is actually the ability to do this is based upon a law of physics. Okay, then we talk about the third law. Third law is pretty simple. We're never going to really use it, but you know, it is a law of physics that to make thermal physics complete, you should talk about it. So the third law of thermodynamics, we'll jump to the third law. We're never going to use it, but we'll just give it anyway. So third law of thermodynamics says it is impossible to take any system to a temperature of absolute zero. You'll never get there. Remember, absolute zero is what? Absolute zero is 0 Kelvin, or it's negative 273 degrees Celsius, or maybe it's, I think it's negative 273.15. Well, we'll say it's negative 273 degrees Celsius. Anyway, you'll never get there. You can asymptotically approach absolute zero in the greatest cryogenic experiments you can do, but you'll never get there. Nobody ever has. And so, given this is a law of physics, this is a law of the universe. You know, this is this ends up being, and this is a more advanced law in that we must know about atoms to even talk about Kelvin temperature. So this is more advanced than, say, the zeroth law, which is very basic, and that tells you ability to take a temperature. We'll realize that the first and second laws of thermodynamics are purely the energy, the pure energy transformation theory, which we're going to study right now. And then as we develop an atomic or molecular theory, like we did in chapter 14, then we're more advanced, and we can even discuss reason why we even have an absolute temperature scale, because it's not based upon the freezing and boiling points of water. It's based upon motions of atoms, thermal energy of atoms. All right. So, so those are the laws of thermodynamics that we've talked about so far. All right. Now, thermodynamics and I've been very careful in this class so far intentionally to discuss what I'm calling thermophysics. Okay, I have not said particularly thermodynamics in this study. I've talked about thermophysics, because thermodynamics, yes, we refer to the laws, the underlying laws of thermophysics as the laws of thermodynamics. But thermodynamics in and of itself is a pure energy transformation theory. And so it is really in the most basic sense, it is a theory of physics that requires no knowledge of the atom. One of the very, very few theories of physics. Why does it require no knowledge of the atom? Because you didn't even know atoms existed, right, until 1830. So thermodynamics is the study of energy transformation. It is a pure energy study. All right, and so and it's primarily based on the first and second laws of what are called thermodynamics. But again, it's a pure energy transformation. It is, I don't know if it's the only field of physics, but it's certainly one of the only. It is, we'll just say one of the only, just in case I'm wrong about something here. So it is one of the only fields, I think it is the only one, but fields of physics that requires no knowledge of the atom. And again, that's by design, because we didn't know about atoms. All right. All right. And the interesting thing about thermophysics, you go to mechanics, some of the concepts of mechanics, I would say, are simple to state, but mathematically, mathematically, I guess I would say involved, maybe a good word. Like conservation of momentum. Total momentum of a system before at some given time is the same as the total momentum afterward. Well, that's a simple statement, except momentum is a vector. You have to do a conservation of momentum in x, y, and possibly z directions. And if you say that the collisions are elastic, then you employ the conservation of energy, which causes you to have square velocities, and then the mathematics gets really nasty, right? But the mathematics is more challenging, but the concepts are easy. Here in thermophysics or thermodynamics, the mathematics for the most part is quite easy. The concepts get more challenging. They're more abstract. So there's no free lunch. I mean, you get one or the other. And so I think you turn in and you have easier mathematics, but you have a little bit more challenging concepts. All right, so anyway, so let's get going here. So we start off with the first law of thermodynamics. And again, when I talk about law of physics, there's nothing for me to derive. A law of physics is, it just is. It is a fundamental of the universe. All right, so I'm going to write down the first law of thermodynamics, and then we'll discuss what it means. So first law of thermodynamics. First law of thermodynamics is simply delta U equals Q minus W. Okay, so delta U, so we kind of imagine here for a moment, I'll draw a little picture of probably our favorite thermal system, if you will, is a little piston. So a little engine piston. There's a cylinder. Inside the cylinder is a ideal gas. We're going to imagine all the gases are ideal. And inside here is imagine there's a cylinder, little driver head here. And it's a piston. Inside of here is a gas. And so heat can go into the system or out of the system. Work can go into the system. Work can be done by the system or on the system. And so inside of this gas is going to be what's called internal energy. So U is the internal energy of the system. Now, today we understand what the internal energy is. So with the understanding of atomic theory, with the understanding of the kinetic theory of gases, we understand the internal energy to be the thermal energy, or the average kinetic energy of the constituents. We understand that now we have a more advanced concept. Now we understand atoms. But back in the 1700s, they did not understand atoms. So this was energy that was contained in the system. That's how they interpreted, the thermodynamicists of the 1700s interpreted internal energy. It's energy in the system. It's an energy theory. We understand that it depends on these moving parts. We understand, 1830 onward, or particularly after Maxwell's kinetic theory of gases, we now understand that this internal energy is the average kinetic energy of the constituents, or the atoms and molecules that make up the gas. Okay, so for right now, we're just going to say it's the internal energy. All right, we have more advanced understanding now, but again, we're going to just have a pure energy theory. So U is the internal energy. Q. Okay, so Q is the heat into is considered positive, or out of, let me back that up actually, it's the net heat. So again, there could be heat going in and heat going out. The net heat, the total, in minus out, it's going to be, whatever is the net. The net is going to either be an overall heat coming into the system or an overall heat going out of the system. But again, it's heat, net heat, into, I'll call this positive, or out of, I'll call that negative, the system. Remember, there is a sign convention to these thermodynamic variables. Remember, it's system specific. Thermodynamic systems are selfish. It's all about me, right? If I get something that's positive, if I lose something that's negative. So if I gain heat, that's good, that's positive. We call that positive. Heat's coming into the system. If I lose heat, that's negative. So that gives me a sign, an SIGN sign on the heat. There is a sign convention for the heat. Okay, and remember what heat is. Just remember, from chapter 12, heat is the spontaneous transfer of energy let's see, how am I doing here? Due to temperature change. So just as this a reminder from chapter 12. Okay, MC delta T. You know, it's again, you have to have a temperature change, but it's hard to control it. Not so easy to control this heat transfer because it is spontaneous in nature. So heat is the spontaneous transfer of energy due to a temperature change. Okay, so that's a reminder from, we already said this, but it's a reminder from chapter 12. I'm going to erase this real quick. What about W? W is the work. So W, work done by, which would be plus, or on, which would be minus, the system. So the system, when we push the piston out, it's going to cause a displacement. And of course, we know that work in a fluid is pressure times volume. So it's either going to be a positive change in volume, it's going to push it up, piston up, that'd be work, that'd be positive work, or negative would be work done by the system. So now again, there's a sign convention associated with this, and you can kind of see it. You know, if you remember, you know, if I imagine I'm gonna have a displacement, we'll say X, delta X, and we'll say that there is an area A of the piston. Well, remember, if there's a force, let's say by the gas inside here, pushing up the piston. Remember the work? The work is the force times the distance, force times the displacement. And I know there's a cosine in there and stuff, but we're going to imagine that the force and the displacement are parallel. Okay, we're done with vectors now for this semester. All right, so we're just going to assume that we have parallel force and the displacement are parallel in this situation, and they are. And again, we don't use force in a fluid system, we use pressure. The pressure is the force divided by the area. So if you solve for pressure, it's PA. So the work is going to be PA delta X. And A times delta X is what? That's a volume. That would be work is the pressure times delta volume. So if the volume increases, that's a positive delta V. That means the work is positive. So again, if the system's doing work, that means that the volume of the gas is increasing. The gas is doing work on the piston. If, let's say, there's an external pressure being applied and the piston gets pushed in, well, that means the volume is decreasing. That's a negative delta V. That means the work is negative. Again, the sign convention is very, very important. If you don't get the sign convention down, that's the only way. The math is quite simple. This is a very simple equation. If you don't, the only way you're going to get hung up is if you mess up the signs. Now, the big question you might look at. So, well, first of all, where does this equation come from? Is there any kind of explanation? Yeah, I know it's a law of physics, but is there any kind of deeper explanation for it? Well, this equation is actually the conservation of energy. And so you look at the conservation of energy, and so this is an application of the conservation of energy, which we have already seen. So this is a form of the conservation of energy. You might say to yourself, wait a minute, I've seen the conservation of energy before. You talked to me about this in mechanics. You said the conservation of energy is total energy is a kinetic energy plus a potential energy. That doesn't look like this. Well, yes, you're right. Energy has many, many forms. And in mechanics, those are the forms that are important. In thermal systems, The forms of the energy that are at play in thermal systems is heat and work. Those are the energies that are involved in thermal systems. So yes, this is a conservation of energy statement. It's just that the energies that are involved are the heat and the work this time. But a more important question, like, well, that's an important question too, but one of the questions is, why this minus sign? Why this? That looks kind of funny. And this minus sign has nothing to do whatsoever with the sign convention I was talking about. This minus sign is an algebraic minus sign. Let me draw my diagram again. I just erased it. Let me redraw it. And see if we can understand the minus sign. So it's clear that, okay, so there's some internal energy delta U, or some internal energy U in the system. All right. And so if heat enters the system, if heat Q enters the system, then the internal energy increases, right? That makes sense. I mean, mathematically, the heat is positive if it's coming to the system, and heat coming to the system is going to do what? It's going to increase internal energy, for sure. Likewise, if heat leaves the system, it reduces the internal energy. And that also makes sense. Again, according to the sign convention, heat leaving the system will be negative, and that will reduce the internal energy. That totally makes sense as well. What about work? If work is done by the system, that's called positive, right? So if work W is done by the system, it is positive. But where does that work come from? It is at the expense of the internal energy. That's where it comes from. So the internal energy must reduce. So positive work has to come from somewhere. Where does energy come from? It comes from the internal energy. So positive work is at the expense of the internal energy. It means it must be positive work must cause a reduction in internal energy. So positive work will cause the internal energy of the system to actually reduce. That is why you have the minus sign there. Okay. So now there's another interesting concept at play here. And that is, if you look at energy, if you look at heat and work, all right, so again, heat is the spontaneous transfer of energy due to a temperature change. So again, as I said, it's spontaneous in that it's not so easy to control, and you know, it's you know, but and on the other hand, work is work is an organized process that involves a macroscopic force exerted through a distance. Just like I said earlier. Now, the thing about what's funny is here is that heat and work are energies of transit. Which means that the system keeps no record of them. Okay, so they're energies of transit. All right, so they're basically energies that just kind of pass. There's no record keeping in the system of these energies. Yes, they're very important energies. However, you know, here you have these energies that the system keeps no record of them. Now, what's funny is that on the left-hand side is a very, very special function. Left-hand side is the internal energy, as I've said, and that's actually a very special function in physics called a state function. Okay, so internal energy is a state function. So what does that mean is it's change, it's you know, it's change delta U only depends on the endpoints. Of the process. And not the path taken, it's path independent. All right. Whereas, you know, the heat and work are energies of transit. That are path dependent. I mean, you see the path directly in the work, in that it entirely depends on the displacement. That's the path. Whereas the heat, you know, depending on, we're going to talk about different thermodynamic processes. Depending upon the thermodynamic process chosen, you know, you may have, you know, that will determine how much heat transfers occurs. But irrespective of, and again, heat and work are energies of transfer that are path dependent. but the delta U is a very, very special function in physics. We're going to understand that every law of thermodynamics is going to have a corresponding, or at least a zero first and second law, is going to have a corresponding very special variable of thermodynamics. Now, zeroth law is associated with the temperature. The first law is associated with a very special variable called the internal energy. So isn't it funny, here on the right-hand side of this equation, you have two energies of transit that are not recorded, that are path dependent, and yet this very special combination, and only this special combination in the universe, creates a very, very special function called a state function. You know, it's not Q minus 2V or Q plus 2, or sorry, Q minus 2W or Q plus 2W or any other combination. It's just Q minus W. That particular situation, that particular combination of heat and work, these two energies of transit combine to make this very special energy. So I give you this internal energy. I'll give you an example. Let's say, for instance, let's say I'm walking down a road to a restaurant or store, and I see a bicycle tire. Lying on the ground. Okay, let's say it is 10 a.m. Okay, I will determine the internal energy of the bicycle tire, and that's easy to do. Okay, so I will measure, the internal energy of the bicycle tire, you know, by taking a temperature. And assuming an ideal gas. Because what? Because the internal energy, which I know is the thermal energy, is only dependent on temperature. It's you know, 3/2 N K T. So if I determine the temperature, I can kind of give a volume calculation for the, you know, for the number of, if I say it's air, I can figure out, you know, say some constant, you know, regarding the, you know, regarding how many air molecules are in this tire. I can essentially just make a measurement and have a determination of the internal energy at a particular time. Now I let this tire lie here. I go do my thing, and then I walk back, let's say around noon or 1 p.m. And I look at the tire and I take a temperature again. All right. So I've taken the temperature of the tire. It's lying on the side of the road. And then, you know, I don't know why I'm doing this experiment, but you know, we're doing it. I'm a scientist. I'm doing this experiment. All right. So later, after I'm done eating or shopping, I walk back and take and determine that the internal energy of the tire increased. because the temperature is higher. Okay, so I'm doing this now later. And now the thing about it is I have no idea why that happened. Okay, and so there is no way of knowing how this happened. Why did this happen? All I know is in change internal energy. So I know the endpoints of delta U. There is no way of knowing through any kind of a forensics analysis why delta U occurred. I mean, it could be that the tire was lying in the sun and received heat, just received heat. Okay, or it could be that somebody decided to go and do an air pump and pump some air in. It could be that someone did work on the tire. And pumped air into it. I have no way of knowing, or it could be a combination of the two. Again, if I'm pumping, if someone's doing work on the tire, well, that's negative, right? But negative of a negative is a positive. So work being done on the systems is going to increase internal energy. So again, I have no way forensically to know, and there's no record in the system to tell me. These are not stored variables. They're energies of transit. The only thing I know for sure are the endpoints. I measured U at 10 a.m., came back later at noon or 1 p.m., and I measured U again, really measuring the temperature. And I know that for a fact. I have no way, however this occurred, there's only a couple different ways that can, there's only two avenues the energy is going to come into the system, and that is through heat or work. And I cannot tell which one it was. There's no way forensically for me to know. Why? Because these are energies of transit. This is a state variable. U is. So again, it's very interesting how this relationship holds. The right-hand side involves energies that are so different than the left-hand side, and yet they're tied together in this very special way. Okay, and so all right, so that's what I wanted to say initially about the first law of thermodynamics. Let's do a couple of problems. I want to do start off basic here. So right now we're in OpenStax chapter 15, and we are in Cutnell Johnson chapter 15. So we're lined up again on chapters. So OpenStax 15.1 says, what is the change in internal energy? Start off basic. Of a car if you put 12.0 gallons of gasoline into its tank. The energy content of gasoline is 1.3 times 10 to the 8th joules per gallon. So gasoline has a lot of energy in it. Determine that when you take a little match next to it. All other functions factors. All other factors such as the car's temperature are constant. All right, so first problem of the day. What is the change in internal energy of a car? We have about 12.0 gallons of gasoline into its tank. The energy content of gasoline is 1.3 times 10 to the 8th joules per gallon. All other factors, such as the car's temperature, are constant. All right, so this is a pretty simple problem. Delta U, change in internal energy. It's going to energy content of gasoline, 1.3 times 10 to the 8th joules per gallon. And then times how many gallons? Again, 12 gallons. You do that calculation, you find out that it's 1.56 times 10 to the 9th joules. We start off pretty easy. There you go. First problem of the day. All right, let's look at 15.2, open statics. This one says, how much heat transfer occurs from a system? You got to read these problems very carefully, by the way. From, very important word. A system if its internal energy decreased, another important word. By 150 joules. While it was doing 30.0 joules of work. Okay, so every word here matters. All right, so again, how much heat transfer occurs from a system if its internal energy decreased by 150 joules while it was doing 30.0 joules of work. So what the thing that can mess you up in thermodynamics problems, and you're going to find out that oftentimes many of these thermodynamics problems, if you have a 4-function calculator, one that doesn't necessarily have cosines and sines and tangents and exponential functions and logarithms, stuff like that, plus minus addition, subtraction, multiplication, division. 4-function calculator, you're probably more or less able to do any kind of these problems in thermodynamics. What gets you is a sign convention. All right. So we have to look at this very carefully. So how much heat transfer occurs from a system? Okay, so if its internal energy decreased, okay, so again, you're looking at the first law of thermodynamics. Delta U is Q minus W. We want to find Q. We know the internal energy decreased. Okay, that's a negative. Decreased by what? By 150 joules. So negative. Why? Because heat leaving, sorry, internal energy decreases means negative. And then while it was doing 30.0 joules of work. So again, if work is done by the system, it's positive. It's done on the system, it's negative. So given that the work was being done by the system, so the system it was doing, that means that would be a positive. So that work is a positive 30.0 joules. All right. So again, how do you do this problem? Well, you're solving for Q. So again, the mathematics is deceptively easy. And all you have is delta U plus W. All I've done is I moved the W on the other side. That's all there is to it. And then you plug in the values. Let's see, delta U, what is it? It's negative. This is where you get messed up if you're not careful. Negative 150 joules plus, algebraic plus. And then here, I have a positive value for the work. So it is literally as simple as this. The heat will then be negative 120 joules. And again, that actually also agrees with the reading as I read this carefully, because it's saying how much heat transfer occurs from a system. Well, the problem's expecting heat to be leaving the system. So if I come up and if I answer this question, I end up having a positive value, then I'm probably going to be like, well, either the problem's wrong or I'm wrong. You know, either the problem's being worded wrong or I'm wrong, because it's saying from the system. I'm expecting the system to be losing heat. And so again, I would certainly expect this. This negative sign just basically means that heat, the negative means that heat is going to leave the system. All right. So be very careful with the sign convention. That if anything can whack you in this thermodynamics, that it's the sign convention. So be very careful on it. All right. I'm going to look at OpenStax 15.3. Okay, OpenStax 15.3. That says a system does 1.80 times 10^8 joules of work. Again, careful wording. Read the problem carefully. The system does 1.80 times 10^8 joules of work while 7.50 times 10^8 joules of heat transfer occurs to the environment. Okay, what is the change in internal energy assuming no other changes? All right, so parentheses such as in temperature or by the addition of fuel? All right, so 15.3 open stacks. The system does 1.80 times 10 to the 8 joules of work. It does work. Again, that's important. While 7.50 times 10 to the 8 joules of heat transfer occurs to the environment, and that's also important. That's giving you a direction where the work is and the heat's going. What is the change in internal energy? Assuming no other changes, such as in temperature or by the addition of heat. All right, so again, this should have a question mark. There you go. Now, so again, we're going to use the first law of thermodynamics, but where you can get hung up, of course, is in sign convention, right? So you got to read these very carefully. All right, keep note of that. I do need space on this one. Okay, so we're going to operate with the first law of thermodynamics. And then again, this simply delta U is Q minus W. All right, so we're saying that work is being done by the system. So if that's the case, W is simply going to be positive. We're going to put in the positives here for effect. Positive 1.80 times 10 to the 8th joules. It's positive. Why? Because the work is done by the system. Very important here. You read these problems carefully, or else you get yourself, wrapped up in trouble. And literally, you might wonder if you miss a problem, it's because of a negative sign. You might say, "Geez, I mean, he really gave me like a lot off in that problem because of the sign." Well, I'm gonna tell you right now. I'm gonna tell you here first and foremost, the signs SIGN have incredible importance and value in thermodynamic systems. The wrong sign means the difference of everything. It's not just a technicality. It is literally something that is absolutely wrong in your system. It is either you're telling me that work is being done by the system or on the system. That's the importance of this sign. And if you get it wrong, then everything else in the problem is going to be wrong, right? So you got to make sure you read this problem carefully. All right, what else do we know? We know that heat is going to how is it read? It's heat transfer occurs to the environment. That means that your environment is outside your gas piston system. Your environment is elsewhere, outside. So if heat's going to the environment, it means it's leaving the system. So then that's going to be a negative. It's leaving the system. Negative 7.50 times 10 to the 8 joules. Again, heat is going, quote, to the environment. Understand what that means. I.e., heat is leaving the system. In sign convention, sign convention, sign convention. I cannot express it any more important. The math is easy. The sign convention is what will get you if you're not careful. Now all that's left to do is literally just plug it into the first law. So delta U, there's not even any algebra. Delta U is Q minus W, right? What's Q? Negative 7.50 times 10 to the 8th joules. Algebraic minus what's W? Well, W is positive. 1.80 times 10 to the 8th joules. So again, I have a two-function calculator that does exponentiation. I can do this very easily. So it's negative 9.3. No sines and cosines. times 10 to the 8 joules. Done. But again, I can be very, very wrong if I get one of these sign conventions wrong. Then my problem makes no sense. Then it's wrong. And if it's wrong, it's wrong. It's probably you'll probably get like 0 credit on it, or maybe a couple of, maybe I'll give you a couple of points for knowing that you need to use the first law. But it's one of those problems that you might look at me and say, well, geez, had I got the right signs, then I would have gotten it right. Well, sure you would have, but you didn't get the right signs. And this is all the work there is to show. So again, that's the thing about thermal systems, is that they're kind of either right or they're wrong. So it's one of those things that there's not a lot of work to show them. Okay, so we talk about thermal systems. We're going to have to kind of develop a vocabulary, and then we're going to look at thermodynamic processes. All right, and so we have to kind of start talking. So we're gonna eventually talk about what are called heat engines. An engine, we're gonna find out, is a way of taking heat and making it do work. That's what we call a heat engine. Before we can actually create heat engines, we have to actually start developing a little vocabulary. All right, so that's what we're gonna do now. So this is the last problem I'm gonna do for a bit, and then we're gonna talk about thermodynamic processes. So one of the most important applications. So now we have a new law of physics. What do you want to do with it? Well, you want to use it, right? You want to make something. Remember you always talk about STEM. You talk about STEM, science, technology, engineering, mathematics. Well, I like to look at it this way. Mathematics comes first, right? That gives you the science. Once you have the science, you can make things. That's called engineering. And then when you live in a world where you have a whole bunch of things that have been made by engineers, that's called technologies. I always like to say MSIT, right? That's really the appropriate way things are being done. But you want to form a cute word, you make STEM, right? But so again, we're at the point where, okay, we've done the mathematics, we've done the science. Let's go make something. So making something means we're going to make an engine. All right, and so one of the most important applications of the first law of thermodynamics is a device that converts heat to work. Which is called a heat engine. And I used to always tell students when we met face to face, you might ask me the question, well, does this apply to my life? Well, the fact that you're in this classroom right now, yes, because you got here because of a heat engine. Your car, the engine in your car is officially a heat engine. It takes heat that you generate by burning gasoline, and it drives the pistons, which drives the drive shaft, which gives you the energy for your lights and your radio, and your air conditioning system, and your battery, and it basically propels you from your home to work. All right, so that's called a heat engine. We'll talk about those, but before we talk about a heat engine, we need to understand some basic concepts. So one of the things about a heat engine, so we're going to get used to some diagrams. We're going to talk a lot about PV diagrams, and we're also going to look at what is called a schematic diagram for the heat engine. So, but first and foremost, let's talk about some processes. All right, and so I'll put up my favorite picture of a piston here again. So we have an engine piston. Now again, your engines have about 4 to 6 or so pistons in it, or I guess 6 to 8 pistons. And so you look at your piston, basically a cylinder with gas inside. And you have this piston. You have this, and they have a little drive shaft on top, or a little connector on top, and it's going to get pushed back and forth in this system. And inside of here is the working gas. We'll also imagine that this gas has, the cylinder has a cross-sectional area A. Okay? And we're going to imagine that this piston will be driven by some sort of displacement D. So it'll be driven by, so let's say, some sort of a displacement D. All right. Now, what's the work going to be? Well, as I've said again, the work is always the force times the displacement. So we'll imagine there's some sort of a force that's being applied on the outside, so the piston's going to get pushed in. Well, again, we don't use force with fluidic systems. We employ the concept of a pressure. The pressure is the force divided by the area. So I can simply solve for the force, and I can substitute it in for the force in the work equation, and I have P A D. And then we say, well, A times D, well, that's this area being displaced by a distance D. That's a difference in the volume, right? A times D is a volume. So I see that the work is equal to the pressure times a change in volume. Okay, so I see that is the way, that is the how you calculate work for a fluidic system. And we've seen that before. We know we had to use that concept when we talked about Bernoulli's equation and fluid mechanics. We've also discussed this when we talked about the kinetic theory of gases. And I told you that the ideal gas law is really a work energy theory, a work energy theorem. It's just an expression of a work energy theorem for a system of the gas and thermodynamic system. So pressure times volume is the way to get work in a fluid system. Now, if the pressure is constant, this process is called isobaric. So iso meaning same, bar, B-A-R is for like pressure. Like you talk about pressure, sometimes you refer to them as millibars. Or what's the device that measures pressure? It's called a barometer. So bar, anytime you see bar, B-A-R, that means pressure. Iso meaning same pressure. So in this process, we have a constant pressure and a changing volume. And of course, as I've told you in the past, we want to work in terms of what are called PV diagrams. So I ended chapter 14 talking about PV diagrams. Those are very important diagrams in thermodynamic systems. So what would a PV diagram look like for an isobaric process? Well, let's look. Constant pressure, right? So let's take a look at what's an PV diagram? Remember, so what does a PV diagram, pressure volume diagram, and we want to talk about these in thermodynamic systems, look like for an isobaric process? Well, what is a PV diagram? Well, it's going to be pressure along the vertical axis, and it's going to be volume along the horizontal axis, right? Constant pressure. So I'm going to go from some V, let's say some V1 to a V2. And I'm going to do it at constant pressure. So I'm going to pick some pressure along here. Constant pressure. Well, what's that look like? Well, it's a constant, right? That's going to be a horizontal line going across. Simplest diagrams you can do. And so there's your PV diagram, constant pressure. I pick some sort of pressure, you know, I'll call it P1 or whatever you want to call it, and it's constant throughout the whole process. And again, how do I calculate the work? Well, it's the area under the pressure volume curve, right? The work is area under pressure volume curve. Just like before, the work was the area under the force displacement curve. Well, in fluid system, it's the pressure volume curve. Well, this is really easy, right? I mean, I don't need integral calculus to figure out the area of a rectangle. I know what the area of a rectangle is. It's going to be this constant pressure. I'll just say it's some pressure P. We'll call it constant pressure P. It's this pressure times what? Times the change in the volume. Just like I calculated before. Constant pressure times the change of volume. That is the work for an isobaric process. All right? This is the work for an isobaric process. Isobaric, again, means constant pressure. Now, in general, we know that in general that this calculation is not so easy, right? In general, you don't necessarily have to have a nice simple process like an isobaric process. You might have something more complicated. So let's kind of remind ourselves of that. So in general, isobaric process is easy, but in general, a PV diagram can be much more complicated. So for instance, let's say it looks something like this. Pressure axis, volume axis. Instead, I have a curve that maybe looks like this. Not so easy. And I want to try to figure out, well, I want to find out the pressure under this curve. How do I do that? Well, what I could just do is say, well, I like rectangles, right? So I could just try to approximate the curve by some sort of rectangle. I have rectangles that are all the same delta volume. I'll try that. So I'll draw these little rectangles out. What do I say? Well, I mean, let's say all of these rectangles have some sort of a volume, delta volume of delta V. And how do I do this? Well, let's say this is rectangle 1. We'll say this is going to be, we want to go from volume 1 to volume 2. We'll say this is rectangle 1, 2, 3, all the way to, let's say, some sort of an I. And I'll just count them. I want to figure out, well, I want to try to find out this, add up these rectangles. So the work would be what? Well, the work would be summation over in counting index I of P sub I times delta V. I just add up all these rectangles, P1 times delta V plus P2 times delta V, P3 times delta V, P4 times delta V, on and on and on, all the way across. But here's the problem though, right? You see these spaces in the curve? That's area that I'm not getting. That's error, ERROR error, right? And so how do I do a better job? Well, I'll consider skinnier rectangles and many more of them. If I really want to do a good job, I'll consider rectangles that are so skinny that they're infinitesimally thin, and there's an infinite number of them. And then what am I doing? I'm employing calculus. So to do this right, I'd have to employ integral calculus. The work would be the integral from V1 to V2 of P dV. I'd have to employ integral calculus in the most general sense to do this problem right. Well, for the concept of an isobaric process, I don't need integral calculus. I know the area of a rectangle. So you can actually figure out the area of a rectangle with integral calculus quite easily. But again, I know that from geometry. I know that from high school. You know, I mean, we know the area of a rectangle. So again, no big deal there. But in most general sense, it's not so easy to calculate. So we're going to see processes that are more difficult to do. Now, let's consider a process where let me make my first very, very simple heat engine. All right, so I'm going to consider a cyclic process. So what do I mean by that? So I'm going to consider a cyclic process. Okay, and I'll explain what cyclic means in a second. So I'll go to my PV diagram, which is going to be my a big time go-to tool in the study of thermal systems. I'm going to imagine here that I'm having a process where I'm going to go from some sort of pressure. So I'm going to map out a little rectangle here. At least even draw a rectangle. Draw a little rectangle. Starting off easy here. And I'm going to consider 4 points, the corners of the rectangle. I'll call this A, B, C, and D. Now, I'm going to imagine here that I have two, so this is my pressure versus my volume. And I have, I'm going to imagine here that there's going to be a change in volume between A and B and C and D of delta V. We'll just say that the magnitude of that change, we'll say if I were to measure the magnitude of that change, it is delta V, the change in the volume. All right, and now let's imagine that I have a particular pressure right here. I'll call this pressure, this is my pressure axis. I'll call this pressure PAB, P sub AB. And I'll call this pressure, this constant pressure down here, P sub CD. Now, if you look here, that I have an isobaric process for AB and for CD. Because why? Because the system is when I'm going from A to B or C to D, the system is at a constant volume. So let's imagine I take this special engine and I have it go around. It's going to go from A to B, and then from B to C, and then from C to D, and then back D to A. All right. So AB, so processes A, B, and CD are isobaric. Why? Because I'm taking the system, I'm keeping the pressure constant, I'm changing the volume in both of these cases. A, D, and B, C are systems where what? The pressure may change, but the volume is constant. So BC and DA are constant volume processes. Because delta V is 0 there. Which we call isochoric. So we have isobaric. Now we have a new word called isochoric. Isochoric is a constant volume process. So when you're going along A, B, or B, C, notice your volume doesn't change. Your delta V there is 0. Now, if we imagine calculating the work. So let's calculate the work and going around here. All right. So again, we have the work. So we have a isobaric, isochoric, isobaric, isochoric. All right. Now let's try to figure out the work going about this process. Okay. So let's imagine for a moment that I will call. We'll let P sub A be. Again, these are just numbers that we're going to throw up here now. And this is actually out of example OpenStax 15.2, by the way. So this is out of OpenStax example 15.2. In case you want to look up what I'm doing. So in this example, P sub AB we're going to let that equal 1.5 times 10 to the 6 pascals. And we're going to let the lower one, P sub CD, that's a smaller pressure, that's 2 times 10 to the 5th pascal. All right, so we're going to calculate the work. All right, so in calculating work, remember work is a scalar. Works just add. So the work would be what? Work AB plus AB, BC, the work BC, process BC plus the work for process CD plus the work for process DA. Okay, now why do I call this process cyclic? Because it goes, it constantly is going to go from A, B, C, D, then back to A again. It constantly returns. It constantly returns to an initial position on the PV diagram. So again, a cyclic process is one that constantly. So a cyclic process. This is a cyclic process. A cyclic process is one that returns, one where the system returns to an initial state. Given by macroscopic variables pressure, temperature, volume. Right? So it's here it is at A, has particular pressure and volume. It's an ideal gas. P equals nRT, goes to B, goes to C, goes to D, back to A, just like it was before. And it does it again and again and again. It's a cyclic process. All right. That's why these engines, for instance, are cyclic processes. Now, how do I figure out the work? Well, work AB. A to B is isobaric. I know how to figure out an isobaric, right? That's pressure times delta volume. So it's going to be, so work AB is going to be the pressure. Which pressure? Oh, AB. Times delta volume. Now, the volume is by an amount delta V, but it's actually getting bigger. It's increasing, right? So that's going to be a positive delta volume. It's an isobaric process. That's how I calculate work in an isobaric process. Pressure times change in volume. How about BC? Well, BC, the volume does not change. So that means that I have to have a displacement to have work. So the volume doesn't change. The pressure for BC is 0, right? An isochoric process does no work. Since it has no displacement. Or in this case, volume change. I.e., delta V equals 0. So an isochoric process, the volume does not change. You have to have volume change. You have to have the piston moving up or down to do work. If the piston does not move, no work is being done. So for an isochoric process like BC, and actually for DA, there is no work. Work is not being done in, isochoric process. Work is not being done for an isochoric process, like BC, and also we will find out in a moment, DA, when we get there. All right, so that means that's easy to calculate. We just put zeros there. So there you go. So now we have moved from A to B, now from B to C. Now we're down here at C, in particular pressure volume coordinates. Now we're going to go from C to D. Okay, now let's be careful. Pressure times change the volume, right? Well, what's the pressure? It's isobaric again. Pressure is now going to be a constant, P sub C D, but look at the volume. The volume is reducing. It's reducing by an amount delta V. That's going to be a negative delta V. Multiply by delta V, negative that is, because it's reducing, it's changing volume, but the volume is reducing now. And now we're at D. We're at this particular pressure volume coordinate. What we're going to do now, we're going to do another isochoric process to get back to A. And we know that isochoric processes do no work. All right. And so with that said, if I put all this together, what do I get? I get the work is P sub AB times delta V minus P sub CD times delta V. Or I can factor out delta V and I get the work is P sub AB minus P sub CD times delta V. Now, by the way, I didn't state this either, but the change in volume as given in the example is going to be 500 centimeters cubed. All right, now that's what the example gave. All right, so the example gave us that change in volume is 500 cubic centimeters. All right, that's if you look at the example. All right, so I have now calculated this this work. Now, can I now put in numbers? Sure. The work is, all right, change in the pressures, 1.5 10 to the 6. Minus 2 times 10 to the 5th pascals. That's all multiplied by volume change. Okay, we have to determine the volume change. We have to do that real quick. So 500 centimeters cubed. So let's do that real quick. I need to get meters cubed, right? So again, delta volume, we'll just do this real quick and I'll erase it. 500 centimeters cubed. All right, so it's easy because we know that there are 1 meter has 100 centimeters, right? Don't forget to cube it. So that corresponds to a change in volume of 5.00 times 10 to the negative 4 meters cubed. All right, so stick that here. All right, I'm ready to go. So when I do that, I find out that the work done in this cyclic process is going to equal 650 joules. All right, which, by the way, if you look at this calculation more closely, this happens to be, so what did I do? I basically added the area under the curve, right? First time through, I had all of this area that I did the first time, right? And then what did I do? Well, I subtracted, when I went the other direction, I subtracted the area underneath CD. So what I actually have here is the area enclosed by the rectangle. If you look at this, if I were to say, hey, give me the area of the rectangle, you'd say, okay, well, it'll be length times width. What's my width? Delta V. What's my length or my height? Well, it's the difference of these two pressures. Well, by the way, that's exactly what the volume is. So in a PV diagram, the work is always the area enclosed in the PV diagram. So again, the work for this entire process is the area enclosed in this rectangle. All right, so the work is always the area of, or the area bounded within the PV diagram. And that's the fancy mathematical way of saying bounded basically means that here's the boundary, the area that's within this boundary. That is, so you're not going to have PV diagrams that are going to, you're going to see PV diagrams that are going to look like flying carpets. They're not going to be very nice geometrical figures like you see here. They're going to be more complicated looking. But the area bounded by the curves, by the process curves in the cyclic diagram is going to be the work. Every single time the engine does this process, it does 650 joules of work. So it goes through the process, ABCDA, 650 joules of work. ABCDA, another 650 joules of work. That's what's driving your car, or that's what's driving whatever this is, whatever the machinery is. Every single time a process occurs, ABCDA, another 650 joules of work is done to do whatever it is that you're trying to do for your machine. All right. Now we have a couple other processes we're going to talk about. We talk about isobaric, we talk about isochoric. So a couple other processes, and I've mentioned one in chapter 13, if I recall. And I'm going to draw another little diagram. We're going to talk more explicitly about these. But I also talked about last time, again, for an ideal gas, we also said, well, of an ideal gas, if you imagine keeping the temperature constant. Okay, I talked about constant pressure, that's isobaric. Constant volume, isochoric. Well, I already talked about constant pressure. Remember, ideal gas law. If the temperature is constant, I have PV equals a constant. We'll say C. C is a constant. And what's the the figure look like? Well, it's going to be pressure is a constant divided by the volume. That's remember, that is a hyperbola in mathematics. So I'm going from one state to another. All right, so this will be A going to B. This is an isothermal. Remember, because it's constant temperature. So again, as I have said already, we're developing a vocabulary. Constant pressure, isobaric. Constant volume, that is isochoric. Constant temperature, isothermal. Iso means constant, thermal, temperature. All right. So again, I have some processes, and again, these are going to be the building block processes of more complicated engines. So we're really building up our vocabulary and our knowledge of thermodynamic processes in order to be able to build up heat engines, which is we're gonna be after next. Okay, now there's another thing to kind of keep in mind here is that if you think about an isothermal system for a moment, all right, let's kind of think about this, in an energy perspective. Now that we can kind of look at this, we can look at the first law of thermodynamics a little bit differently. I mean, well, we look at the ideal gas a little differently in terms of the first law of thermodynamics. So remember the first law, and I'm talking about this constant temperature process now. Talk about the first law. What is it again? Delta U is Q minus W. Well, for an ideal gas, I know that the internal energy is 3/2 NKT for ideal gas. I know, I talked about this with the bicycle tire example, right? For an ideal gas. Well, if the temperature is constant, and these are all 3/2 N and K are constants, right? K is Boltzmann's constant. That's flat out a universal constant. I don't expect. I'm assuming here in this problem that the number of air molecules or gas molecules is going to remain constant. So 3/2 NK, that's a constant. So if T does not change in an isothermal process in going from one state to another, that means that U does not change. All right. So if T does not change, if T is constant in the process AB, then delta U is 0. The change in the internal energy more or less corresponds to the change in the temperature. Temperature change is 0, so the internal energy is 0. That means in the first law of thermodynamics, delta U is 0. That means whatever work is being done under this curve, right, and going from some volume 1 to volume 2, whatever that work is going to be compensated by the heat. So the system is going to change heat essentially as work is being so what's happening here is that work is being done, it's going to be compensated by a heat transfer. Okay, there's going to be some sort of heat transfer, compensation, heat transfer in order to get here. There's going to have to be some sort of equilibrium going on between work and heat for an isothermal process. Okay, so we know that for an isothermal process, the net work and the net heat are the same. Why? Because the internal energy is 0. For an isothermal process, the work that's being done under the curve, the work You know, it's basically the pressure, the area under the pressure volume diagram must be compensated exactly by a heat transfer for an isothermal process. Now, we have one other process that we're going to consider, and that is a process where heat does not change, right? So let's remind ourselves, work and heat are balanced for an isothermal process, right? But let's imagine here, we consider a process, we consider one other process. Where heat transfer does not occur. So there is no heat transfer. i.e. Q equals 0. This is called an adiabatic process. All right, so let me erase some of this. We'll keep the original curve, the isothermal curve on here. Now, what does the first law look like at this point? Well, delta U, remember, U is what? 3/2 NKT. We're talking about an ideal gas again. Again, we are considering an ideal gas throughout all of these arguments. Delta U. What is the first law of thermodynamics again? Oh, yes, that is Q minus W. Now, what happens? Well, we're talking about an adiabatic process at this point. Q is now 0. So now delta U is going to be directly related to whatever the change in a work is, or whatever the net work is. Okay, now what's going to happen is that the system is going to change temperature. So if you imagine a system, let's just say we take a process starting at A going to B. Okay, we have this isotherm. Well, in either case, that is the curve that allows heat to compensate the system. But now we're not going to allow that heat. So what's going to happen if I imagine taking an adiabatic process starting at the same initial point A in the PV diagram, its process to go to the same volume is going to end up being lower. So essentially, what's going to happen now is that the process going from A to B, where we're not allowing heat transfer. So what's going to happen now is that the temperature will have to change, and we're essentially going to be going to a situation where the pressure is going to be lower. And so with that said, this is an adiabatic process, and I start them adiabatic. I start them at the same initial location A, or same state A on the PV diagram to kind of show the difference of the two. And we can even make a process out of it. We can say, well, we can take the process from state A, do an isochoric, go from B to C, and then go back to A, right? And so what would be the work done for this system? It'd be the area enclosed, the area bounded by this curve. This is an isothermal, going from A, isothermal process. This is an isochoric process. And finally, this is an adiabatic process to come back to A. And the overall process is cyclic, because I'm going A, B, C back to A. Okay, so all right, so all right. So with that said, let's let's talk a particular. So I have so again I have more vocabulary here, so I'll add up to my little parking lot. So again, constant pressure, and then finally we have no heat transfer. Q equals 0. That's called adiabatic. These are the building block thermodynamic processes in which I will build my engines. An isobaric means constant pressure, isochoric, constant volume, isothermal, constant temperature, and adiabatic means that Q equals 0. I mean, how do you make an adiabatic process? I didn't really talk about that. Well, adiabatic processes can be done a couple different ways. An adiabatic process can occur if the insulation is excellent. It means you have very, very good insulation, so no heat transfer will occur that way. Or the process occurs so fast that there is insufficient time for heat transfer to occur. So either you have excellent insulation where heat transfer is disallowed into or out of the system, or the process is so fast there's just not enough time for it. All right, so those are the two different ways to get an adiabatic process. They are approximately true for thermal systems. All right, now let's talk about, so what do we know about with PV diagrams? Well, what we want to talk about is how to calculate the work. Well, we know for an isobaric process that's really easy because that's just the constant pressure temperature change to volume, P times delta V. We got that. Isochoric, that's also easy, V equals 0. So that means that if delta V equals 0, there's no work. Work is 0. The piston has to move in order for work to be done. What about isothermal? So now what I have to do is I cannot avoid the use of calculus sometimes. So I'm going to kind of show you the overall way that you'd have to do it involving calculus. And if we don't understand that, that's okay. Again, what's important is to understand that there is a methodical mathematical process involved to compute these formulas, and that what you need to do is know how to apply them and know what they are. All right, so let's look at figuring out the work for a PV process. I'm sorry, for an isothermal process. All right, so here are the processes. I need real estate, so I'm gonna have to erase these now. All right, so we want to calculate the work want the work done for an isothermal, same temperature, process for an ideal gas. Again, everything we're doing here is an ideal gas. Okay, an ideal gas is, I mean, when you're talking about engines, what you have is a gas, and it's very perfectly safe to consider as ideal. So work done for an isothermal process for an ideal gas. Well, we go back to the ideal gas law. PV equals nRT. All right, there's your ideal gas law, which we talked about in chapter 13. And it's isothermal process. So the temperature equals a constant. All right. So what does this mean? Well, it means that I can actually write the pressure as nRT, which is a constant, divided by the volume, which is a variable. And, well, what do I have now? Well, again, to remind ourselves, I don't have a pretty little, rectangle any longer. I now have this curve that's that is a hyperbola. And I want to find, again, this is the pressure volume PV diagram. And I want to find, I'm going to go from, let's say, A to B. And I want to find the work. There's going to be a V sub A, or we'll call this state 1 to 2, we'll say. I'm going to go from 1 to 2. This will be V1 volume at, of the system at, the system at this particular state has a volume V1, and the system at this particular state has a volume V2. Okay, so now I want the work. I want the work, which is the area under this curve. And I can't just go to, I can't just say it's length times width. I mean, this is not a rectangle. This is a hyperbola. How do I figure out the area? Well, I have to employ integral calculus. So what do? Well, you find the work as what? The integral from volume 1 to volume 2. Let me just. I need space. So again, if you don't understand the calculus, that's okay. For those that do, I mean, again, I just want to do a complete job here. So the integral from volume 1 to volume 2, P times dV. And I know what P is, right? I know because the ideal gas law. So what is P? Well, it's going to be nRT over V. dV. And nRT is a constant, pull it out. Work is nRT integral V1 to V2 of dV, the differential over the volume, V. And of course, if you've had calculus 1, if you had calculus 1, you'll see this, we recognize this as a natural logarithm. So this would then be that the work will be nRT, let's see, work. We do this integration as we do in calculus. We found that the work is nRT times the natural logarithm of the absolute value of the bigger volume, or volume 2, minus the natural logarithm of the absolute value of volume 1. Again, these volumes are positive by nature, so I mean, again, in general, you want to do absolute values in a situation like this, but we can forego the absolute value sign. So we know that. So we know V1 and V2 are positive. They're volumes, so physically they have to be positive. So we can neglect the absolute value signs. You can pull, so again, at this point, we have the work is nRT times brackets natural log of V2 minus natural log of V1. And as I've said in the past, you can only do 3 things with logarithms. And so again, as I said, if I have natural log of V2 minus natural log of V1, what I can do is I can combine those as a division. So the work is nRT times the natural log of the first divided by the second if I have subtraction. V2 over V1. Isothermal work in an isothermal process, going for an ideal gas and going from basically from the P1V1 to the P2V2. Okay, so again, isothermal, that's the work. Okay, so that is the formula you get in your book. It's not by magic. It's determined by adding up the area under the pressure volume in the PV diagram. In this equation, this formula is only good for an isothermal process. All right, and so I'm developing a set of tools here, or a set of information. And so what do I have right now for my information? Well, I'm able to calculate various work, right? I have work, let's see, for isobaric, the area of the curve, well, what's that going to be? Well, it's going to be work is a constant pressure, whatever that is, times the change in volume. Isobaric, quite easy. Area of a rectangle. Isochoric, constant volume. Work equals 0. Since the volume is constant, delta B is 0. Isochoric. Isothermal. Again, keep in touch here, it's ideal gas. Okay, isothermal, work. nRT, that constant temperature T, times the natural logarithm of the final volume divided by the initial volume. This could be a negative number. If V2 is less than V1, work, I mean, a natural log of a fraction is negative. The work could be negative. If V2 is greater than V1, work is positive. Right? But this is the formula strictly for an isothermal process. Has to be isothermal to use that formula. Okay, so we're developing our ways to calculate the work in the PV diagram. Then we want to go to adiabatic, but we have one more thing we have to talk about, is we have to revisit these specific heat, but we're going to actually talk about what's called a heat capacity. All right, so kind of keep these in mind. We have to take a little detour here and talk about what's called a heat capacity. All right, so let's do that next. All right, heat capacity. Of an ideal gas. Okay, now we need to talk about these in order to be able to give expressions and an actual physical form or mathematical form to the adiabatic process. That's why we're doing this. So it's a little detour. All right, so we know, talk about what we know. We know from the kinetic theory of gases, which we talked about in chapter 14. All right, that the internal energy we've talked about this already even today of an ideal gas is U is 3/2 NA KT. Or I'm sorry, we'll say nRT. We'll do it in moles. Okay, monatomic ideal gas. One atom. Okay, so again, N, number of moles of the ideal gas. R is 8.31 joules per mole Kelvin. That's the gas constant. T, absolute temperature. All right, so again, going back to the ideal gas, that is the internal energy. All right, so we know this. We also know just from chapter 13, actually no, chapter 12. In chapter 12, in our very first thermophysics chapter, we know, and we're going to express this in a molar sort of way, that Q is N C sub V delta T. Okay, C sub V, again, N is the number of moles. C sub V is called the molar heat capacity at constant volume. So the important thing is, in this system, you're holding the volume constant to make this measurement. Molar heat capacity at constant volume. Okay, so again, it's like we saw MC delta T, right? And so we're looking at it a little different way. So what we saw back in chapter 12 is we saw what was called, we did a similar kind of expression. We can, is that we said that Q, so in chapter 12, we said that Q was MC delta T, and we said that C, we call that the specific heat. Well, when we call it specific heat, the book and I left off a term in there. It really would be the specific heat capacity. That's really what we're talking about. So in reality, there is a heat capacity that depends on just the mass, not the number of moles. And I would actually refer to this C as a capital C over the mass. Okay, so in physics, when you talk about thermodynamics, particularly, specific, when you see something that says specific, it means per mass. That means that this is the heat capacity. You're dividing by the mass of the system to get the specific heat capacity. So what you're really doing is, instead of MC delta T, you could have written this instead. you could have called this capital C delta T, right? And so, but we always have specific heat. So the way that we normally do it is by specifying the mass and the C. But hypothetically, you could be, I'm sorry, little c. You could be talking. You could just, instead of little mc, you could just put in a capital C, because little c and also your specific quantities are typically small letters. All right, so you use small letters for specific quantities, and the capital letters that are not. So it knows a capital C for the heat capacity, that's the mass heat capacity, and the little c for the specific heat capacity. So that's what you saw in the past. Now we're gonna dress this up as molar heat capacity at constant volume. That little v there reminds us that we're keeping the volume constant when we consider this particular calculation. All right, so let's go. So now that we define these, let's go back to the first law of thermodynamics. All right, so I'm going to erase all this. We have to remind ourselves what these equations are, but I need real estate. So, all right, so let's go back to the first law of thermodynamics. All right, to remind ourselves, delta U is Q minus W. Okay, now, and I can say here, well, let's see here. I know that we're talking constant volume. So for constant volume, W, which is some sort of pressure times the change in volume, well, that's zero if it's constant volume. It means the volume is not changing in this particular process I'm considering. Constant volume means that the work is zero. So that really gets down to is that delta U equals Q. The W has gone away. Talking about a constant volume process, so there's no work being considered in this particular case. Now remind ourselves here, delta U. Remember, we're talking about Q. Sorry. Remind ourselves that Q is NC sub B delta T. I wrote that down a moment ago. And so in this particular case, in delta U is 3/2 nRT, or nR delta T in this particular case. U is 3/2 nRT, delta U is 3/2 nR delta T, right? And so again, this is for an ideal gas. We're assuming an ideal gas. Well, let's put everything together. So we have, let's see here, delta U is what? 3/2 nR, let's see. So C sub B, one second. Let's solve for C sub B. So solving for C sub B here means that C sub B will be Q over, so Q over what? N delta T. That's solving for C sub B, or we'll say 1 over N. Actually, yes. Let me 1 second. No, by definition, C sub B, given that Q is the same as delta U, Q is the same as delta U in this particular case, I can substitute right here. And for this particular case, I can write the delta U as NC sub B delta T. And if I solve for C sub B, I can write that that's going to be 1 over N delta U with respect to T. Delta U over delta T. All right. And if I know what U is, so delta U is going to be NR delta T. That's going to be 1 over N times what? Delta U over delta T is going to be 3 halves NR delta T all over delta T. Delta T's cancel. These N's cancel. And I find out that C sub V is 3 halves R. Or 3 halves times 8.31 joules per mole Kelvin. And that's going to be 12.5 joules per mole Kelvin for an ideal gas. So molar heat capacity, constant volume for an ideal gas. And this is the molar heat capacity. At constant volume for an ideal gas. All right. C sub V, 3 halves R. Nice and simple. What is R? 8.31 joules per mole Kelvin. So what did I do? I went from the first law of thermodynamics. I know that if I have a constant volume process, the work, which is the pressure times change in volume, well, constant volume means there's no change in volume. So delta V is 0. So that means that delta U is Q, same as Q. In that particular case, then that I'd find out that, and then here I know that if, well, delta U is Q, and I know that Q is N C sub V delta T, which I just gave you before. So the number of moles times the molar heat capacity at constant volume times delta T. Well, I can just substitute U in there because they're equal. I can write this. No, I can solve for C sub V, 1 over N delta U over delta T. And oh, by the way, I know what the delta U looks like for an ideal gas is 3 halves NR delta T. And I can cancel out the delta T's, cancel out the N's, and C sub V is just 3 halves R, or 12.5 joules per mole Kelvin. It's a nice constant calculation. Give me 1 second here. Okay. Now we consider a different process. This is constant pressure. All right. So remind ourselves what C sub V is. These are things I need to develop. Okay, now we're going to consider a situation of constant pressure. We just did constant volume. What about constant pressure? All right, in that particular case, I would write what? I'd write that Q is N C sub P delta T. Same look, right? But C sub P, capital C sub P, is the heat capacity at constant pressure. In the same form, it's actually the, well, let's be more specific than that even. It's the molar heat capacity at constant pressure. So we're holding the system now at constant pressure. Before it was constant volume. All right, and so now we have to take a look and say, well, we go back to the first law of thermodynamics. And again, delta U equals Q minus W. And what I can say then is like, well, I can solve for Q. Q is delta U plus W. Simple as that. Well, I know what so again, I know what Q or we can say delta U plus W is Q, I guess. So Q again, delta U is Q minus W. That's the first law. And I can say then that basically that that W or delta U plus W equals Q. Well, let's see here. I know what these forms look like. So in this particular case, well, I know that that if I have a constant volume process, and we've seen this before, constant volume means isobaric process. That's going to look like P times delta V. I know what that looks like. I just got done telling you what Q looks like. So I could say, well, the delta U plus a P delta V is going to be an NC sub P delta T. Okay, all I'm doing is I'm using the form of the heat for molar heat capacity at constant pressure. And since I know that, but before I put a 0 for work because it was constant volume. Now it's constant pressure. Now I have to look at an isobaric process. So it looks like this form. All right. So now remind ourselves now that we have an ideal gas law. So ideal gas law, we know that the form of U is nRT, right? And so, or actually 3/2 nRT. Well, actually, let's look at the ideal gas law itself. So, ideal gas law. So going back to the ideal gas law, we would say that P delta V has a particular form. It's nR delta T. All right, so PV equals nRT, but if I'm keeping the pressure constant, the only variables I can change are pressure, volume, and temperature. Well, if I keep the pressure constant, which is what I'm doing here, then if I change the volume, I'm going to have the corresponding change in temperature, since N and R by definition are going to be constant, right? And so if I do that, then I can say, okay, well, assuming this, we can say, well, let's just take the change in volume. Or sorry, let's take this equation and let's consider taking the change with respect to the temperature. So I'm going to essentially take the change in temperature on both sides. So this side's easy, delta T's cancel out, all right? Well, if I take the change in temperature here, I essentially know that that U, so let's kind of go back to what I had before now. So I have this. Now, if I remember, just from before, that delta, so what is U now? Well, so again, U depends only on temperature. So again, we're, for an ideal gas, U only depends on temperature. We said this a few times now. So in this particular case, then we would say, well, we know that that's the case, then I can, and that's irrespective, again, irrespective of restrictions. on pressure and volume. So irrespective of that, if it's an ideal gas, it depends strictly on temperature. All right, and so what I remind ourselves here is from before, to be heat at constant volume was, remember, it was 1 over n. Look up in your notes a little higher. Delta U with respect to T. That means that I have this delta U with respect to T. I can substitute directly and say, well, this is just going to be n times C sub V. So that implies then that delta U with respect to T is just n times C sub V. I see on the right-hand side, I have n times C sub P. Well, here, delta V with respect to T, well, what is that going to be? Well, again, P. So again, I see that I said delta U with respect to T, I can write n times C sub V right here. And then what about the ideal gas law? So again, pressure times the change in volume is nR delta T. If I'm looking at PV, if I'm taking delta T on each side, that means that this term is nR. So instead of delta U with respect to T, because of this relationship, for the that I get from the specific heat at constant volume, and again, this is a relationship because of an ideal gas. I'm always going to get this. So instead of the right hand, instead of this term, I can write instead NC sub V. The second term, P times delta V with respect to T, I can write NR. And the right hand side, I can just read that NC sub P. And of course, I can cancel out my N's, and I have a nice relationship. That C sub P, the specific heat at constant pressure, minus the specific heat at constant, the heat capacity at constant pressure, minus the heat capacity at constant volume is equal to the gas constant. So again, C sub P is the heat capacity at constant pressure. C sub V is the heat capacity at constant volume. I take their difference, I get the gas constant. Okay, this is a very important relationship. I'm going to use it later. All right. Okay, so now what we're going to take a look at is another very important concept that came straight from the Maxwell-Boltzmann theory, or the Maxwell theory of the kinetic theory of gases. Okay, so again, this relationship here, heat capacity, constant pressure. You can look that up in a book for any kind of substance. Heat capacity, constant volume. Okay, don't get it mixed up with specific heat. It is a molar heat capacity. So this is the molar heat capacity, constant pressure. This is the molar heat capacity, constant volume. All right, so let's, again, the gas constant is something that is molar. So again, let's just kind of remind ourselves what this means, and then we'll move on. Again, for an ideal gas, so for an ideal gas, we just wrote that C sub V minus C sub P equals R. C sub V, remind ourselves, molar heat capacity at constant volume. C sub P, molar heat capacity at constant pressure. And of course, R is the gas constant. Okay, so again, very important relationship. Now, we've been restricted so far to monatomic ideal gas, but we can actually, and again, what we can do now is consider other types of ideal gas, other types of gases, not necessarily monatomic. All right, and so what happens is, though, that when you do that, the Maxwell theory breaks down a little bit, and they have to fix it up. So Maxwell had to fix up his theory. So again, C sub V, as I just got done calculating earlier, equals 3/2 R, right? Agrees with experiment for monatomic gases. We just computed this earlier. Right. So C sub H 3/2 R. You look at the experiment. For monatomic gases, but then Maxwell, James Clerk Maxwell, extended his theory. Extended the theory, the kinetic theory of gases, to allow for polyatomic molecules. Okay, so how did he do this? Well, essentially, we have what is called the equipartition theory, theorem of energy. So Maxwell employed what he called the equipartition theorem. Of energy. All right, that's what we're going to talk about next. Equipartition theorem. We've been talking about monatomic ideal gas all the way up till now. But we want to actually make the theory more general for other kinds of gas molecules. Okay, we've been talking about gas atoms, really, and if we really do have a molecule, we've been considering it as acting like a monatomic atom, if you will. So even like in the case of, we had an earlier problem, we were talking about the helium in the solar corona. We had a problem in chapter 14 about that. Well, the helium is a diatomic molecule, but we consider it like a monatomic, gas, just to be able to do the calculations. We haven't talked about the equipartition theorem, equipartition theorem yet. So let's do that now. All right. So Maxwell had this very important theorem that he put across in the kinetic theory of gases. All right. So Maxwell's theorem for the equipartition of energy. Okay, so his theorem is worded like this. Every kind of molecule has a certain number F. Of degrees of freedom. Which are independent weights . in which it can store energy. Each such degree of freedom has associated with it on average an energy of 1/2 kT. Per molecule or 1/2 RT per mole. Okay, so rereading this, Maxwell's theorem of equipartition of energy. Every kind of molecule has a certain number F of degrees of freedom, which are independent ways in which it can store energy. Each such degree of freedom has associated with it, on average, an energy of 1/2 kT per molecule or 1/2 RT per mole. Well, what does that mean? Well, first of all, we've been talking about monatomic ideal gases. So in this particular case, a monatomic or a simple atom can only have 3 independent ways of moving. All right, so a simple atom we'll say monatomic atom can only move in 3 ways. Remember, objects can move via translation, rotation, or oscillation. All right. Well, when you have a monatomic atom, it's really like a point particle. So it can only move in 3 directions. It can only move in translation, in the x direction, or the x coordinate, the y coordinate, and the z coordinate. And that's it. No rotation is possible. So again, a monatomic atom is considered as a point particle with no physical extent. So no rotation or oscillation is possible. Again, we're talking about an atomic theory here, or molecular theory. All right, and so what we're talking about here is that, well, the object can move in the X, Y, and the Z directions. That's 1, 2, 3 degrees of freedom. So a monatomic atom has 3 degrees of freedom. Associated with X, Y, and Z translational motion. Well, what's the energy corresponding to that? Well, as you look at the equipartition theorem, every degree of freedom is associated with 1/2 kT. All right, so in this particular case, well, every degree of freedom has 1/2 kT associated with it. So every degree of freedom has energy (1/2 kT). So how much energy for monatomic ideal gas? Well, a monatomic ideal gas has internal energy of U, 3 degrees of freedom, times 1/2 kT for each degree of freedom, or 3/2 kT. Well, okay, let's get more complicated. Let's talk about, let's say something like a oxygen atom, or sorry, oxygen molecule. All right, so let's talk about something more complicated. We have an oxygen molecule, for instance. Now. So now consider a diatomic molecule. Like oxygen, O2. And oxygen always comes in a pair. Looks like a dumbbell, right? There's a atom over here, O, connected, another atom, O. Okay, it looks like a dumbbell. And about, let's say, some axis. This is our O2. Well, now we have physical extent. So O2 can move via translation in X, Y, and Z. So that accounts for 3 degrees of freedom. One, two, three, X, Y, Z, right? But now we have physical extent. The oxygen can basically rotate about the axis that I have shown here, or the oxygen can rotate about an axis coming out of the board. So here's one rotation that the oxygen molecule can do, basically along about that vertical axis, and another rotation about an axis into the board. Now you might say, well, what about the rotation about the line connecting the two? Well, there's very, very, very little moment of inertia about the line connecting the oxygen, so that doesn't really matter. We don't really count that. There's a bigger moment of inertia for this motion, essentially, and this motion. You have a rotation about the vertical axis, right? Just like that. Rotation about a horizontal axis like this, and this rotation about the line connecting the two oxygen atoms do not matter. Again, there's not enough moment of inertia. All right. So there are two rotations. So there is a rotation about of O2 about the vertical axis shown. And a rotation of O2 about an axis perpendicular to the whiteboard. Now, again, the rotation about an axis connecting the O's does not count since the moment of inertia about that axis is so small. All right, so in that case, what do we have now? 3 degrees of freedom from translation plus 2 degrees of freedom from rotation, since the other rotation about the axis of about the line connecting the two O's is does not apply. So we would expect there to be 5 degrees of freedom for this situation, right? And so we get 3 from translation and 2 from rotation. So 5 degrees of freedom. From O2. 3 from translation. Plus 2 from rotation. That's equal to 5. So how do you figure this out? Well, according to Maxwell's theory of equipartition of energy, the internal energy would be 5 degrees of freedom times, well, how much energy per degree of freedom? 1/2 kT. Or 5/2 kT. Okay, so again, now if you considered a general shape or maybe a polyatomic, so again, this is a diatomic. This is good for, so this is for a diatomic ideal gas. Diatomic only. Monatomic, you can only move X, Y, Z. You get 3 degrees of freedom, or the internal energy is 3/2 kT. For diatomic, you get a dumbbell shape like this oxygen molecule, O2. You get 3 from translation as the object moves around as if it is a single particle, or the oxygen molecule, but then you get one from each of the rotations. But again, one of the rotations doesn't count because the moment of inertia about the axis connecting the diatomic molecule is so small. But for a polyatomic atom, you do get 3 rotations. You don't get to say that one of the rotations doesn't count. So for a polyatomic, you get 3 from translation and 3 from rotation. Okay, and so for a polyatomic molecule, consisting of 3 or more atoms, we get 3 degrees of freedom from translation plus 3 degrees of freedom from rotation and simple math says 3 plus 3 equals 6, equals 6 degrees of freedom. Okay, and so we can kind of show this pictorially. I'll do the best I can to reproduce my picture I have in my notes. So we have a situation where we just have a monatomic ideal gas like helium. So helium monatomic. In a situation we have diatomic like oxygen. Okay. Or polyatomic, like let's say methane. This would be an interesting one to draw. Let's see. Up here. A polyatomic. All right, hydrogen up on top of the pyramid. And what do we got? Okay, so we have hydrogen, so 4 hydrogens, the pyramid shape, and 1 carbon. This one's methane. So methane, CH4. All right. And so what can we say here? Well, we can draw a little table here. I can see molecule. I can write example. And degrees of freedom. Translation, rotation. I like to keep a picture up there too. So I have a molecule. Example. Translation. Rotation. and the total. And this will be degrees of freedom. All right. So I could have a situation of monatomic, diatomic, or polyatomic. Okay. The examples that I give, well, I have helium, noble gas, doesn't want to interact with anybody. So helium. I have oxygen, which comes in a form of diatomic molecule, looks like a dumbbell. Or I have methane, CH4 as an example of the polyatomic, as I've drawn above. So for helium, well, you get 3 from translation, X, Y, and Z. You get nothing from rotation. So again, this will be plus. You get nothing from rotations. You get 0. 3 plus 0 equals 3. 3 total degrees of freedom for the monatomic gas. For a diatomic, we get, again, remember, 3 from translation. You get 2 from rotation, because one rotation doesn't count because rotation about the axis that actually connects the 2 atoms in a diatomic molecule doesn't count. 3 plus 2 is 5. Then you have the polyatomic. Polyatomic, you get the entirety of rotation, 3. I'm sorry, everything from translation. You get all 3 rotations, that's 3. 3 plus 3 is, of course, 6. Okay, so this is how you compute the degrees of freedom. You have to know whether it's a monatomic, diatomic, or polyatomic gas. So then how does Maxwell fix up the, what's the general form for the change in the internal energy then for an ideal gas? Well, Maxwell says, and the extension of the kinetic theory with the theory of equipartition, Maxwell says that in general, the change in the internal energy of an ideal gas is given as F divided by 2 times nR delta T. F is the number of degrees of freedom. It's 3 for a monatomic, 5 for a diatomic, and then 6 for anything that's polyatomic. And so what does that mean? Well, then the heat capacity, constant volume. What is that? Well, again, that's 1 over N delta U with respect to the temperature. And that is how you figure out the heat capacity at constant volume. The molar heat capacity at constant volume. All right, well, what do we know? We say that, well, you have 1 over N, and see, delta U, well, that's that up there, right? That's F over 2 nR delta T, all divided by delta T. My delta T's cancel, my N's cancel. I figure out that the molar heat capacity at constant volume is going to always be F over 2 times R. R is the gas constant. If you work it out, it becomes 4.16 F, joules per mole Kelvin. That is the heat capacity, the molar heat capacity at constant volume. For an ideal gas, with F degrees of freedom. All right, so that is an extension of Maxwell's theory. But the thing about it is, you know, one of the things I kind of pointed out a little earlier in this class is that we're getting toward the end of Physics 1, which means we're flirting with Physics 2, if you will. We're starting to see, you know, and in Physics 2, when we talk about entering the 20th century, there are a number of unanswered questions, you know, in physics that could not be answered with the theories as known. So one of the unanswered questions was an interesting behavior that was seen for a diatomic gas. So we see that this theory is in general correct, except we have some strange behavior. And again, you know, we started seeing it, and this may actually be this first actual strange behavior that leads to the quantum theory of matter. There's other behaviors that, you know, we'll later talk about. I talked about black body radiation, you know, the work done by Max Planck, you know, and when we talk about radiation heat transfer, but that was like 1900. We're talking we're talking about in the 1860s. Maxwell saw this. So some people actually believe historically that Maxwell, and what I'm about to show you, laid down the initial seeds of quantum theory 40 years earlier than Planck. All right. So again, I think that some people have argued that the initial seeds of quantum theory were laid down by Maxwell, the great James Clerk Maxwell. So let's just see what we're talking about here. Let me try to draw a little graph here. So in this graph, on the vertical axis, I'm going to give you C sub V divided by R. So again, it's the heat capacity at constant volume divided by the gas constant. And I'm doing this for a diatomic molecule. I think in this particular case, it is hydrogen. This is actually going to be hydrogen. So hydrogen is like oxygen, right? It's another dumbbell molecule. It's H2. So basically, two atoms that are essentially connected, but you know, kind of think of a ball and sticks. You know, you can take two balls and connect them with a stick. And that's kind of like how you would make a hydrogen or an oxygen molecule in, like, you know, chemistry display. You know, chemistry set. So C sub V over R. Okay, now draw this over here. And I'm going to lay out some values here. I'm going to give a value of 3/2 along here, a value of 5/2, and then maybe we're going to give a value of 7/2. Now, I'm going to give the horizontal axis is going to be temperature. Now, you're talking about a diatomic molecule. According to the equipartition theorem, according to the enhanced kinetic theory of gases by Maxwell, I would expect to have C sub V over R to be 5/2. Just like I said before, I expect to have what? I expect to have 3 degrees of freedom from translation and 2 degrees of freedom from rotation. However, I only get 5/2. I mean, if you look at low temperatures, basically below 80 Kelvin, something interesting happens. I get 3/2. So I get 3/2 below 80 Kelvin. Again, we're talking hydrogen. And all of a sudden, we get this transition, a very fast transition. And then we go to 5/2. And we might say 5 halves, we might say that for ordinary temperatures, typically what people will say. So you have 5 halves, and eventually you get up around 3,200 Kelvin, you go very, very high in temperature. So your 5 halves at what we call the ordinary temperatures. And eventually, right around 3,200 Kelvin, you will, well, let's see here. You right before 3,200 Kelvin, you see one more transition, and it's transition up to 7 halves, and then it's at 7 halves briefly, and then the atom basically dissociates. It pretty much falls apart. And so at this point, you no longer have a hydrogen atom. At this point, it has dissociated. So H2 dissociates. To two H's. What on earth is going on here? You know, this region here we would refer to as, typically call it ordinary temperature. This occurs at a temperature of very high temperature of about 3,200 Kelvin. Is when you dissociate hydrogen. So you expect the hydrogen molecule to have the C sub V over R of 5 halves. However, for low temperature, 80 Kelvin and below, it's at 3 halves. So what Maxwell and others could not figure out is what is causing the molecule to suddenly switch. All of a sudden, it reaches this one particular level of energy, and it switches to 5 halves. Sudden switching. Nothing in the theory can predict this. And it turns out that what's really happening is quantum physics. What's happening here is that the energy levels, the rotational energy levels are quantized. They only come, you cannot get them. I mean, you have to have a certain level of energy before this particular quantum state is achieved. Now, again, this doesn't make any sense right now in physics 1, but rotational energy levels are quantized. You need quantum physics. So you have to reach a certain energy, no less than that energy, in order to essentially turn on these states. So here you have just translation. There's not enough energy for rotation. Here you have rotation. So the rotational energies being quantized, you cannot get any rotational energy unless you're at a certain basic level, a certain minimum level, a quantum of energy. And so again, the energies, we'll find out in quantum mechanics, energies come in amounts. They come in, they come in quantum amounts. You cannot get just any energy. They come in certain fraction or certain multiples of a photon energy called HF or h nu. The frequency of the corresponding electromagnetic energy or the photon, if you will, and H is a special constant called Planck's constant. If you have any energy, there's any energy in the system that's just any tiny fractional amount less than this energy, you do not get that energy state. You do not qualify to get that energy level. To qualify, you must have enough energy. You must be above that basic quantum of energy. And so nobody understood this. There was no quantum physics. Quantum physics was not going to happen for another 60 years, another 70 years, in fact. I mean, Albert Einstein wasn't even born yet. Okay, all these great quantum physicists weren't even born yet when Maxwell's doing this. All right, and so Maxwell, and then if you keep on adding, keep on increasing temperature, finally you go to the vibrational level. So actually, if you come to find out, when you understand quantum theory, that not only are you going to get the 3 degrees of freedom from rotation, but there's going to be 2 from vibration. You can vibrate this way or vibrate this way. So you have 2 polarizations of vibration. And so you get those as well. But the molecule can't stand enough, it can't stand any more increased energy. It just breaks apart right at 1300 Kelvin. So at that point, the game's over. The molecule breaks apart. You no longer have H2. Now you have 2 hydrogen ions. All right. So we're happy. We're seeing here is the seeds of quantum mechanics. Nobody can understand the sudden switching of energy levels. Nobody can understand why for a temperature below 80 Kelvin, the hydrogen molecule, which is basically a dumbbell, acts exactly as if it was just a monatomic ideal gas, because there's not enough energy to get to the quantum levels. So it turns out the vibrational energies are quantized too. So vibrational energies are also quantized. Well, Maxwell began to understand this. Unfortunately, Maxwell didn't live long enough to, quantum theory could have happened probably 30 years earlier had Maxwell lived longer. So anyway, vibrational energy levels are also quantized. Again, you need quantum mechanics, you need physics to understand. So, in September of 1899, I've told this story before, but Lord Kelvin was he was the elder statesman physicist representing physics at that time. It would have been Maxwell had he lived long enough, but Lord Kelvin, gave the State of the Union address, if you will, for physics, where we're going from the 1800s and we're entering the 1900s. And Kelvin gave what was the famous 2 clouds speech. He says, I feel sorry for future physicists trying to get their PhD and doing research because, well, we kind of have it all figured out. We have a very successful theory of mechanics. We have a very successful electromagnetic theory. And again, when you take physics 2, you'll realize that electromagnetic theory is nothing short of beautiful, absolutely amazingly successful. Then you have a very successful thermodynamics. So what else is there to do? We have a few more things to work out, and sorry, future physicists. Well, but he said, but we have we have 2 clouds on the horizon. One of these clouds will end up being relativity, which you're talking about, what's called a luminiferous ether. That I'll talk more about that in physics too. But they're trying to figure out how in the world does an electromagnetic wave get through outer space, and and how fast does it go? And this is where Albert Einstein came into play. And then you have this funny business with these quantized energies. Can't understand that. And then there's stuff like, what's this radiation coming out of nowhere? Like, this, it end up being nuclear radiation, where we have this pitch blend. We get this seemingly a violation of conservation of energy. We have this energy I could put my hand above it and I can see the bones in my hand. So what is that? So all these various things that, the little things that work out. Well, it turns out those are revolutions. They took up the entire 20th century, and they're still being studied today. So unfortunately, Kelvin could not be more wrong. But again, I wouldn't blame Kelvin. Kelvin was an absolutely brilliant physicist. He was just showing an example of the incredible confidence that physicists had at the time. They're kind of drunk on their own success to some extent. And so again, you always want to be careful, making assumptions that things you don't quite know about, or maybe you don't know about at all and you assume just make sure that when you say something in science, you're absolutely sure it's right. Or if it's wrong, at least you've shown that you've done every effort possible to be right. All right. So with all that said, I've developed the basics to talk about that 4th process earlier. We talked about in the thermodynamic processes. We already talked at length about the isobaric process. That's process of constant pressure. We talked about the process of isochoric process, the process of constant volume, and we've also talked about the isothermal process. And I know, and that's a process of constant temperature. I know how to figure out the work for all three of these processes. Now, what at this point I want to do is talk about the fourth process, which is the adiabatic process. All right, and so now that I have some background, let's talk about that. And the math is going to get a little advanced here for a moment, so do not despair. You'll find out that what you're needing to understand is the application of the final equation. All right. So again, let's talk about the adiabatic process. I go through this just to kind of show you there's no magic in physics. So we'll talk about the adiabatic expansion of an ideal gas. The ideal gas is going to expand adiabatic, which means without heat transfer. So adiabatic expansion of an ideal gas. And we have everything we need at this point to do this problem, right? So we start off with the first law of thermodynamics as usual. Delta U is Q minus W, first law. All right. Now, in general, we're gonna, again, when I say adiabatic, I'm not making any restrictions on pressure, volume, or temperature. I'm making restrictions on the actual heat transfer, either the cylinder or whatever the container which the heat transfer is occurring. Either it is very, very well insulated, which would cause heat transfer not to occur, or the process occurs so fast that there's not enough time for heat transfer to occur. All right. Either way, it's adiabatic. Right. But in general, I'd write my pressure as P times delta V, as usual. I'm sorry, my work. My work would be some sort of pressure, variable pressure times the change in volume. Again, I'm expanding. I'm expanding from, remember the adiabatic process I drew in the PV diagram. I'm going from some V1 to some V2. And my pressure is not constant, it's variable this time. All right. Now, if I look at this, I say, well, if I combine these two equations, I get that delta U, the change in the internal energy, is Q minus P delta V. All right. However, as I just said, it's adiabatic. Talking about adiabatic expansion this time. What does that mean? Q equals 0. No heat transfer is allowed. All right, and so what I now have is that my first law of thermodynamics reduces to delta U is negative P delta V. All right, and I also know from what I just got done talking about is that delta U, again, we're talking about what? Ideal gas. So for an ideal gas, delta U is N C sub V delta T. Again, number of moles, the molar heat capacity, and constant volume. Again, that little V means constant volume. This particular case, delta T. Again, I can always say this irrespective of restrictions, because the internal energy strictly depends on the change in temperature. All right. So if I combine these two, I can then say that, well, instead of delta U, I can basically substitute. So I'm going to substitute right here. And I can say, well, instead of delta U, I could write NC sub V delta T. NC sub V delta T on the left-hand side, and that's going to be negative P delta V. All I did is I took the formulation or the formula for the change in internal energy for an ideal gas, strictly depending on the change in the temperature, and I substitute that into the first law of thermodynamics. And again, because I'm talking about adiabatic expansion, Q went away. The right-hand side only has negative P delta V there. All right, so again, no trickery, nothing up my sleeve. All right, now what I'm going to do is all I'm going to do now is just divide out. I'm just going to divide out the C sub C sub B just algebraically. So I'm going to divide both sides by C sub B. So N delta T, and then you'll see why I'm doing this in a minute. It's going to be negative P over C sub V times delta V. All right. And I'm going to put a little star next to this, and I'll talk about equation star later on. All right. So when I talk about equation star, you'll know what I'm talking about. So what I did is I was kind of, retract what I did, or not retract. I'm sorry. Repeat what I did. Getting tired here. All right. So again, first law of thermodynamics. I start off with that as I usually do. I know that there is no restriction on work, so work pressure is a variable. I'm literally going to go from one volume to another. Again, I'm going on what's called an adiabat. Essentially in the PV curve, I'm going to go from, I'm basically taking, and I showed you this picture. I'm literally going along an adiabat, and so again, going from V1 to V2 in a PV diagram, right? And so pressure is certainly going to pressure will certainly change. It's variable. Again, you remind yourself, that curve I drew, the ABC curve, I drew a isotherm and adiabat, both extending from the same initial state A, right, in the PV diagram. That's, you think about that. So P is variable. Given that Q goes away in an adiabatic expansion, then my first law of thermodynamics is just that the change of internal energy is negative P delta V. And I also know that because it's an ideal gas, that I can write this expression down. N C sub B delta T. C sub B there's the heat capacity at constant volume. I combine the two, and I essentially, so instead of saying delta U, I write what the formulation is because it is an ideal gas. And all I've done is I've just solved for N delta T, right? And I put a little star next to it saying, now I'm going to go back to that equation in a little bit. All right, so we'll try to put that one on we'll remember this. Okay, so again, write this in your notes. That's equation star. All right, I need real estate. Okay, so here we go. I'm going to erase all this stuff now. We'll remember good old equation star in a moment. All right, now remember an ideal gas. So let's go back to the ideal gas. And I know that it is given by the equation of state P equals nRT. Okay, so we know that for an ideal gas, and so what we're going to do is we're going to vary. We're going to do a variation. I mean, essentially, it's like a differential in calculus. So I'm going to vary the left-hand side. So I'm going to vary. So left-hand side, I have two variables there, and so it's like the product rule I told you about earlier. I'm going to vary P, keeping volume constant, and then the next term I'm going to keep pressure constant and vary V. So I'm going to basically say, well, I have P delta V plus V delta P. I've applied a variation to each side. So basically it's volume's turn, leaving pressure constant, plus next term, it's pressure's turn to get varied, leaving the volume constant. Again, this is a variation, what's called a product rule in calculus. All right. And there's only one variable on the right-hand side. There's only one thing to vary on the right-hand side. So I have N R delta T. And all I'm doing is I'm just taking the ideal gas law and varying it in every way possible. I have no restrictions. Okay. I'm not calling it constant pressure. I'm not calling it constant volume. I'm not calling it constant temperature. The only restriction in this problem is that the heat transfer is 0. All right. And so as far as I'm concerned, I'm open game. I'm game for literally varying everything. All right. Unlike previous derivations. So I'm going to solve this for N delta T. So N delta T, all I'm going to do, I'm going to divide everything through by R, right? So I'm going to have P delta V plus V delta P, all divided by R. Okay? And let's remind ourselves for a moment from a previous derivation, remember that R, the gas constant, can be expressed in terms of the heat capacity. So recall that R is the difference of the heat capacity at constant pressure, the molar heat capacity at constant pressure, minus the molar heat capacity at constant volume. I derived that a little earlier. Instead of the gas constant can be considered as the difference of the molar heat capacity at constant pressure and the molar heat capacity at constant volume. So I can actually express that right here and write that N delta T is P delta V plus V delta P divided by C sub P minus C sub V. All right. And so there you have it. Now, remember when I did equation star, I essentially set that equation equal to N delta T. So what I'm going to do is I'm going to combine this equation with equation star. So you go back in your notes, let's combine it with equation star. All right, so I have this equation here. We're going to combine with equation star thus eliminating N delta T. All right, so combining with equation star, what am I going to do? Well, so equation star was what? Well, the right-hand side of equation star was, if you're looking back at your notes, it was negative P over C sub V times delta V. And what else is equal to N delta T? Well, this stuff. So it's going to be P delta V plus V delta P, all divided by C sub P minus C sub V. All right. So what I've done is I've now taken two approaches to write two equations. I've eliminated N delta T, and now I'm left with this equation. Okay. Now what's left to do? Well, I have this. Now, what I'm going to do at this point is I'm going to do some algebra. I'm going to clean this thing. I'm going to clean this up. So the first thing I'm going to do is I'm going to essentially break apart the first. I want to put all the delta V's together for the moment. So I'm going to put anything that's delta V and put it together. I noticed that this entire first term is delta V. And if I were to break apart the right-hand side, I have delta V, and then over here in this term, I'd have no delta V's at all. So what I can do is I can break this apart. So I can have negative P over C sub V times delta V. If I break this apart, I have this numerator, P delta V, over C sub P minus C sub V, plus V delta P over C sub P minus C sub V. And the idea is I just want to separate the variables, right? So I'm going to put all the delta V's together. I'm trying to make rhyme or reason out of all this, right? So in so doing, I'm gonna put everything. So what I'm going to do is I'm going to multiply through by a negative sign. I want this to be positive. So again, I can do that. That becomes positive. This becomes negative. This becomes negative. I'm just multiplying through by -1. Nobody says I can't do that. And I'm going to put the delta V term on the other side. If I do that, I find out that I have 1 over C sub V P delta V. Okay, the other side, plus 1 over C sub P minus C sub V times P delta V. And then what's left, I'm going to leave the other term alone, minus V delta P over C sub P minus C sub V. All right, now, if I'm trying to add a couple of different terms, notice I have a P delta V and a P delta V. If I want to combine the two, what do we know we always have to do? We have to get a common denominator, just like we would any other time we're adding fractions, right? So I'm going to get a common denominator here. So let's get a common denominator. And of course, that common denominator would have to be, given that, we'll look at this here a little more closely. So the common denominator, yeah, we're just adding a couple of fractions, right? It doesn't look like it, but we really are. The common denominator for the left-hand side well, I have C sub B in the denominator, or C sub B minus C sub B. Well, the product of the two would be the common denominator. So it's got to be C sub V times quantity C sub P minus C sub B. I got to fix it up to do that. So what's this term missing? Well, this term is missing a C sub P minus C sub B. So I got to multiply top and bottom by it. All right. So I'm going to have, let's see, C sub P minus C sub V, P delta V, divided by C sub V times the quantity C sub P minus C sub V. All I've done is I've multiplied top and bottom of this term, because this term is missing. If I want to get common denominator C sub V times C sub P minus C sub B, I need to multiply the top and bottom by C sub P minus C sub B. So that's all I did for that first term. And I'm just working on the left-hand side of the equation. This second term is missing C sub V. So this one I got to multiply top and bottom by C sub V. So again, I'll have C sub V, P delta V over C sub V times C sub P minus C sub V. And the right-hand side is going to be left alone. I haven't done anything to the right-hand side. The right-hand side is going to be nothing more than negative V delta P over C sub P minus C sub V. Okay, and that's all I've done. Now I can combine the two. And if I combine the two, something, at least I have some cancellation happen. But look carefully. I have a negative C sub V. Well, let's just multiply it out, right? So I have on the left hand, this over here, I'm going to combine everything. So I can essentially distribute. So I have C sub P, P delta V. All I'm doing is distributing through algebraically, minus C sub V, P delta V, and then plus the other numerator, C sub V, P delta V, all divided by C sub V times quantity C sub P minus C sub V. And the right hand side, I have what? I'm so far I haven't done anything to the right hand side. I have negative V delta P over C sub P minus C sub V. All right, so something nice happens is the C sub V terms cancel. So I can at least cancel these two terms out. That simplifies my equation a little bit. All right, so let's write the simplified version up here. All right, so I have something a little bit more simplistic here. So I have the left-hand side is now simplified to C sub P, P delta V over C sub V times quantity C sub P minus C sub V. The right-hand side is now negative V delta P over C sub P minus C sub V. Now, what I can actually do at this point is simplify even further. Notice that in the denominator on both the left and right-hand side of the equation, I have a common C sub P minus C sub V. I can cancel those two out. All right, what am I left with now? Things are getting simpler and simpler. C sub P over C sub V, P delta V is negative V delta P. All right. Now, I can put them all on the same side. So I have C sub P. Do I have enough room here? Over C sub V, P, C sub P over C sub V times P delta V plus V delta P equals 0. I'm getting closer and closer. Now, let's go back to, we're going to do one more thing. We're going to divide each side of the equation now by just PV. And all I'm doing right now is algebra. Okay, we're down to here, trying to simplify things. So we're going to do now is we're going to divide both sides by the equation by PV. So divide both sides of the equation by PV. If I do that, I get C sub P over C sub V times P delta V divided by PV. Okay, plus V delta P divided by PV. And of course, anything 0 divided by anything is just 0. All right, now what's nice is the first term, the P's cancel, and the second term, the V's cancel. All right, so what do I get now? Well, I get V's canceled, and this one I'll write this first term. Doesn't really matter how I write it. So what I'm left with is delta P over P plus C sub P over C sub V times delta V over V equals 0. All right. Now I'm going to define this ratio of molar heat capacities. I'll call it gamma. So again, this is typically done in thermodynamic textbooks. Gamma, again, this is a little g in Greek, is C sub P over C sub V is the ratio of molar heat capacities. Typically, you'll be given this number. Again, it's the heat capacity, the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. Typically, oftentimes, you'll be just given the ratio of the two. And so, and we can do one more, so we can write this one more time. As now delta P over P plus gamma delta V over V equals 0. So again, new Greek variable, right? It's a Greek G. The capital would be this, that's gamma. We call it gamma. The capital is capital gamma, the little case is little gamma. All right, so again, we physicists have to, we can't, our own alphabet isn't enough. We have to borrow other people's alphabets, right? So we borrow the Greek alphabet. All right, we're gonna do one more thing. We're gonna pass to the differential limits. We're going to pass the problem, so pass to the differential limits. Essentially, we're going to invoke calculus. So we're going to make the deltas really, 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 really small and infinitesimal, and we write that dp over p plus gamma dv over v is 0. That's what this gets down to. So we can then rewrite this equation as dp over p is negative gamma dv over v. And the next thing you'd want to do is you'd want to employ what's called integral calculus. So we want to do an integral. Again, if you don't understand integral calculus, that's okay. We're going to get a final answer, and that's what I want you to understand. I just want to let you know there's no magic in physics. So effectively, you would employ integral calculus. And these are fairly simple integrals. Gamma, remember, is a constant. So you'd have the integral of dp over p is negative gamma times the integral of dv over v. And of course, anybody who's had calculus 1 would know that these end up being natural logarithms. So you'd have the natural logarithm of the pressure equals negative gamma natural logarithm of the volume. And then, of course, since you're not doing what's called a definite integral, you'd have some arbitrary constant. Okay, so effectively what you'd end up getting now is you'd say, okay, well, I would exponentiate both sides. So what I'm going to get here is let me do this. I'm going to say the natural log of p plus, I'm going to take on the other side, plus gamma natural log of v equals a constant. And now one of the things, remember, I can only do 3 things with logarithms. I have the addition formula, the subtraction formula, and I know that if I have a constant potential natural logarithm of an argument, I can take that coefficient and move it up as a power. So I can actually write that this is the natural log of p plus the natural log of v to the power gamma equals a constant. And I can only do 3 things with logarithms. I showed you one of the things, that was the difference formula. Here is converting the coefficient to a power, that formula, and I'm going to do one more formula. Is that I know the addition. I know the addition to logarithms becomes a multiplication. So we're employing all of our rules of logarithms today. So now I have natural log of p plus natural log of something else. Well, this is the same as the natural log of a product of the two, p times b to the n. One more thing. I can now exponentiate both sides. So e to the natural log of p v to the gamma is e to a constant, which is just another constant. E to whatever that constant is just another constant, right? So e to the natural log, well, an exponential undoes the natural logarithm. I just get the argument back. So for adiabatic expansion, I get that p v to the gamma is a constant. That is the formula that applies for an adiabatic expansion. So that's the important formula for adiabatic expansion. So if I were to go and calculate, we're not going to calculate the work here, but if I were to calculate the work for an adiabatic expansion, what would I do? Well, this is the formula This is the relation between the pressure and the volume. I know what gamma is. Gamma is the ratio of the molar heat capacity of constant pressure divided by the molar heat capacity of constant volume. Volume to that ratio times the pressure is always a constant in an adiabatic expansion. That means that anytime I'm along an adiabat, I calculate this relationship, I get the same constant. Okay, that's what I get. So if I were to be so inclined to calculate the work, we're not going to do it here. But if I were to be so inclined to calculate the work, what would I do? I mean, again, I'm going back to calculator. But I would say, well, the work is the integral PdV. Oh, let's see, what do I know? Oh, yeah, sorry. I know the PV to the gamma is a constant. Call it C, whatever that constant is. Then I would say, well, what's P? Well, P is CV to the negative gamma, right? Getting multiply both sides by negative v to the negative gamma. And so I would go and say, well, the work, and it's going to go from volume 1 to volume 2. The work would be the integral from volume 1 to volume 2 of CV to negative gamma dV. I mean, so if I were to do that, it would be something like this. So I would add, so it would be like a C over a negative gamma plus 1 V negative gamma plus 1, something like that, right? So anyway, I know how to calculate the work. I'm not going to do that in this class. It's beyond the scope of the classes. This is too mathematically advanced. But it just lets you know that I have the ability to do it. All right, and so what are the important, by putting it all together for processes, what are the important processes? And so again, thermodynamic processes. Let's put everything together. Well, I have isobaric. Constant pressure. What do I know? Well, I know that the work is P and delta V. That's all I know. Isochoric. Constant volume. What do I know? The work is 0. Because delta V is 0. Change in volume means delta V is 0. I have to have the piston move in order for there to be work. The piston must displace. The piston does not displace, no work is done. Isothermal equals constant temperature. Work is nRT, natural log of V final over V initial. Now, adiabatic. Means no heat transfer. Okay, and what do I know? Well, I know that there's a relationship PV to the gamma is a constant. Now, the work is a little too complicated to calculate in this class. Gamma is the molar heat capacity of constant pressure divided by the molar heat capacity of constant volume. And this just kind of sums up all the stuff I've been doing for a while. Okay, now, one other important concept, particularly we're about to lead into the second law of thermodynamics. Another important concept as we talk about these processes is that we want to consider the concept of reversibility. Okay, so we want to talk about what's called a reversible process. Okay, so that's very important. Let's talk about what it is first. So reversible process. You know, a reversible process okay, is one in which both the system and its environment can return to exactly the states they were in by following the reverse path. Okay, this kind of gets into the concept of like we talked about a similar process when we talk about conservative forces versus non-conservative forces, right? If I imagine if I change my system and I have some sort of a, let's say I have some sort of a path in a PV diagram, and I take the process from A to B. So again, A to B. Well, what does this really mean? Is that I have a system. What this curve really represents is I have some sort of a piston, for instance. The piston contains a gas, and let's say there's a top of this piston where there's a mechanism for thrusting it, and it goes back and forth. Now let's imagine here that I displaced my volume and I changed the pressure, and then let's say I could just undo everything I did. So the system is at this state, I change it, then I just undo that change and I bring everything back to where it was as if I never did the change in the first place. I bring not only all the variables of the piston back or the system back, I also bring back the whole state of the universe. Everything around me, my surroundings and the system, all change right back to where they were as if nothing happened. It means I can go from one part of the path and I can just, I'm going from one part of the path, one path going from A to B, but it says, hey, I can take the system back to exactly the way it was by going B to A. And I have exactly what I had before as if I did nothing. All right, and so real macroscopic systems are not reversible. Now, if you go down to microscopic systems, you can get reversibility, but the problem is real systems are never perfectly reversible. All right, and so you don't get this real system. It's for something that's more complicated. You can't really do this. So real systems are not reversible. You really cannot do this. And the problem really comes down to is that, we'll kind of go from that concept and we'll just leave it at that. So what I want to do at this point is I want to start talking about the second law of thermodynamics. All right. So we're going to lead now to the second law of thermodynamics. All right. So we talked about the first law. We are going to begin discussing the second law of thermodynamics. But first, we need to motivate why we even need, or why we would even look for such a law. So, so you kind of imagine here for a moment that, we've talked about a lot in physics, but let me give you a couple of examples. So imagine I have a movie, and again, let's talk about the time when I used to have movie cassettes, for instance. Let's say you rent a movie at Blockbuster, and before you're done with your movie, again, many of you hopefully are not too young to remember Blockbuster, but you rent this movie, and hopefully most of you are not too young to remember getting video cassettes. Essentially video tape cassettes, but I still have many of them in my house. But you imagine that you rent yourself a movie at Blockbuster, you watch the movie, and of course the typical thing to do, or the courteous thing to do, or at least it's a Blockbuster rule, was to rewind your movie and return it back in a fully rewound, so that the Blockbuster employee doesn't have to go do it, or the next person who rents the movie doesn't have to put the movie in and start seeing the movie like 2/3 of the way through or toward the end, and have to rewind it himself or herself. Okay, it's just a courteous thing to do, and I think they even had a rule about it, right? And so imagine here that you have a movie, and then let's say you keep the video feed in the movie as you rewind it, and you get to watch the movie in reverse. So you see a funny situation. Watching a movie in reverse is always kind of funny, right? And so you imagine kind of like I don't know, say a situation where you have a cowboy coming into a saloon, and the cowboy goes into the saloon. Let's say it's a bad guy, goes in the saloon, he pushes open the saloon doors, and he takes out his pistol, he fires it into the ceiling. You see the unfurling of the smoke, you see the damage to the ceiling, you see the bullet going into the ceiling, and then you see a ruckus happening, right? People are overturning tables, people are throwing things. Let's say some lady throws a vase at the cowboy, misses him, hits the wall, shatters. You see a big bunch of ruckus going on. Well, let's imagine watching the movie in reverse. You watch the movie in reverse, and it's kind of ridiculous when you watch it, right? You see the shattered vase coming off of the wall, and going right back perfectly into the lady's hand, or you see the tables just all of a sudden turning right side up. Then you see the smoke and the bullet going right back into the cowboy's gun. The cowboy's walking backwards through the saloon doors, and the whole process looks kind of absurd. But the question I have is, why couldn't that happen? Nothing in the laws of physics that we've studied so far says that can't happen. Or how about this situation? I have a let's say a volume of let's say air, and I have this, all of a sudden I have this green puff of smoke that I set off into the corner of this volume, corner of a room, for instance. Now, what do you expect to have happen? Well, you expect this puff of smoke to, because of diffusion, to essentially fill up the whole room. Wouldn't you be surprised if all of a sudden all that smoke just suddenly sucked up into the corner? The question is, why doesn't that happen? I mean, it'd be very surprised if it happened, I'm sure. But the question is, why doesn't violate the first law of thermodynamics by any means? Or how about this situation? I'm sitting at a Starbucks, let's say. It's before we have COVID, so I can actually go into a Starbucks and actually sit there and study if I want. And I come in there and I have my physics books on my computer, and I'm totally happy. I got I have a nice hot cup of coffee. And I get into my studies and I forget about the cup of coffee after a while. and I realize I'm taking a little break here for a moment. I'm going to go to the bathroom, and I take a sip of my coffee, and it's no longer a hot cup of coffee, and now it's a lukewarm or cold cup of coffee. So I go to the bathroom and I come back, and to my surprise, I have a hot cup of coffee again. Now, what am I going to think? Well, I'm going to think, wow, what a nice barista. He or she, I guess they know I'm a regular, and they replenished my cup of coffee for me. That's very, very nice of them. Not once am I going to think, wow, spontaneous heating has occurred. I have a cold cup of coffee, and suddenly, magically, I have a hot cup of coffee. Spontaneous heating. But the question I have is, why can't spontaneous heating actually happen? What prevents it? Well, it turns out that a law of physics is a behavior of the universe is always true. It does not have a more fundamental cause. Well, the prevention of a behavior in and of itself is a behavior. So the fact that there seems to be an arrow in physics where it seems like the physics equations only go one way and not the other way, and the other way, the opposite way, is prevented, that's a law of physics. The prevention of a behavior in and of itself is a behavior. All right, and so I want to realize that the answer to all of my three postulations, if you will, or my three, the answer to my three examples is the second law of thermodynamics. Now, right now, all three of these examples don't seem to be related at all. We're going to find out that they're all very related, and they're all related by the second law of thermodynamics. So my motivation is, why do things happen one way and not another? All right, and so processes in physics seem to happen one way, but not the opposite way. Why? Example. Why can't I play the movie of life backwards? I mean, why doesn't that happen? Why does it look so ridiculous to us if I do that? Or why does a puff of green smoke in the corner of a room fill the room? But the opposite process does not occur. Or why can't we have spontaneous heating? Now, I'm going to have a little trouble coming up with a good statement of the second law of thermodynamics. And in my attempt, I'm actually going to, in my way of, or my method of doing so, I'm actually going to make I'm going to state four expressions for the second law of thermodynamics. It's going to only be the fourth one that's really going to be of use. You know, we're kind of spoiled. We're used to having a law of physics and then automatically using it. Well, we'll get laws of physics, but again, they are behaviors of the universe that are always true, that do not have a more fundamental cause. I mean, well, It's not nature's problem if we humans can't figure out a way of using it. If a law of physics is a law of physics. So the barista example that I had, or the coffee example, is in itself our very first statement of the second law of thermodynamics. So normally we're meeting face to face, I would have on the side of the board, I'd have the first law written down, and I'd have each of my attempts at the second law. We're going to have to kind of just, I can't do things the way I like to do things, so we're going to kind of go through the various attempts of the second law, and when I get down to the final version of second law of thermodynamics, I'll summarize everything. All right. So our first attempt at the second law of thermodynamics, I'll write it down. It is a legitimate. It is our most basic and, quite frankly, useless version of the second law of thermodynamics, but it is true all the same. So the second law of thermodynamics, the first version of it. Okay, so again, we're gonna make 4 statements for the second law, and as we progress, in fact, we're gonna realize that the first 3 statements are useless, and the last statement is the one that's gonna be useful. All right, and quite frankly, we don't have the language, we don't have the vocabulary yet to even speak about this, the last or the final version of the second law of thermodynamics. We're not there yet. Right. So the first law of thermodynamics is quite simple. Heat transfer occurs spontaneously from higher to lower temperature bodies. But never spontaneously in the reverse direction. All right, so my first version of the second law of thermodynamics. Heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. Well, okay, so this first version of the second law of thermodynamics is absolutely useless. Now you might say, when I first saw this, back when I was first studying physics, my first reaction was, come on, physicists. So you don't understand some things, you make it a law of physics. Well, hang on though. I mean, I would remember a law of physics, and I've said this many times, is a behavior of the universe that is always true, that does not have a more fundamental cause. This is true. Heat transfer. You will never see spontaneous heating. Heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneous in the reverse direction. You will never get a hot cup of coffee out of the blue. It'll never just happen magically. You'll never have spontaneous heating. All right, so that'll never happen. And it is because of the second law of thermodynamics. Now, again, I cannot do a problem with this. And there's nothing I can really do. It's basically a useful statement. It is a true statement, but it is useless. I mean, it's good for a cocktail party. If I want to talk to somebody and impress them in a cocktail party, I could say, hey, I know why you don't have spontaneous heating of your coffee, because it violates the second law of thermodynamics. Okay, that's about the only good use I could make of this particular statement of the second law. It is very much true. And it is true even when we get our 4th version, our final version, that it is useful. it is still going to be a true statement of the second law of thermodynamics. All right. Now, let's go back to heat engines. All right. So let's really talk about heat engines, and really we're at a point right now where we can really do them justice, because we're now talking about the second law of thermodynamics. All right. So that is the first version of the second law of thermodynamics. Again, we will see 3 more versions as we progress along. So now we're going to go into heat engines. I've kind of talked about heat engines briefly. We're really going to study them now. We'll see with heat engines, we'll see that we're going to have to employ the second law of thermodynamics some more. So again, as I said earlier, a heat engine is a device that uses heat transfer to do work. Okay, so we're utilizing the first law of thermodynamics. So what we would do is we typically will draw a little diagram that depicts our heat engine. So we talk about, we'll have a high temperature reservoir. Again, I've talked about reservoirs in the past. They're big enough where they can lose heat but still maintain their temperature. Call it T sub hot, high temperature reservoir. Okay, heat, again, it's a spontaneous process. So I'm going to make it like a little wavy arrow. Heat comes from the high temperature reservoir. We'll call that heat Q sub H. That's heat that is coming from the high temperature reservoir, Q sub H. It goes into the heat engine. So I'll kind of draw my heat engine as kind of like this circle, if you will. It goes into the heat engine. The heat engine does work. And the work is more of a directed, I'll make it more of a directed arrow, because work is something else that I can control more. Heat engine does work. And you have another reservoir, maybe the environment, that's at a temperature T sub C. Heat, waste heat or exhaust heat, goes into T sub C. And that amount of heat is Q sub C. Now, one of the things to keep in mind here is that this is the heat engine. And this is a diagram that you typically will see a lot. The little circle just represents a heat engine. This is high temperature reservoir. Or higher temperature, I guess. This is the lower temperature reservoir. I guess I'll say higher temperature. May not necessarily be high, but it's higher. Lower temperature reservoir. You gotta remember, a reservoir is an environment that's so big that it can lose heat or gain heat, and it's not going to change its temperature. All right, and so now one of the things to keep in mind here is that the change in internal energy for this particular process is going to be 0 because it's cyclical. All right, so a heat engine is a cyclical process. So heat Q sub C, or excuse me, Q sub H, is released from a higher temperature reservoir T sub H, the engine does work W, and heat Q sub C is released into the environment, or into the environment reservoir, I guess, if we will. At T sub C. All right. Now, an engine, as I've said before, is a cyclical process. That means it's constantly returning back, A, B, C, D, A, A, B, C, D, A. Essentially, what that means is that given that the internal energy depends only on the endpoints, the energy at A minus internal energy at A is going to be 0. Okay, this process is always occurring. This is the heat engine. All right, it's cyclical. It's a cyclical process. Okay, so again, keep this in mind. The heat engine is a cyclical process. In that it periodically returns to its initial state. So if I were to take the change in internal energy, remember, internal energy only depends, so internal energy only depends on the initial and final state. Or change in internal energy. So change in internal energy only depends on the initial and final state. It is a state variable. So if I'm returning back to initial state, then my delta U will be U initial minus U initial, because remember, in this particular case, final is initial, and that's 0. So the change in internal energy for a cyclical process is 0. All right. So that makes the first law, equal to the following. So again, if that's the case, if delta U for a cyclical process is 0, so for a cyclical process, the first law of thermodynamics becomes. So remember, first law of thermodynamics is delta U is Q minus W. But if delta U is 0, that means that W is Q. The net work is a net heat, or W, and this is net work, so net work equals net heat. So that net work is Q hot minus Q cold. That's your first law of thermodynamics for a heat engine. All right. So again, given that cyclical process, the change in internal energy is 0. That means that the net work equals the net heat. or the net work is Q hot minus Q cold. The heat coming into the engine minus the heat going out of the engine. All right, and so in this particular case, then you would want to define an efficiency. All right, and so you want to say, okay, well, if I know that I have heat coming in and you know, heat Q sub H going out, well, I'm going to define what is called an efficiency for a thermodynamic system. All right. We define an efficiency. So this is going to be called conversion efficiency is what it's called. We'll call it efficiency. So we want to figure out how good our system's doing. And like anything in life, you know, you want to figure out, well, efficiency was what? How good is something? Well, you know, what am I getting out of it? Divided by what am I putting in? Again, anything in life, you want to ask that question. You know, you might be asking that question about this class. What am I getting out of it? Compared divided by what am I putting in? All right. So in this case, well, let's see here. If you're talking about, you know, let's say an engine, what do you're probably going to be burning some sort of fuel to get Q sub H. You're paying for that. And what are you getting out of it? You're getting work. You're getting double. You're paying to, let's say this is describing the engine of your car. I'm putting my hard-earned money into the gas pump, and I'm getting gas out of I'm filling my car full of gas. I'm paying to burn that fuel. What am I getting out of the fuel is I'm getting Q sub H. That's what I'm paying for. What am I getting out of it? I'm getting work, W. I'm getting the work to drive my car, to put energy in my battery, to work, you know, my radio, my lights, and so on and so forth. I'm paying for W. So my efficiency, which I usually call EFF, what am I getting out? Well, I'm getting out work. And what am I getting in? What am I putting in? I'm burning gas. I'm paying for this Q sub H. Well, remember what work is. Work for a cyclical process is Q hot minus Q cold. So I can substitute the efficiency will be Q hot minus Q cold divided by Q hot. And I can essentially distribute the 1 over the Q hot, and I get that the efficiency is equal to 1 minus Q cold over Q hot. Rewrite this. So the efficiency is 1 minus Q cold over Q hot. Okay, so that's how efficient my engine is. 1 minus the ratio Q cold over Q hot. Oh, okay. So I really want to do as good a job as possible. I really want to engineer that. I really want to make this engine be really, really efficient. In fact, I want to do such a good job that I want to make the efficiency 100%. I want to make it 1. So what does that mean? Well, that means I want to make it such that Q cold is 0. I like to try to make an engine where I put no heat into the environment. Well, bad luck. You're limited by the second law of thermodynamics. Second law of thermodynamics says you can't do that. By definition, engines will always be inefficient. In fact, not only can you not do that, in fact, that will be our second version of the second law of thermodynamics. Is this inability that, I mean, if you make Q sub C 0, then you'd have efficiency of 1. But that's impossible. You can't do it. Second law of thermodynamics says so. So that gives us our second version of the second law of thermodynamics. Again, everything kind of looks cooked up so far, but so the second law of thermodynamics, the second version. Second version says it is impossible in any system for heat transfer from a reservoir to completely convert to work. In a cyclical process. In which the system returns to its initial state. All right, so another version of the second law of thermodynamics says it is impossible in any system for heat transfer from a reservoir, now the T sub H reservoir, to completely convert to work in a cyclical process in which the system returns to its initial state. Basically, what that says in legalese is that you cannot have Q sub C equals 0. All right, so Q sub C, what this really says is Q sub C cannot ever equal 0. That's the short version of that law. All right, and so all heat engines, by its very definition, must be inefficient. And most are very inefficient. All right, and so so the question really comes down to is like, well, let's get kind of an example of how we make a heat engine. We can't have any kind of efficiency, but let's kind of get an example of what a real heat engine might look like. Okay, we've defined so far what our overall pictorial diagram of a heat engine looks like, and also we've been talking about a couple versions of the second law of thermodynamics, and we've talked about all the various thermodynamic processes. So let's actually try to make a real heat engine, and so let's pick the one that's in your car. So the one in your car is called the Otto cycle. That's OTTO, named after, I don't remember the name of the person, but it kind of sounds funny and almost like you want to spell it AUTO like your car, but no, it's OTTO. So the heat engine in your car, the heat engine process, if you will, in your car is given by what is called the Otto cycle. Just kind of draw the PV diagram, what that looks like. All right, well, let's kind of All right, so anyway, I'm gonna erase this. I'm gonna draw the Otto cycle, and then I'm gonna kind of talk about the Otto cycle. So let's talk about the Otto cycle. I'll try to draw it over here. All right, the Otto cycle. Try to draw the PV diagram for it. This is a real cycle for an engine. So you go A, B, C, D, A. So, and this is a pressure volume PV diagram. You'll have adiabatic process coming up from A to B. An isochoric process from B to C. Then you have an adiabatic expansion from C to D. Then you have another isochoric process back from D to A. Okay, so these are adiabatic. And so your system is going to constantly be going, your car, as you drive your car, is going to be going always through this process over and over and over and over again the entire time you drive your car. All right, and so let's kind of look at this process first of all. So the process AB, and these are adiabatic. The CD and the AB are adiabatic. Okay, so, and then let's also kind of put in here, you're going to get Q hot in the BC. You'll get Q hot from this direction. And your exhaust in your car go out at CD. All right, so let's break this, and this is the Otto cycle. Okay, so let's break this down. Okay, so the AB, the adiabatic process AB, adiabatic process AB correspond is the compression stroke. So it corresponds to the compression stroke. And your pistons are constantly going down. So your compression stroke, expansion stroke, right? It corresponds to the compression stroke. Okay, and of your gasoline engine. Okay, then you look at so the work here, work done is so work is done basically on the system here. It's compressing, it's pushing the gas in. So work is done on the system. So in this case, the work is done on the system. You know, basically the gas mixture in the cylinder. Okay, and to increase the temperature and pressure. So you notice that the pressure is going to increase and the temperature is going to increase as well. It's an ideal gas. Okay, then you have the next one. You have BC. BC. Okay, so BC is heat transfer. So heat transfer Q sub H occurs at constant volume. Okay. And essentially, of course, it's very fast. It corresponds. So again, this process is very fast, and so it doesn't really change volume. Process is very fast and corresponds to burning of fuel. That's where your fuel gets burned. So your piston is down at this point. The piston has been compressed all the way down to its bottom of the stroke. At constant volume, the Q sub H enters the engine, basically at a constant volume. And then we have the adiabatic expansion. All right, so we go to adiabatic expansion now. So now we're going to go from C to D along adiabatic expansion. All right, so again, this is the combustion right here. The Q sub H is done. Combustion. This is the combustion process, and the Q sub H. Very important. Internal combustion engine. This is where your combustion happens. Okay, that's a fancy word for burning. Okay, now we go to CD. Is adiabatic expansion. Okay, and adiabatic expansion, that's where you do work in the outside world. So this is the work that's done to drive the car. Okay, and I'm just trying to, running out of room here. And finally, we're going now to DA. DA is going to be heat transfer. Heat transfer Q sub C to the environment occurs. So heat transfer Q sub C to the environment occurs for constant volume DA. That's your exhaust. So as your pistons are just going back and forth, you have AB, compression stroke. You get the combustion. You get the heat, Q sub H that goes from the burning of the gas, the combustion of the gas. Q sub H goes into the engine. You have an adiabatic expansion that causes all the work that gets done for the car, driving the car, putting energy into the battery, so on and so forth. And then you have the constant volume where the gas or Q sub C gets released to the environment and exhaust. That takes the pressure and temperature back to where it was before, back in A, and the whole process goes again. And so as you drive your car around, it's constantly doing A, B, C, D, A, B, C, D, A, B, C, D, on and on, constantly. Every single time your piston is going back and forth, you're going through this process, this auto cycle process, over and over again as your car drives. Okay, so again, engines are typically highly inefficient. So the question might arise then, okay, well, I get it. Second law of thermodynamics says that I can't have a perfectly efficient engine. Well, the next natural question would be, how efficient can the engine be? Okay, so that was taken up by a young French engineer by the name of Sadi Carnot. Okay, so we have to accept the fact that you can't have a perfect heat engine. So the question is, okay, how efficient can a heat engine be? I get it. Second law of thermodynamics says I can't have it be perfectly efficient. Well, how good of a job can I do? So how efficient can a heat engine be? So this is a question that was asked by Sadi Carnot. So French engineer, Sadi Carnot. You know, he died young, unfortunately. He lived from 1796 to 1832. Asked this question. Asked and answered, I guess I would say answered this question. So Carnot looked at he wrote a paper, and in this paper he essentially devised what we would call a Carnot engine. So Carnot, and Carnot, this name might be on a bonus question. Carnot devised an idealized engine. Which we will refer to usually as called a Carnot engine. You can't actually make one of these, but he was trying to figure out an engine that's as good as you could possibly do. And in this Carnot engine, you always want to look at things in a PV diagram. PV diagram for the Carnot engine. Well, in this Carnot engine, you would have, you'd go from A over to B, and then from B to C. So A, B, C, over to D, and then back to A. You'd have 4 processes in this situation. And in this upper process, you take in Q sub H. In the lower process, you would release Q sub C. Now we have the side processes, D and BC would be adiabatic. You have an adiabatic expansion. Here you have an adiabatic compression. And then these other ones would be isothermal. And this one is isothermal. Now, the important thing to take away in this is that this is what made Carnot engine very unique, is that all processes are reversible. Now, of course, we know we can't actually have a reversible engine, but in Carnot's perfect engine, every process here would be reversible. Now, by definition, isothermal and adiabatic processes are reversible. However, for an isothermal process to be reversible, it has to be very, very slow. And why do I say that? Well, imagine if you're heating up food. If you heat up food really, really fast and haphazardly, let's say you go and you have yourself some sort of a TV dinner or something, and it's frozen. You put it in the microwave, you heat it up, and you do it haphazardly. Well, what's the problem? Well, the problem is you're going to have hot spots and cold spots in your food. To really do a good job, you have to allow enough time for the heat to diffuse through the food in order to have the food become, to have a thermal equilibrium. And so you have to allow enough time so this to be a very slow engine. You'd have to allow enough time for isothermal process to actually occur. So this engine basically is impossible. But in reality, though, so this leads us to the third expression of the second law of thermodynamics. And so, because all the processes are reversible, if something was irreversible, it's irreversible because you'd have like turbulence, or you'd have some sort of friction that would dissipate energy. So let's kind of state why the processes, the best you can do has to be a reversible process. All right. So if a process is irreversible, then there must exist friction or turbulence that would dissipate energy. Turbulence and friction always dissipate energy. Out of the system. So if Carnot is to devise an ideal engine, then all processes must at least be reversible. I mean, if you're going to make something that's an ideal engine, let's get rid of any friction, any heat loss, or any energy loss due to friction or turbulence. Let's get rid of that right now. Let's do the best we possibly can. Okay. So first and foremost, you have to give yourself the best possible chance to succeed at this by at least eliminating any sources of energy dissipation. Any source of energy dissipation is going to cause the engine to be less efficient. Remember, efficiency is I'm putting Q sub H into the system. I'm trying to get the maximum work out. So if I'm dissipating energy because of friction and turbulence, that's just going to make the efficiency worse. All right. So this leads us to the third version of the second law of thermodynamics. And this is all due to Carnot's paper. So second law of thermodynamics, third version. All right, so what does that say? A Carnot engine operating between two given temperatures has the greatest possible efficiency of any heat engine. Between these two temperatures. Furthermore, all engines employing only reversible processes have the same maximum efficiency. Operating between the same given temperatures. All right. So read this again. Third version of the second law of thermodynamics. A Carnot engine operating between two given temperatures has the greatest possible efficiency of any heat engine between these two temperatures. Furthermore, all engines employing only reversible processes have the same maximum efficiency operating between the same given temperatures. Now, in Carnot's paper, Carnot did one better. Carnot told you what that efficiency had to be. So Carnot derived a relationship that's beyond the scope of this class in his paper. So we're trying to figure out what is this maximum efficiency. So in Carnot's paper, in his paper, Carnot derived an important relationship. Which will be used to calculate the maximum efficiency. Carnot said in his paper that in this paper he derived the following relationship: that the ratio of Q sub C over Q sub H, the heat going into the environment compared to the heat that's going into the engine. You know, heat going to the environment to lower temperature reservoir divided by the heat coming in from the higher temperature reservoir is the same for this perfect engine, is the same as the ratio of the Kelvin temperatures. Only for ideal heat engines. You cannot say this about any other engine other than one that is ideal. Now, of course, an ideal engine really doesn't exist, but that's why it's called ideal. But for an ideal engine, for the engine, the best possible engine you can ever create, operating between temperatures T sub H and T sub C, has this following relationship: that the ratio of Q sub C over Q sub H is the same as the ratio of T sub C over T sub H. And again, the T sub C and T sub H are in kelvins. They have to be absolute. What does that do for my efficiency? Remember, I calculated the efficiency. Again, this is the perfect engine. So for a perfect engine, I'll calculate the maximum efficiency now. Should be pretty easy. In general, the efficiency of any engine is 1 minus Q sub C over Q sub H, right? That's the efficiency of any engine. But the efficiency of a Carnot engine, the perfect engine, put a little C here for Carnot. Well, I would simply just take that ratio Q sub C over Q sub H and replace it with T sub C over T sub H. That's the ideal Carnot engine. That's the best I can possibly do. And if I want to get perfect efficiency, I would have to have T sub C equal to 0. And of course, that's impossible because of the third law of thermodynamics. All right, and so that's the best I could possibly do. So any engine operating between T sub C and T sub H, that's it. That is the maximum. And that really gets me the let's see, there's a fourth expression here for the Carnot engine. Oh, I thought I had it. Hang on a second. All right, anyway, that's an efficiency Carnot. I guess on the last expression, let me work some problems first. All right, so we'll do this. So we have 3 expressions. We have the Carnot efficiency. So let's do some problems to get our feet wet. All right, then we'll talk about the fourth expression for the second law. All right, so let's work a few problems, and then the problems for a while. OpenStax 15.20. All right, that says a certain heat engine does 10.0 kilojoules of work. And 8.50 kilojoules of heat transfer occurs to the environment. All right, in a cyclical process. A, what was the heat transfer into the engine? B, what was the engine's efficiency? All right, so a certain heat engine does 10.0 kilojoules of work and 8.50 kilojoules of heat transfer occurs to the environment in a cyclical process, typical for engines. What was the heat transfer into the engine, and what was the engine's efficiency? All right, and so again, this is a basic example of an application of the first law. All right, so let's kind of work some problems out here. All right, so well, I'm going to look at the first law of thermodynamics. And of course, that's going to be delta U equals Q minus W. So delta U is Q minus W is the first law of thermodynamics. And of course, I know that the process is cyclical. Cyclical process means delta U equals 0. That's, again, I've done this a few moments ago. Cyclical process. All engines, heat engines, at least the ones we're going to talk about here, are all cyclical processes. That means that delta U goes to 0 in the first law. That means then that the net work equals the net heat. Again, net work equals net heat transfer. Or in this case, we know that the net work, the work that's going to be done by the engine, will be the difference of Q sub H and Q sub C. Q sub H is the heat coming from the fuel source, from the high temperature reservoir, and minus Q sub C is the heat that gets released to the environment. Okay, so now what do we know? Well, we know that 10.0 kilojoules of work is done. So W is positive 10.0 kilojoules. Again, why is that? Well, again, remember our sign convention. Work is done by the heat engine. So the engine does work. Work is done on the engine, then that means that, done, underline wrong, by. Work is done on the engine, means that would be negative. Right? So W is 10, so the work is being done. Again, the engine, that's the whole purpose of the engine is to do work, right? We know that, if we read carefully, it says that heat transfer occurs to the environment. What does that mean? That means that heat is being released to the environment. Well, that's another way of saying Q sub C. Q sub C, so that's heat transfer to the environment. That's 8.50 kilojoules. All right, and so we're asking for, again, part A was, what's the heat transfer into the engine? Well, that's Q sub H, right? So I can solve for Q sub H, solve the work, first law, and I would get that Q sub H is W plus Q sub C, or 10.0 kilojoules plus 8.50 kilojoules is 18.5 kilojoules. So the heat transfer into the engine, which we always call Q sub H, will be 18.5 kilojoules. Simple as that. 18.5 kilojoules the heat transfer to the engine. Part B asks for the engine's efficiency. All right, so we have, this is part A. So now we have Q sub H, we know Q sub C, we know W. We want the efficiency. All right, so again, we can do it a couple, we don't have temperatures, right? So again, we wouldn't use temperatures anyway because it's not an ideal heat engine. So what's the efficiency again? The efficiency, part B, efficiency will be 1 minus Q sub C over Q sub H. Simple as that. The efficiency is 1 minus 8.5 kilojoules. That's the energy, that's the heat goes into the environment, divided by 18.5 kilojoules. And I find out that the efficiency comes out to be 0.54. That's actually very, very good for an engine. Most car engines are about 30%. This engine is 0.54. That means that 54% of what you pay at the gas pump to do work, 54% of that will actually go to doing work. You usually get about 30% or maybe 35% out of your car, and then the other 65 to 70% you're just throwing away to the environment. Because that's part B. So car engines are generally very inefficient. Okay, OpenStax 15.23. All right, that says A, what's the efficiency of a cyclical heat engine? In which 75.0 kilojoules of heat transfer occurs to the environment. For every 95.0 kilojoules of heat transfer into the engine. All right, that's A. B, how much work does it produce? For 100 kilojoules of heat transfer into the engine. So these problems, you just have to be very careful on how you read them. All right. All the words are very important. They all mean something. A lot of writing. Okay, so OpenStax 15.23. So A, what is the efficiency of a cyclical heat engine? Which 75 kilojoules of heat transfer occurs to the environment for every 95.0 kilojoules of heat transfer into the engine. So every single time 95 kilojoules of heat transfer, Q sub H goes into the engine, 75, Q sub C equals 75 kilojoules gets spit out into the environment, okay? How efficient is that engine? And then B, how much work does it produce for 100 kilojoules of heat transfer into the engine, all right? So let's give myself some real estate here. Let's erase this. Okay, so for part A, you're reading this thing very carefully. We know that we're gonna for every single 95 kilojoules of heat transfer that goes into the engine, we know that Q sub C, which is 75.0 kilojoules of heat transfer, gets released into the environment as exhaust. How efficient is that engine? Well, the efficiency, we know for any engine is 1 minus Q sub C over Q sub H. The efficiency be 1 minus 75.0 kilojoules divided by 95.0 kilojoules. Again, I don't care about converting to joules because I'm just going to be having a fraction like this, and it's a unitless fraction. Whether I put kilojoules or joules in there, I'm going to get the same number out. All right. So the efficiency I will find is 0.211. So a pretty poorly efficient engine. Okay, now I know how efficient it is. Part B says, well, part B says if you're gonna put in 100 kilojoules of heat, how much work are you gonna get out? So let's try to imagine that we're gonna put in 100 kilojoules of heat. And the question is, well, if I do that for this particular engine, how much work do I expect to get out of it? Well, we go back to one of the definitions of efficiency, right? Efficiency, remember, is what you get out of something. That's the work divided by what did you put into it. In this particular case, I'm burning fuel to get heat. All right, so I want to figure out the work, so I just cross multiply, and the work is nothing more than the efficiency times Q sub H. Or the work will be 0.211 times 100 kilojoules. The work will simply be 21.1 kilojoules. So again, every single time that engine does a cycle, or it puts in 100 kilojoules, for instance, 21.1 kilojoules will actually go to doing real work. And the rest of the 79-ish kilojoules will go out to into the environment as waste heat. Okay. The OpenStax 15.28. Okay, so this says is a certain gasoline engine has an efficiency of 30%, which is typical. %30.0%. What would the hot reservoir temperature be? What would the hot temperature reservoir the hot reservoir temperature? What would the hot reservoir temperature be? B for a Carnot engine. Having that efficiency if it operates with a cold reservoir temperature of 200 degrees Celsius. Operates with cold reservoir temperature Okay. Okay, so yeah, it looks good. Okay. A certain gasoline engine has an efficiency of 30.0%, right? Typical. What would the hot reservoir temperature be for a Carnot engine having that efficiency if it operates with a cold reservoir temperature of 200 degrees? Something in my notes real quick. Okay. So what do I know? Well, I know that. So again, we know that we know the cold temperature or the cold reservoir. We know the efficiency. We're gonna make the assumption it's a Carnot engine. Okay. So we're given the efficiency, and it's 30% or 0.300. All right. And we don't know the high temperature reservoir, but we're told the cold temperature reservoir is going to be 200 degrees Celsius. But again, we want to do Kelvin. So let's put it in Kelvin right now. So 200 plus 273 is 473 Kelvin. Okay. So what we want to do is we want to try to figure out what the high temperature reservoir is. So what we can do is we're told it's Carnot. So again, we're told we cannot use the Carnot formula unless we're actually told, we actually see words like ideal or perfect, or we actually get told that it is a Carnot engine. Otherwise, you're not allowed to use the Carnot formulas. You cannot do that. So we're told the engine's Carnot. Okay, so that's a cue that we can use those formulas. That means that the efficiencies of Carnot, efficiency would be equal to 1 minus T sub C over T sub H. The only way you can use those formulas. Now, we know the efficiency, we know T sub C, the thing we don't know is T sub H. So what do? Well, we're going to have to solve for T sub H. So again, 1 over, so T sub C over T sub H will be efficiency. So it'll be 1 minus the efficiency. And we can flip the equations upside down both cases. So T sub H over T sub C okay, flipping it is 1 over 1 minus efficiency. And I can cross multiply T sub C, T sub H is T sub C divided by 1 minus efficiency. And I'm ready to go. T sub H. Again, all these temperatures, when I do the Carnot calculation, must be in Kelvin. Cannot do them in Celsius. Makes no sense to do so. So again, I have 473 Kelvin divided by 1 minus 0.300. I find out the high temperature high temperature, or temperature of the hot reservoir will be 676 Kelvin. But you always want to return the problem the way it was given to you. So the problem is given to us in degrees Celsius. So I'd want to return it as T sub H will be the 676 minus 273, or T sub H is 403 degrees Celsius. There you go. So again, I was given sometimes you're given a clue. Here I was told directly that the engine's Carnot. Sometimes you have to look for words like perfect or ideal. All right. I was given the efficiency, and I was given the temperature of the cold reservoir. Okay. All right. I'm going to look at OpenStax 15.30. 15.30 requires a little more deeper thinking. Okay, I think that goes. Yeah, okay. OpenStax 15.30. Okay, so this says, what is the hot temperature of a Carnot engine? Okay, so I know it's Carnot, I'm specifically called out. So A, what is a hot temperature reservoir? Is a hot reservoir temperature? Of a Carnot engine. It has an efficiency of 42.0%. And a cold reservoir temperature of 27.0 degrees. A typical summer day or so, or like a reasonable day outside, a little bit over room temperature outside. Okay. And then B, what must the hot reservoir temperature be? For a real heat engine? That achieves 0.700% of the maximum efficiency. Efficiency. But still has an efficiency of 42%. A lot of words in this one. and a cold reservoir at 27 degrees Celsius. And then C, does your answer imply practical limits? Practical limits. C, to the efficiency of to the efficiency of car gasoline. Some of these problems are pretty long. Okay. OpenStax 15.30. A. What is the hot reservoir temperature of a Carnot engine that has an efficiency of 42.0% and a cold reservoir of 27.0 degrees Celsius? Okay, that's a purely Carnot problem. B. What must the hot reservoir temperature be for a real heat engine that achieves 0.700 of the maximum efficiency, but still has an efficiency of 42% and a cold reservoir of 27 degrees Celsius, right? And then does your answer imply practical limits to the efficiency of car gasoline engines? All right, so keep that in mind. And I need real estate, of course, so I have to raise all this. Okay, so part A. Part A is a pure Carnot problem. So again, we're going to read it here. So what's a hot reservoir temperature? Okay, I want T sub H. If a Carnot engine has an efficiency of 42% and a cold reservoir temperature of 27. Okay, so this is a typical basic Carnot problem. What I'm looking for is T sub H, the temperature of the hot reservoir, and I'm being told that the efficiency can be a Carnot efficiency. In this case, it's 42%. That's 0.420, and I'm told that the cold reservoir temperature, well, I'm told it's 27 degrees Celsius, but again, I want to put this in Kelvin, so I need to add 273, and so the cold reservoir will be at 300 Kelvin. I mean, that's typical, and that's your car's outside on a typical day, 27 degrees Celsius is not that bad, like a little bit above what we would call room temperature. All right. So again, I'm told that the engine is Carnot in part A. So if I'm told it's Carnot, then I can use the efficiency, the Carnot efficiency, 1 minus T sub C over T sub H. Okay. And so simply it's going to be 1 minus T sub C is 300 Kelvin. Oh, actually, I don't know but I don't know C sub H. All right, so I'm going to do similar math as last time. Again, T sub C over T sub H will be 1 minus the efficiency. And do a little algebra. I flip the equation. T sub H over T sub C is 1 over 1 minus efficiency. Multiply, cross multiply essentially. T sub H is T sub C over 1 minus efficiency. T sub H will be the 300 Kelvin divided by 1 minus 0.42. T sub H will be 517 Kelvin. Or again, you always return the problem as you got it. So I was given a cold temperature. I was given a temperature reservoirs in degrees Celsius. So let's make the high temperature reservoir be in degrees Celsius. So T sub hot will be 517 minus 273. And that's going to be 244 degrees Celsius. So very, very hot. All right, so that's for a Carnot engine. Now let's consider a real engine that gets 70% of Carnot. And that requires a reading a couple of times, but and this is my T sub hot. This is a purely Carnot problem, assuming a perfect engine. That would be the high temperature reservoir would have to be at 244 degrees Celsius. If the low temperature reservoir, the outside is 27. So if I'm driving around 27 degrees Celsius ambient temperature, to get 42%, I'd have to have the engine work operating at 244 degrees Celsius, which is very, very hot. Now, part B. All right. So part B says, I reread it, says, what must the hot reservoir temperature be for a real heat engine that achieves 0.700 of the maximum efficiency, but still has an efficiency of 42%? Okay, so what we're saying is, I don't know what this efficiency is, but we're saying it's gonna achieve 0.700 of the maximum efficiency, which I would call X, and still have an efficiency of 42%. Okay, that's the efficiency that I'm after. And so what this is telling me is that this is a real engine. And the real engine will achieve 0.700 of the maximum efficiency, but this real engine is going to still have a 42% efficiency. And so my efficiency, if I solve for X, my efficiency X will be 0.600. Okay, so then that's the efficiency of the corresponding Carnot engine. So again, we're talking about what is the corresponding Carnot engine, and that the car would be 70% of that and still be 42%. Okay, so the question is, okay, well, now I have converted into a Carnot problem, or the efficiency of so now the question is, well, my T sub C is still going to be 27 plus 273 or 300 Kelvin. The question is, what must the high temperature reservoir be? And again, I would say, well, this efficiency, the corresponding Carnot engine would operate between what? It would be 1 minus this T cold over T hot, corresponding Carnot engine. I've gone through the math a few times now. We know that T sub cold over T sub hot is going to be 1 minus X. This is the corresponding Carnot efficiency. I flip everything upside down. I get T hot divided by T cold is 1 over 1 minus X. Cross multiply, T hot is T cold divided by 1 minus X. And so I have 300 kelvins divided by 1 minus 0.600. The high temperature reservoir would have to be, in this particular case, 750 Kelvin. Okay, that corresponds to a high temperature of 750 minus 273, or 467 degrees Celsius. Okay, so sometimes you have to wonder, be careful what you wish for. One of the things you should always look at when you're driving your car is to see where that temperature gauge is. You should always be glancing at that temperature gauge ever so often. Your temperature gauge should be right smack between hot and cold. If it is too hot, even a little bit too hot, you better take your car and have it serviced. Because the last thing you want to do is you want to melt your engine. You do not want to run with the temperature of the engine being too hot. And so there's no way that you're going to be able to achieve a 467 degrees Celsius and operating temperature in your engine. There's no way that can possibly happen. So essentially, if you are to consider a Carnot engine, you'd be forced to have to operate at a high temperature reservoir that is way, way, way too high, beyond what is reasonable. And so there's no way that can actually happen. So again, so one of those things that be careful what you wish for. If you want a Carnot engine, if you want that kind of Carnot efficiency, you'd have to operate at a high temperature reservoir, or your high temperature reservoir would have to be at an exceedingly high temperature. And we don't know how to make an engine that can work, that can operate at that hot. Basically, your car already operates hot. If you ever kind of wonder, you drive your car for a while, and then you get, you park in the garage, and you put your hand on top of the hood, and it's really hot, right? Or let's say you have a problem in your car, and let's say it's overheating. Well, the engine is very, very, very hot. And you wonder, why is the engine operate so hot? Well, because it is a heat engine. It must operate at a high temperature in order to be able to give you work. Again, the work, if you look at the Otto cycle, the work is the area of contained or bounded in that curve, that PV diagram. Well, you want to get more work, you either take the high temperature higher or the lower temperature lower. Because one way or the other, you want to maximize that area of that bounded region. That gives you the amount of work and the efficiency of your engine. All right. Okay, so now the heat engine is not the only application to thermodynamics or the first law. We also have other very important appliances, very important applications. We have what's called the heat pump and refrigerators. So those are other very important applications of the first law. So heat pumps, air conditioners, and refrigerators. Changing topics. All right, and so the idea here is that that heat transfer. So again, with the heat pump, we'll talk about the heat pump first, then we'll talk about refrigerators and air conditioners. All right. So the idea of a heat pump is that essentially heat gets transferred. So we'll talk about the heat pump first. So again, maybe you may not have never heard of a heat pump. But the idea about a heat pump is it's kind of a heat engine in reverse. Okay, so a heat pump, the idea is, well, you have a house or a room or something. And let's say it's a colder day outside, you want to heat the room. So what you have is you have refrigerated coils on the outside. So you have some sort of a coil on the outside, and Now the outside is at a temperature T sub C, and so what happens is the you have the coils. They're gonna well, let's put it this way. We'll kind of talk about the process of the heat pump. All right. So the idea of a heat pump is that you want to take you want to essentially dump heat into, let's say, your house. Okay, so you have a temperature at T sub H, and the idea is you want to, here's your engine, your heat pump, and you have an outside or environment temperature T sub C. Okay, so it looks kind of like the heat engine diagram, but the idea is you're going to have heat that's going to come in from the environment. So you have the heat that's going to come into the environment, and it's being driven into the engine. So again, it's going from the cold to the hot. Okay, this is Q sub C. And of course, heat doesn't normally want to go from cold to hot, so that requires input work to make that happen. You have to do work. You have to pay for work to make that happen. And what happens is you end up dumping heat into the space where you want it to warm your room. That's Q sub H. Okay, so you're taking heat from the outside, you're doing work, and you're going to get Q sub H into your heated space. All right. So again, the idea is this is the inside of your house. You want the Q sub H. This is your environment. And you have to run some sort of a compressor in order to be able to actually get the heat from the environment into the house. The wasted heat is going to be what you want you want the heat into the house. All right, that's what you're after. Now, turns out that a heat pump can actually be run backwards. You can actually use it as an air conditioner. All right, and so when I moved to California for the first time, I was in my apartment, and one of the first things I did is I went around my apartment, kind of making sure I knew where everything was. And so I saw that what I saw on the side wall of my living room was the air conditioner. At least I thought it was the air conditioner. Or I guess it was, what did I think? I guess I thought it was I thought it was the air conditioner. And I thought, okay, well, where's the heater? So looking around, I'm like, where is the heater? I couldn't find it. So I slowly went back to what I thought was just the air conditioner. And I looked at him like, well, what do you know? That's a heat pump. So I can actually use this as an air conditioner and as a heater. So essentially, depending on which way I want to run it, I can use it as an air conditioner or a heater. Now, a heat pump works best in environments that are fairly where it doesn't get too cold. San Diego, California would be an example of a place that really never gets that cold. And so if you have an environment like that, a heat pump works well. So how does the heat pump work? So first of all, what's nice about the heat pump is, you're going to get heat. Well, let's see here. Let's see how a heat pump works. All right, so the idea is, for the heat pump, we know that Q sub H, the heat that's going to go into the room that you're trying to warm, is going to be Q sub C plus W. Okay? Now, W is the work. W is the work required to run the heat pump. All right? You get Q sub C for free. Now, again, you're gonna use the thing about it is, I mean, the idea is, well, if I'm going to use the heat pump, the question is, well, that's great, except how expensive is W? If W, I mean, essentially, if you just burn fuel, you pay for everything. Pay for all of Q sub H. You decide you're going to go burn fuel like natural gas, you're going to pay for all of Q sub H. Well, here you get Q sub C for free. But the problem is, how expensive is W? If you're doing work, if W is performed through electricity or electrical heating, we'll say through electricity, it is likely very expensive financially. And you are likely better off just burning fuel. All right, so again, if you're getting a QCC for free, well, the question is, how expensive is W? If W is very expensive, then there's no point. You might as well just you might as well pay for it all by just burning fuel. So the question is, how does the heat pump work? Is the question. All right, so again, let's talk about how it does it work. See this heat pump? Let's kind of talk about the method or the machinery, essentially. All right. So in the outdoor coils, you have coils that are outdoors. In the outdoor coils, okay, we refer to that as the evaporator. So you look outside, you have the evaporator. Heat transfer Q sub C. Yeah, we're talking about the operation of the heat pump. Heat transfer Q sub C. Occurs to the working fluid from the cooler, outdoor air. So again, the coils are outdoors. So heat transfer occurs to the working fluid from the outdoor air, and it turns into a gas. So the fluid was a liquid. Again, we're talking about refrigerant, and so essentially you're looking at it. The working fluid is a non-CFC refrigerant. So Q sub C causes the liquid to evaporate to a gas. Right? So in the outdoor coils, you had a liquid. It is a refrigerant, a non-CFC. CFC again stands for chlorofluorocarbon. We used to use Freon. We don't use Freon anymore because it burns holes in the ozone layer. So we have a liquid, and that liquid evaporates to a gas because of the input of Q sub C from the environment. Okay. Now what happens? Well, now the fluid goes into the house. All right. So in this case, we have electrically driven compressor. So this is where you start paying money. The electrically driven compressor so the compressor work input W, it does the work. Okay. It raises the temperature and pressure of the gas. And forces into the condenser coils that are inside the heated space. Heated space. I won't be able to fit the whole process on here. So again, you start off with you have outdoor coils, the evaporator. Heat transfer, Q sub C, again, comes from the environment, occurs to the working fluid. The working fluid is a non-CFC refrigerant. So heat transfer Q C occurs to the working fluid from the cooler outdoor air, and it turns it into a gas. It essentially evaporates the liquid refrigerant, turns into a gas while it's still outside. That working fluid then, so that QCC then causes liquid to evaporate into a gas. And then you have a compressor that now you're paying electricity to drive the compressor. That gives you W. That gives you the W. So Q sub C plus W. That raises the temperature and the pressure of the gas and forces it into condenser coils that are inside the heated space. All right. Now, okay, so keep that in mind. The next step okay, the next step is that because the temperature of the gas is higher than the temperature inside the room, and it's been driven up way high in temperature because of the pressure and temperature have increased. It gets put into the condenser coils. Now its temperature is higher than the temperature in the room. The temperature of the gas is higher than the temperature inside the room. Okay, and what happens then is that heat transfer to the room occurs because of this. And the gas condenses to a liquid. All right. And then finally, after that happens, the heat's been dumped into the room. That's your Q sub H. Again, so this is Q sub H. So Q sub H is dumped into the room, essentially, with this process. Okay. Finally, now that it's a liquid, the liquid from the flows back through the pressure reducing valve. To the outdoor evaporator coils, being cooled through expansion. And then the process begins again. Process repeats. So to summarize, you have liquid refrigerant, non-CFC liquid refrigerant that is in the evaporator coils outside the house. Q sub C, heat from the environment enters the refrigerant, causes it to evaporate. That's why it's called the evaporator. Evaporate to the gas. The pressure and temperature of the gas is increased, and it gets forced into the condenser. The condenser coils are inside the house, and because the temperature of the gas is higher than the temperature of the room you're trying to heat transfer Q sub H goes from the condenser coils into the room. Because of this heat transfer, the gas condenses to a liquid again. The liquid then flows out through with the pressure reducing valve and reduces the pressure and temperature, and it goes back outside again to start the whole process anew. And it continues going on and on and on. Now the thing about it is the compressor is where the work is done. The compressor is which causes the gas to get moved into, go to higher pressure and temperature. That compressor is what you're paying for. So you're paying for the electrically driven compressor. That's your input W. All right. So again, the compressor drives the gas and forces into the condenser coils. That compressor is what causes the unnatural behavior of heat to go from Q sub C to Q sub H. All right. So again, you're creating a heater. You can turn a whole process around and make it into an air conditioner. So the question is, what is the efficiency? I mean, what are you getting out of this process? Well, for the heat pump, you don't call it an efficiency. You call it what's called a coefficient of performance for the heat pump. So what you talk about is you talk about the goodness factor. You talk about what's called the coefficient of performance for the heat pump. So we call this a COP sub HP, coefficient of performance for HP heat pump. So, okay, well, it's some sort of an efficiency factor. Well, what do we want to define for efficiency? Always, well, coefficient of performance for the heat pump, any efficiency, again, is what you get out of it divided by what you put into it. What are you getting out of the heat pump when you're using it as a heater? You're getting that Q sub H that heats your room. That's what you're getting out of it this time. And now, what are you paying for? Now you're paying the electric bill to drive the compressor. Okay, so again, what are you getting? So again, it's always, what are you getting out? What are you putting in? Kind of in slang. Okay, so again, for this particular efficiency, the coefficient of performance of a heat pump, what are you getting out of this? Well, I'm trying to heat my room. 8 Q sub H. I'm trying to heat my house. What am I putting in? Well, I'm paying to operate the compressor. Now, for the heat engine, this is exactly backwards, right? Remember, for the heat engine, what did I have? Well, I had an efficiency, right? An efficiency for the heat engine. So for the heat engine, what was I getting out? What was I getting out of it? Well, now for the heat engine to drive the car, for instance, what am I getting out? Well, I'm getting out work. I'm driving the car, operating the drivetrain. I'm operating the lights, the radio. So I'm getting work out of the car. And what am I putting in? Well, I'm burning gas. I'm combusting gas. What I'm putting in is Q sub H. So a heat pump is exactly the reverse of a heat engine. All right. So what I can actually look at and say, well, a heat pump, you can look at it, coefficient of performance for the heat pump, you can say it's 1 divided by the efficiency. If I go off and calculate an efficiency, 1 divided by the efficiency is the coefficient of performance for the heat pump. So why, when I said that a heat pump works best in temperate climates, why is that? Well, again, a heat pump, you always know that the efficiency is never going to be 1. It's always going to be less than 1, right? So looking at this, the efficiency is always going to be less than 1. We said it about engines. So efficiency will always be less than 1, always, no doubt about that. That means that the coefficient of performance, that implies that the coefficient of performance for the heat pump will always be greater than 1. All right, and so where am I going to get the best efficiency? Well, let's kind of look at it. Let's kind of look at a Carnot problem. Let's look at the Carnot issue here. So look at Carnot. You know, again, that's going to kind of tell me, you know, my best situation. Well, remember the Carnot. Efficiencies of Carnot was 1 minus T cold over T hot. If T cold is close to T hot, then I'm going to get a number here that's clearly close to 1. I'm going to have very poor efficiency, right? So if T cold is close to T hot, then efficiency Carnot will be a small number. But then coefficient of performance heat pump will be a large number. Why is that? Because the coefficient of performance of the heat pump is 1 divided by the efficiency. So a really inefficient engine makes for a great heat pump. So if it's a really poor engine, it's gonna be a great heater. That's what that basically tells you. So in the case of, you know, some nice temperate climate like San Diego, for instance, you know, the hot temperature and a low temperature don't ever really differ by that much. So that means that the efficiency of that heat pump will be a fairly poor number, which means that it'll be a good heater for me. And so again, it works best if you're efficient in temperate climates. And what about air conditioner or refrigerator? Okay, so again, we're talking about heat. We're talking about basically running an engine backwards. What's the purpose of a refrigerator or air conditioner? Well, what they do is they actually move. So heat transfer occurs. Heat transfer Q sub C occurs from a cold place, you know, where food is stored in a refrigerator, or where people are in a room, to a hotter environment. You're moving heat the other direction. All right. And so what you're trying to do now is you're trying to get the heat out of the place where you want to keep cool. And you're pushing it into a location that's hotter. Again, that's going to require work being done because that's not normal. Heat normally, you know, that usually doesn't work that way. You have to do work in order to make something go from cold to hot. All right. So again, you define what is called a coefficient of performance for a refrigerator. And so we say, well, coefficient of performance for a refrigerator, COP ref, again, is what are you getting out divided by what are you putting in. What are you getting out of a refrigerator? Well, you're moving Q sub C. You're taking cool air, or you're trying to cool an environment you want to keep cool. So you're moving cool air out of a compartment that either contains food in the case of a refrigerator, or contains people in the case of a room. So what you're trying to do is you're trying to move Q sub C this time. And what are you paying for? What are you putting into it? Well, again, you're running the compressor, you're running W. That's your coefficient of performance for the refrigerator. You're moving Q sub C and you're paying for W. Well, the question is, well, again, we know that the coefficient of performance for the heat pump will always be greater than that of so we know that, so coefficient of performance of the heat pump in comparison, again, in that case, it was Q sub H over W, right? Well, given that, we always know, so we know that the coefficient of performance of the heat pump will always be greater than the coefficient of performance for the refrigerator. Why? Because Q sub H will be greater than Q sub C. So the question is, how do we relate the two? Well, we can relate the two quite simply, but we can say, well, coefficient of performance of a refrigerator is what? Well, it's going to be Q sub C over W. But what is Q sub C? Well, remember, work for any cyclical process is always going to be Q sub H minus Q sub C, right? That's for any cyclical process. Well, that means that I can actually write that instead of Q sub C, I can solve that equation and say, well, instead I can write this. I can write Q sub H minus W instead of Q sub C divided by W. And I can write this as Q sub H over W minus W over W, which is just 1, or Q sub H over W. What is that? Coefficient of performance for the heat pump. So the coefficient of performance for the refrigerator operating between a couple of temperatures is going to be the corresponding coefficient of performance for a corresponding heat pump minus 1. So not only is coefficient of performance of the refrigerator less than that of the heat pump, but I can actually calculate how much less. Pretty simple relationship. So generally speaking, we can get a coefficient of performance of refrigerators to be pretty high. So, coefficient of performance for a refrigerator, we can typically get up from around 2 to 6. They're usually they're usually quite efficient. So COP values for your refrigerator usually run from 2 to 6. Usually they're pretty good. So usually run from 2 to about 6 on the. Again, this is going to be how good a refrigerator. Again, 6 would obviously be the most efficient refrigerator, and 2 would be the least. But worst case scenario, your worst refrigerator is still going to have a coefficient performance of around 2. I mean, that's usually pretty good. We have all other kind of ratings. We have an energy efficiency rating that's usually kind of complicated. But in the United States, usually a lot of English-speaking countries, in Australia, Canada, and the US, we use an Energy Star system. You go to a store and you see Energy Star, and that's usually a rating out of 5 stars. Right. So again, you have different ways of doing ratings. The physicists would use a coefficient of performance, but again, people who go into a store and want to buy a refrigerator are going to use this Energy Star system. It's a simpler system, easier to understand. All right. Let's work a few refrigerator problems, air conditioning problems. Usually we talk about refrigerators. So I'm going to look at OpenStax 15.37. Okay, what is the coefficient of performance of an ideal heat pump? that has heat transfer from a cold temperature of negative 25 degrees Celsius to a hot temperature of 40 degrees Celsius. Okay, so we're talking about an ideal heat pump. Ideal means Carnot. All right. You see words like ideal or perfect. You ought to be thinking about Carnot. Okay, first and foremost. All right. And so if you want to talk about the energy efficiency, of a Carnot, let's talk about efficiency first. So efficiency Carnot. Well, it's going to be 1 minus T cold over T hot. Now they have to be in Kelvin temperature units, right? So that's going to equal 1 minus, okay, T cold, right? This is T cold, well, we're told it's negative 25 Celsius. Plus 273. Got to get it into Kelvin. I'll just kind of do it on the fly. On the bottom, temperature T hot, well, we're told it's 40 Celsius plus 273. So the Carnot efficiency is going to be, that's the first thing I want to do is calculate Carnot efficiency. You worked it out, it's going to be 0.208. Now, we're not talking about a heat engine, though. We're talking about what? A heat pump. All right, so remember, the coefficient of performance of a heat pump is always 1 divided by the efficiency. No matter what the efficiency is. In this case, it's Carnot efficiency, but it doesn't matter. It's an efficiency. So all I would do is say, well, the coefficient of performance of the heat pump is just 1 divided by 0.208. And I would find out that the coefficient of performance of the heat pump would be 4.81. So pretty bad engine, but a great heat pump. So again, inefficient engine, 0.208 is pretty bad, but a heat pump, 4.81. So again, this is the best you can do. I mean, if you're operating between these two temperatures, 0.208 is as good as you're going to possibly get. So all that says is you have a bad design, because if that's as good as you're going to get, this is from the laws of physics. Well, that's just one of those things. But again, it's not a good value for the efficiency, but 1 divided by it, it's a good value. 4.81 is a pretty good value for a heat pump coefficient of performance. And if you get values around 2 to 6, you're doing great. I'm gonna do one more refrigerator and air conditioner problem. So that's a heat pump problem. A heat pump problem. So let's do again. Remember, a heat pump is an engine running backwards. The engine you're getting Q sub H, and you're paying for W. Here for the heat pump, you're paying. Sorry, for the engine you're getting W, and you're paying for Q sub H. For the heat pump, you're getting Q sub H, and you're paying for W. So again, that's some places, some cases, that kind of heat's called waste heat. In other cases, that's the heat that you want. So again, it's an engine run backwards. Okay, let's look at OpenStax 15.39. Okay, what is the best coefficient of performance? Of an possible for a hypothetical refrigerator. Boom, boom, boom. That could make liquid nitrogen at negative 200 degrees Celsius to and has heat transfer to the environment at 35 degrees Celsius. Okay, so this says, what is the best coefficient of performance possible for a hypothetical refrigerator that could make liquid nitrogen at negative 200 degrees Celsius and has heat transfer to the environment at 35 degrees Celsius? So when you see the word best, that's another example of a situation that you're going to use Carnot. Best, perfect, ideal, or you could just see the word Carnot. So when I'm looking at best coefficient of performance possible, that means I'm going to be considering a corresponding Carnot engine. Now the temperatures we're dealing with, the cold temperature is negative 200 degrees Celsius, and the hot temperature is 35 degrees Celsius. Okay, I got a little fuzzy here. All right, so let's work this out. So we're talking about a refrigerator, hypothetical refrigerator. All right, so what we're going to do is we're going to calculate the efficiency and then go from the heat pump and then go to refrigerator using our relationships, right? So again, we're talking about Carnot. So if you see the word best, that implies Carnot. All right, so efficiency, so again, efficiency Carnot. It'll be 1 minus T cold over T hot. Now, again, I need to put these temperatures in Kelvin. So 1 minus T cold will be, again, negative 200 degrees Celsius plus 273. I got to get it to Kelvin. Divided by T hot, I'm just doing it on the fly, 35.0 degrees Celsius, plus 273. I'm converting on the fly to Kelvin. So if I do that, efficiency sub Carnot is going to be 0.763. So it should kind of alarm you a little bit because that's a very efficient engine, which means it's probably going to be a really bad heat pump and refrigerator. All right, you can see this. That's very high efficiency. So what do we do now? Well, we calculate the coefficient of performance of the corresponding heat pump. That'll be, so the corresponding heat pump, that'll be 1 over the efficiency Carnot, or 1 divided by 0.763. So the coefficient of performance for the corresponding heat pump will be just 1.31. But we're not talking about a heat pump. We're talking about a refrigerator. So remember, the coefficient of performance for a refrigerator is equal to the coefficient of performance of the corresponding heat pump minus 1. So the coefficient of performance of the corresponding refrigerator will be 1.31 minus 1. The coefficient of performance of this ideal refrigerator is only going to be 0.31. So it's a terrible refrigerator. Excellent engine, but a terrible refrigerator. Okay, so 0.31 is a, so again, we're, so one clue was when I calculated the efficiency, it was a really good number. Well, I'm like, oh, this would be a great engine, which means it'd be a really bad heat pump and an even worse refrigerator. All right, so again, that's an ideal. It's as good as you're going to get for these operating temperatures. Okay, so we talked about all the applications of the first law of thermodynamics. We talked about making engines, refrigerators, air conditioners, and heat pumps. So now we still haven't, and we have three versions of the second law of thermodynamics. None of those versions are any good. They're all true, but none of them are good. So we're going to go, we want to now go and derive the fourth and final version of the second law of thermodynamics. And how do we go about doing that is we go back to Carnot's paper. We still don't have a working form of the second law of thermodynamics, all right? So we still need a working form, something where you can actually do a calculation for the second law of thermodynamics. So remember Sadi Carnot, the French engineer, young French engineer. We're going to go back to his paper. Now, Carnot, interestingly enough, is responsible for the third version of second law of thermodynamics, but little did he know, he actually, in the same paper, derived the fourth version and actually a new, very special variable of the universe in his paper. So we go back to his paper. So Carnot's paper. Stated that the following relation holds for a Carnot, or an ideal, if you will, heat engine. And that relationship is as following. So again, this is a review here we talked about earlier. Carnot said, well, if you want the fraction, the ratio of Q sub C over Q sub H, that's equal to the ratio of the reservoir temperatures, the absolute temperatures of the reservoirs. That is only true for an ideal heat engine. Well, let's do a little bit of algebra. Real simple algebra here. We rearrange this relationship and we can get the following. We can get Q sub C over T sub C is equal to Q sub H over T sub H. For Q sub C over T sub C equals Q sub H over T sub H. And we can do one more thing. We can say, well, I can also write that Q sub H over T sub H minus Q sub C over T sub C equals 0. So I have a transient or a energy of transit called heat. I have this unique combination where I divide it by a corresponding temperature of a reservoir, And at any given time, if I do this relationship, I do this subtraction, I always get 0. Well, that spells that that's probably a very important relationship. That I am actually, this Cutnell has tripped over a very unique combination of thermodynamic variables that happen to give you a nice, clean answer. You essentially, this combination of variables, Q over T, is special. In an ideal engine, this relationship, no matter what ideal engine we're talking about, no matter what the Q sub H, Q sub C, T sub H, and T sub C, I always will have this subtraction equal to 0. Q over T, whether Cutnell knew it or not, he defined a very special variable in thermodynamics, and it happens to be a state variable. It is called the entropy. So what Q over T is, whether Cutnell Cutnell realized this or not, he actually essentially defined a new state variable in thermodynamics. And in fact, the state variable, the state function, that corresponds to the second law of thermodynamics. So we can define what we call delta S is Q over T sub-reversible. So again, Cutnell's situation is that he had he developed a very idealized engine that was based upon reversible processes. So of course, reversible processes are idealized in them themselves. This is called the change in entropy. Entropy is the state variable, or a state function. I'll say state variable. In that, like internal energy, its change delta S only depends on the endpoints of the process. It is path independent. And unlike the heat is entirely path dependent. But the entropy, just like the internal energy, is path independent. And this is a very special variable in physics. Very, very special relationship in physics. Now the units on entropy, well, the units on the heat is an energy, joules. The units on temperature is Kelvin. So the units on entropy are joules per Kelvin. And when you have joules per Kelvin, there's no special physicist that you honor. You just say joules per Kelvin. That is units of entropy. Now, the fact that delta S equals 0, that's only for a perfect process. All right, so delta S equals 0 only for reversible processes or a reversible ideal engine. For any irreversible real engine delta S is greater than 0. Now the question you might ask is, well, okay, if we have defined entropy for a reversible engine, how in the world are we going to use it for a real engine? And I tell you, well, it doesn't matter, and that it is a state variable. So even though I can use delta, I can use the entropy for a real engine. So even though entropy is derived, or maybe I should say defined, for a reversible engine, I can use entropy for a real irreversible engine because entropy is a state variable. Again, it means it's path independent. I don't care about the path, so I can calculate the entropy for a corresponding reversible path that I determine or imagine. I can just imagine. Doesn't matter because it's path independent. All I care about is calculating it between two endpoints. So it doesn't really matter if it's real, I mean, if it's a real system or not. It's path independent. So again, all I care about is the endpoints. And so now we have a, let's see here, final statement of the second law. So we can finally state, so essentially, if you look at the second law of thermodynamics, one of the things we can talk about the entropy is that it is a measure of disorder. So one of the things that we talked about earlier is why doesn't, why, for instance, can't I run a movie backwards? Well, because I can't go from order, so greater disorder to less, from less order to greater, or from greater order to less, less order to greater order. I have to always go from toward disorder. All right, and so the idea is, if I look at the a case of, let's say, I ask the question, why does heat transfer only occur from, well, actually, let's just give you the, let me give you the final form of the second law of thermodynamics, and then we'll answer some fundamental questions. All right. So the final form of the second law of thermodynamics. The fourth version is the following. It says the total entropy of a system either increases or remains constant in any process, it never decreases. So mathematically, delta S total greater than or equal to 0. That is the mathematical statement of the second law of thermodynamics. The entropy is the state variable that's associated with the second law of thermodynamics. Just like the internal energy is a state variable associated with the first law of thermodynamics, and of course the temperature is associated with the 0th law. Every law of thermodynamics has to have, so again, as we developed this second law of thermodynamics, we kept searching and searching for what is that special state variable, and finally we get the entropy. So now the question is, well, why can't I, for instance, have heat transfer going from cold to hot, for instance? You know, so let's kind of answer some of our questions here. So let's let's see here. Yeah. So let's try to answer some questions about why, that I posed earlier in the beginning of this lecture. Now we're kind of poised to be able to answer them now. So why can't heat transfer occur from cold to hot? Okay, and I think I have an example that goes over this. So, for instance, let's say, for instance, that I'm looking at example 15.6. So, OpenStax, example 15.6 says spontaneous heat transfer from hot to cold is an irreversible process. Okay. Calculate a total change in entropy. If 4,000 joules of heat transfer occurs from a hot reservoir at T sub H equals 600 Kelvin, which is 327 degrees Celsius, to a cold reservoir at 250 kelvins, T sub C, which is negative 23 degrees Celsius, very cold. assuming that there is no temperature change in either reservoir. All right, so we're going to assume that the reservoirs are constant. So we have a very simple process. 4,000 joules of energy, of heat, is going to go from the hot reservoir to the cold reservoir. Okay, so let's see what's going to happen here. Again, OpenStack's, again, very simple heat transfer process. All right, so again, OpenStack's example 15.6. So we're looking at schematically a hot temperature reservoir, T sub H, equaling 600 Kelvin. Okay, we got one reservoir. Heat transfers into another reservoir at T sub C equals 250 Kelvin. Here's your heat. Okay, let's look at two different perspectives. You have delta change in entropy from the heat leaving hot reservoir. Now, heat leaves the hot reservoir. That means it has to be negative, right? So it's going to be Q hot over T hot, or negative 4,000 joules. It's leaving the reservoir, so hence the sign of it has to be negative, over 600 Kelvin. Delta S hot. If you do that calculation, you find out it's negative 6.67 joules per Kelvin. Likewise, now heat goes straight into the cold reservoir. All right, what's delta S cold? Delta S cold will be Q sub cold divided by T sub cold, and it's going to be the same Q, but this time it is positive because it's entering. Remember, heat entering the system is going to be positive. That's our sign here. So positive 4,000 joules divided by 250 Kelvin. And delta S cold will equal positive 16 joules per Kelvin. What is the total change in entropy? So delta S total is delta S hot plus delta S cold. Delta S total is 16 joules per Kelvin minus 6.67 joules per Kelvin. Delta S total is going to be positive 9.33 joules per Kelvin. A positive value. Irreversible process. It means this process, entropy, second law of thermodynamics requires that the entropy change be greater than or equal to 0. So what this means essentially is that I can't have spontaneous heating, because if I did that, all of these calculations would be backwards. I'd have what? I'd have heat coming from Q sub C at T sub C and going into Q sub H at T sub H. That means these signs would be reversed. This would be a positive sign, this would be a negative sign, this would be negative 9.33 joules per Kelvin. You know, again, I can't have that. It's 9 points, it's got to be positive. So the fact is, entropy, the change in entropy can never be negative. The fact that change in entropy must be greater than or equal to 0 forces that only heat transfer can occur from a high temperature body to a lower temperature body, not vice versa. Spontaneous heating is forbidden because of the second law of thermodynamics. Well, another way of looking at the second law of thermodynamics is that it also is It's associated with, well, let's look at another interesting relationship here. All right, let's talk about second law of thermodynamics and a concept that might seem really strange to you. And that is the availability of energy to do work. Again, work is energy that is basically a force through a displacement. Let me show you an interesting example here, and we're gonna understand this whole concept. It's gonna be kind of a dreary concept eventually. We're gonna talk about, we'll just let me show you the example here. I'll show you we'll kind of talk about how the universe is probably going to end. So, and it's going to end by death by entropy, very likely. So, looking at example 15.7, OpenStax example 15.7. All right. In this example, I'm going to do what? I'm going to say A. I'm going to calculate the work output of a Carnot engine. Operating between temperatures of 600 Kelvin and 100 Kelvin. Okay, and then for part B, now suppose that the port, I'm sorry, and I didn't write some stuff down. All right. For 4,000 joules of heat transfer to the engine. Sorry. And then part B says, now suppose that the 4,000 joules of heat transfer occurs first from 600 Kelvin reservoir to a 250 Kelvin reservoir. Without doing any work. And then before transferring it into a Carnot engine operating between 250 Kelvin and 100 Kelvin. Some words I'm just not writing down here. Big. Okay. Okay, so I think this will look better when I draw a picture. Okay, so here we go. So calculate the work output of a Carnot engine operating between temperatures of 600 Kelvin and 100 Kelvin for 4,000 joules of heat transfer to the engine. And now suppose that the 4,000 joules of heat transfer occurs first from a 600 Kelvin reservoir to a 250 Kelvin reservoir without doing any work before transferring into a Carnot engine operating between 250 and 100 Kelvin. Okay, so the best way to kind of look at this is to draw a couple of pictures. All right, and so let me do that first. Okay, so in part A, I'm going straight from high temperature reservoir T sub H equals 600 Kelvin, and then that heat is going to go into the engine. And it's going to come out into a lower temperature reservoir. And so it's going to come in and it's going to do, well, let's see here. Let's calculate this. So again, the low temperature reservoir is going to be at 100 Kelvin. Okay, so thing is to keep in mind here is that we know that for the Carnot engine, it's the perfect engine, right? And so in this particular case, we know that delta S is going to be 0 because it is a Carnot engine. There's going to be work output, again, as is true for any engine. So we're going to have some sort of work output. So heat Q sub H is going to come in at the high temperature reservoir and Q sub C at the low temperature reservoir. Okay, and the engine's going to do some work. Well, what do we know? Well, we know that we're going to have, let's see here. What else do we know? It's a Carnot engine. All right, first of all. Right. And so let's just look at it this way. So delta S is 0, but let's kind of imagine here, first and foremost, that what we're talking about here is a Carnot engine. All right, so it's a Carnot engine, which means I know how to calculate the efficiency of all I know are T sub H and T sub C. So efficiency sub Carnot is 1 minus T sub C over T sub H. All right, and so the efficiency, 1 minus, let's see, the low temperature reservoir is 100 Kelvin, and the high temperature reservoir is 600 Kelvin. So the efficiency Carnot is going to end up being 0.833. And I know this because I was told that this is a Carnot engine. Now, I'd like to figure out what the work is. How do you figure out the work from anything? Well, so again, I know that Q sub H is 4,000 Kelvin. I was told that. So 4,000 joules. 4,000 joules of heat transfer goes into the system. That's part of the given. So what that means is that, well, the efficiency is what? The efficiency is always going to be, you know, what you get out divided by what you put in. So work divided by what am I putting in? It's an engine. Q sub H is what I'm paying for. So the work is going to be the efficiency times Q sub H. Or 0.833 times 4,000 joules. So the work is going to be, doing that calculation, it's going to be 3333 joules. That's the work. Okay, which then means that, well, So I know the work now, because I know the Carnot efficiency, I can figure out Q sub C. All right, and so now I know this. What do I know about a heat engine? Well, I know about any engine is what? It's a cyclical process. So the net work is always equal to the net heat. So I want Q sub C. That's going to be Q sub H minus W. Doing the algebra, Q sub C will be the 4,000 joules minus 3,333 joules. And I'll find out that Q sub C is going to equal 667 joules. So if I look at this, picture now, I know that Q sub H is 4,000 joules. I know that I have to have some sort of waste heat. That was 667 joules. And I know that the work that was done in this process was 3,333 joules. Now, what did I do? I went from high temperature reservoir of 600 Kelvin to a low temperature reservoir of 100 Kelvin through a Carnot engine. And I did 3,333 joules of work. Okay, so keep those numbers in mind. All right, and I'll parking lot this as I have minimum real estate here. So Q hot is 4,000 joules. Q cold, 667 joules. And the work was 3,333 joules. All right, so those are important numbers. Now, I'm going to change my system somewhat. For part B, that was part A. For part B, I changed my system somewhat. And I say, well, what I'm going to do is I'm going to start off, for part B, I'm going to start off and say, okay, I have this temperature reservoir at T sub hot is 600 Kelvin. But what I'm going to do is I'm going to immediately put the heat into a lower temperature reservoir. Heat's going to go straight into, without any kind of Carnot engine, we have Q sub hot, 4,000 joules, the same 4,000 joules. And it's going to go into another reservoir first. And I'll call it T sub H prime, if you will. Is 250 Kelvin. Okay, this is my Q sub H. The same 4,000 joules. Now what's going to do? What's going to happen? Now I'm going to put the Carnot engine and hook it up to this lower temperature reservoir. So now I'm going to have this Q sub H prime. All right, and it's going to go into the engine. All right, and the engine is going to do some sort of work. And out is going to go to the environment is the waste heat. So what's going to happen now? Well, so now what I have is I will have first and foremost there will have to be so this is the Carnot engine, which is going to have no entropy change, right? However, there's going to be entropy being done and for the heat going from T sub H over to T sub H prime. So I need to compute that. All right, so again, I'm going to I gotta determine. So first of all, I determine what that entropy is, and so let's do that. I'll call it delta S1, and it's not going to be 0. So going from here, delta S1, and this is the entropy going from the 600 Kelvin reservoir to the 250 Kelvin reservoir. That'll be, so it's going to leave the 600 Kelvin reservoir. So it's going to be negative Q sub H, because it's leaving, over T sub H. And then it's going to be plus Q sub H, because it's entering the other reservoir, over T sub H prime, all right? So it's leaving the 600 Kelvin reservoir, and it's going to directly go to the reservoir that's at 250 Kelvin. Now that is an irreversible process. That is not the cyclic perfect Carnot engine like we were talking about before. And so what's that entropy going to be? Delta S1 will be negative 4,000 joules over 600 Kelvin plus 4,000 joules over 250 Kelvin. Now, unlike before, the process increased the entropy of the universe by nothing. There was no entropy increase. Now, if I do this calculation, the process of the heat transferring from the 600 Kelvin reservoir to 250 Kelvin reservoir is going to cause an increase of an entropy of the universe by a positive 9.33 joules per Kelvin. So the entropy will have increased. The entropy for the second system is not going to, is again, it's a Carnot cycle. So the entropy over here, now for this region, is going to be 0. So all the entropy of the system is going to be what happened between here and here. Again, but before, and in the previous part A, there was no entropy increase. Now I have this process that happens first, which causes an entropy increase. All right, so now what happens? Well, now I have no loss of heat. My Q sub H prime is still going to be 4,000 joules. All right, so let's parking lot this guy. Delta S1 is positive 9.33 joules per Kelvin. Okay, so now let's try to figure out, so Q sub H prime, we're going into the Carnot cycle now. Q sub H prime is still 4,000 joules. So again, 4,000 joules coming here, 4,000 joules going into the Carnot cycle. So Q sub H prime is 4,000 joules. Now, I'm going to the Carnot cycle, and so just like before, I want to calculate the efficiency. So the efficiency, I'll call the efficiency prime. I mean sub Carnot. Okay, so it's going to be 1 minus 250 Kelvin over 100 Kelvin. I'm doing it between these two temperatures. And again, whoops, I didn't write this down. T sub C is 100 Kelvin again. I'm needing a new pen. 100 Kelvin. So between this new reservoir, this intermediate reservoir, and the same low reservoir, and I find out that the efficiency of Carnot, when I do that calculation, is going to be 0.60. Well, what's the work going to be now? Well, again, the work is always what? So the efficiency is always what I get out of something, which is the work in the case of a heat engine, divided by what did I put into it? Heat, right? And so in this particular case, I again, same calculation, I solve for the work. Just like before, the work is the efficiency times Q sub H. The work is going to be 0.60 times 4,000 joules. And lo and behold, the work is now going to be 2,400 joules. A lower value than before. Remember before it was 333 joules. Now, if all I do is I put this process in where it goes from one reservoir to the other, literally just transferring heat from a 600 Kelvin reservoir to a 250 Kelvin reservoir, my work output goes down from 3,333 joules to 2,400 joules. So the second system does it does 933 joules less work. What happened? I mean, I literally went from what? I went from 600 Kelvin reservoir to a final reservoir of 100 Kelvin in part A, going straight into a Carnot cycle, doing basically not increasing entropy at all. And then what happens is now I have a process where I take it from a 600 Kelvin reservoir, heat transfer straight to a 250 Kelvin reservoir, where I now do, and I increase the entropy of the universe by 9.33 joules per Kelvin. Then I take it from this intermediate reservoir through the Carnot cycle into the lower reservoir. And what happens? Well, before I did 3,333 joules worth of work. Now it's 2,400 joules. I'm doing less work. Why is that? Well, the answer to that is when entropy is performed, a certain amount of energy is made unavailable for the rest of the life of the universe to ever be used as work again. Every single time the entropy increases, a certain amount of energy becomes unavailable to do work. It's still there. It is as if it was tagged or labeled as unavailable to do work, unavailable to essentially. And of course, if it's unavailable to do work by the work energy theorem, it's unavailable to cause things to move. All right. And so what we actually see here, and this is from a direct example, is that the entropy increase causes an amount of energy to be considered permanently unavailable forever in the universe. Okay, and so when a system causes an increase in entropy, okay, a certain amount of energy becomes unavailable to do work ever again. And we saw that. We saw that because of this increase in entropy, there's a certain amount of energy. We saw less work. We saw a 933 joules less work because the second system did increase the entropy. Now, there's a general formula that actually we can calculate. It's a work unavail, we usually call it. Work unavail is usually given as the change in the entropy, delta S, times the lowest operating temperature of the system. In your system, the temperature that is the lowest temperature of operation in your system. So in our case, the lowest temperature that we had was the low temperature reservoir of 100 Kelvin. So remember, delta S from the second system, that was that delta S1, right? That was 9.33 joules per Kelvin. And the lowest energy that we encountered in that system was the energy of the low reservoir, which is 100 Kelvin. Does this work? Let's see. Work unavail will be delta S, which is 9.33 joules per Kelvin times 100 Kelvin. And yea, verily, look at this. Work unavail is 933 joules per Kelvin. We saw that 933 joules per Kelvin, less work was done in the second system than the first system. Why? Because the second system, because of this increase in entropy, 933 joules of work was labeled or tagged forever as unavailable. Now, this is a little bit of a scary thought in that the universe, every single day we exist, the universe is constantly increasing in entropy. There's an idea of what's called the heat death of the universe, where enough entropy increase will have occurred where there will be no more energy available to do work. So this is a concept that, many people believe that this is how the universe will eventually end, is when entropy essentially runs the universe out of available energy to do work. So this is a concept called the heat death of the universe. Essentially, when all possible energy to do work is unavailable. Every day, a bunch of it becomes unavailable. Now, again, this will happen in billions of years, so don't worry about your future or your grandchildren. But again, this is something that eventually is going to kind of pretty much run the universe out at some point. All right. Now, entropy also is tied with a concept called order and disorder. So the universe is always, and it gets to this answers another question that I initially posed is, why can't I run a movie backwards? And, why can't I run the movie of life backwards? Well, because, and I said in my initial, example, I talked about the cowboy movie where a guy comes in and shoots, the ceiling, and you see the smoke coming out of the gun, and you see people throwing things at him and tables being overturned. Well, if I run the movie backwards, what happens? Well, let's say, a base is thrown at the guy and smashes. Well, the base comes off the wall magically, comes back together, sits back down, all the tables suddenly get in nice order, cowboy runs backwards. The whole movie looks ridiculous because it doesn't happen. Why doesn't it happen? Because we go from a state of total disorder to a state of order. We cannot do that naturally without doing work. All right, so let's give an example that Ludwig Boltzmann gave. So in this case, we're looking at example 15.8. OpenStack's example 15.8. So, and again, this is a concept of order to disorder. So find the increase in entropy. Of 1.00 kilograms of ice originally at 0 degrees Celsius that is melted to form liquid water at 0 degrees Celsius. So, and again, ice is a tight, regular arrangement of atoms, a regular arrangement of water molecules. Liquid water is not. Liquid water, we would say, is much more disordered. We would expect melting to actually give you a large amount of entropy, because ice is very, very arranged. It's very ordered. Liquid water is not. So if I did a calculation, I should get a large number for the change in entropy. Let's see what happens. So we know that melting, when we melt something, so we know delta S is Q over T. What heat? Well, again, it's going to be heat. That's going to be, the Q is the heat of melting. That's the mass times the heat of fusion. Remember, the heats of fusion, heats of vaporization are huge, right? So we're talking about 1 kilogram of ice. You look up the heat of fusion, it's 334 times 10 to the third joules per kilogram. Very large number. Q is going to be 3.34 times 10 to the fifth joules. Temperature, again, is going to be 273. Freezing, right? 273 Kelvin. And so the entropy increase is going to be 3.34 times 10 to the fifth joules divided by 273 Kelvin. So as Boltzmann had calculated, the change in entropy for this process to go from high order to disorder is going to be a very large number, 1.22 times 10 to the third joules per Kelvin. So again, entropy is, as you've probably many times heard, is a process where you go from large order to large disorder. Okay. All right. So let's work some problems out, and then I'm going to talk about statistical approach to physics. All right. So let's work a few problems out. We're going to get our feet wet here. All right. So OpenStax 15.47. That says on a winter day, a certain house loses 5.00 joules of heat to the outside. About 500,000 BTU. Remember, BTU is British thermal units. What is the total change in entropy due to the heat transfer? Due to the heat transfer alone? Assuming an average indoor temperature of 21 degrees Celsius. And an average outdoor temperature of 5 degrees Celsius. Okay, so on a winter day, a certain house loses 5.00 times 10 to the 8 joules of heat to the outside, about 500,000 BTUs. What is the total change in entropy due to the heat transfer alone? Assuming an average indoor temperature of 21 degrees Celsius and an average outdoor temperature of 5.00 degrees Celsius. Okay, so again, this is a basic problem. We don't have any change, any temperature change. We basically just have reservoirs. Okay, so the heat. So heat Q. Okay, so Q equals 5.00 times 10 to the 8th joules. All right, is lost from the hot reservoir. At T sub H. Okay, so again, it's going to be 21 Celsius, but we want to go into Kelvin, of course. So 21 plus 273 is 294 Kelvin. Okay, so Q sub H will be negative Q, because it's losing it, right? The temperature, the heat is being lost from the house. So negative 5.00 times 10 to the 8th joules. Heat Q equals 5.00 times 10 to the 8 joules is gained by the cold environment. All right, and so that means Q sub C will be gained, right? So positive 5.00 times 10 to the 8th joules. You want to find a total entropy. Well, delta S sub H will be Q sub H over T sub H. Well, let's just write over here. Delta S sub H will be Q sub H over T sub H, or negative 5.00 times 10 to the 8th joules divided by the 294 Kelvin. Okay, that'll be, well, actually, let's just do one calculation at a time here. T sub C, by the way, will be what? It'll be 5.00 plus 273, or 278 Kelvin. All right, so delta S will be delta S sub H plus delta S sub C, or negative, or well, basically Q sub H over T sub H plus Q sub C over T sub C, or negative what I'm calling Q, this 5.078 joules, over T sub H plus Q over T sub C, delta S. I can pull the Q out, and I get 1 over T sub H minus 1 over T sub C. Or, again, Q I pulled out, it's just going to be the magnitude there. So 5.00 times 10 to the 8th joules times what? 1 over T sub H 1 over the 294 Kelvin minus 1 over the 278 Kelvin. And I get an increase in entropy. I'll put it up here. When it's all said and done, I'll get an increase in entropy of positive 9.79 times 10 to the 4 joules per Kelvin. Again, it's a process that always increases the entropy of the universe, which it should, or else otherwise there's a serious issue here. Every day that house loses heat, the entropy of the universe increases. So the entropy of the universe is always increasing. All right. Let's do another one that's going to be a little bit different. OpenStax 15.49. Here's one where the reservoir temperatures remain the same. What happens if the temperature of an object changes? That'll be the next one. OpenStax 15.49. All right, that one says a hot rock is a hot rock ejected from a volcano's lava fountain. Cools from 1100 degrees Celsius to 40 degrees Celsius. And its entropy decreases. By 950 joules per Kelvin. How much heat transfer occurs from the rock? Now, some students might look at this and say, oh, wait a minute. How can entropy decrease? Well, again, remember the total entropy decreases. I'm sorry, the total entropy must always increase. We're just talking about the rock. We're not talking about the environment. We're just talking about that the actual rock itself is actually decreasing in entropy. But the problem is, all the problems we've done before have reservoir temperatures that don't change. Now we have a temperature that changes. Well, how do we calculate the entropy of something like that? Well, the problem is that we would require integral calculus to actually make such a calculation. So if you look at the entropy, you'd have to look at corresponding entropy changes of little tiny changes of temperature and add all those changes up. Because the temperature changes, you'd have to do very small incremental set of entropy problems. And so in general, okay, if temperature changes during a process, calculating entropy requires integral calculus. So I have to actually calculate incremental entropy changes, and the way to do that overall with calculus, you know, the way to add in calculus is to do what's called integral calculus, right? You have an integral, we call this a line integral, so we're integrating over a line of changes, and we say this is delta Q, change in Q, divided by the temperature, all right? Well, again, we can't do, we're not doing integral calculus here, so we are not performing integral calculus in this class. So we make an approximation. And calculate the entropy change at the average temperature. I mean, calculate of the endpoints, basically, the average between the endpoints. You know, if you calculate at either endpoint, it's going to be much worse. Calculating the average is not going to be great, but it's better than if you calculate at either endpoint. So again, we have to figure out, the average of the endpoints. Okay, we're not going to do integral calculus in this class. We have a body that changes temperature. Okay, we've not had that before. And so what we're going to have to do is we're going to have to find an operating temperature where we calculate the entropy. And so we're going to choose an average temperature. So we're going to calculate it at, T is going to be, so remember, it's cooling from 1100 degrees Celsius plus 273. And then add the, so again, add the two temperatures, divide by 2. The low temperature is 40, cools down to 40 plus 273 divided by 2. So the average, we use it at the average, and we find out that the average temperature between the two endpoints is 843 Kelvin. So again, neither one of these is a great, you know, neither, again, the endpoints is going to be worse, but the thing is, you know, this is not going to be an accurate calculation. And this is what happens when you don't use integral calculus. You automatically implement inaccuracies in your calculation. All right. And so in so doing, you know, because you're not using integral calculus, we have to, you know, we're going to get error essentially. So, but it's the best we can do right now. So again, the entropy is getting lost. We're told that the entropy is reducing, so it's negative Q over T, right? And so in this case, the entropy is Q over T, and Q is T times delta S. All right, and so in this case, Q is going to be this 843 Kelvin. And remember, we were told there was an entropy loss of negative 950 joules per Kelvin. Putting this all together, you find out that the heat transfer is going to be negative 8.01 times 10 to the 5th joules. And it is negative, why? Because heat is getting lost from the system. Heat is being lost from the system, so hence it's going to be a negative heat transfer. So again, I said there's a little glare here of a light. So again, negative 8.01 times 10 to the 5th joules. Heat is lost from the rock. Okay, next problem, OpenStax 15.51. So that one says the sun radiates energy. at a rate, we've seen this number before, of 3.80 times 10 to the 26 watts. From its 5,500 degrees Celsius surface. Into dark, empty space. You know, a negligible fraction radiates onto Earth and the other planets. Okay, the effective temperature of deep space is negative 270 degrees Celsius. What is the increase in entropy in 1 day due to this heat transfer? And then B, how much work is made unavailable? Okay, so the sun radiates energy at a rate of 3.80 times 10 to the 26 watts from its 5,500 degrees Celsius surface into dark, empty space. A negligible fraction radiates onto Earth and the other planets. The effective temperature of deep space is negative 270 degrees Celsius. A, what is the increase in entropy in 1 day due to this heat transfer? And B, how much work is made unavailable? Okay, so again, this is kind of telling you here that we have an ordinary star, the sun, one of many stars, one of 100 billion stars in our galaxy. There's 100 billion galaxies, so the universe is constantly generating entropy all the time. So first of all, how much power is, how much heat is radiating a day? So what I want to try to get is I need to get a change in entropy, right? So I'm shooting for Q over T. So I got to figure out like how much heat is leaving the sun. How do I figure that out? Well, again, the heat will be the power times the time. I'm talking about 1 day. So remember, the power is the work over the time, or the amount of energy over the time. So the amount of heat will be the power times the time, PT. Well, how much time are we talking about? 1 day. Well, 1 day, there are 24 hours in a day. Days cancel, and there are 3,600 seconds in an hour. Hours cancel. So the amount of time in 1 day is 86,400 seconds. So the power, the energy that is released by the sun in one day will be 3.80 times 10 to the 26 watts. Multiplied by the seconds in a day, 86,400 seconds. So I did that calculation. I found that that heat value is 3.28 times 10 to the 31 joules. All right, that's heat lost by the sun in one day. Now, the sun has a high temperature reservoir, so let's kind of write that down here. So Q, again, is, let's put this in a parking lot for the moment. Q is 3.28 times 10 to the 31 joules. Now, the sun serves as a high temperature reservoir, and space serves as a low temperature reservoir. All right, so the sun is a high temperature reservoir. Of temperature T sub H, say at T sub H, again, we had 5,500 degrees Celsius, but we don't want that. We really want that in Kelvin. Add 273, you get 5773 Kelvin. That's temperature of the sun in Kelvin. Space is a low temperature reservoir. At T sub C. Again, that's going to be what? Negative 270 degrees Celsius plus 273 is 3 Kelvin. Okay, so so we have here is delta S. Again, it's going to be delta S hot plus delta S cold. We have this Q. So again, the sun loses heat. That's going to give me negative Q over T sub H. The space gains heat plus Q over T sub C. And I can factor out Q, and I get 1 over T sub C, which is positive, minus 1 over T sub H, which is negative. So I find out that the entropy change in just one day, entropy increase in the universe because of the sun radiating for just one day, is going to be 3.28 times 10 to the 31 joules times 1 over 3 Kelvin minus 1 over 5773 Kelvin. And I find out that delta S, let's see if I have enough room here, that delta S is equal to 1.09 times 10 to the 31. Joules per Kelvin. All right, so again, delta S I find is 1.09 times 10 to the 31 joules per Kelvin. That's how much entropy increases in the universe because of the sun radiating in just one day. That is a tremendously large number. How much work has been in the universe is being made unavailable forever because of this process? And so this is my answer to part A. Part B, we have another equation that tells us the work unavailed. So work made unavailable, part B, is, remember, the temperature change, the entropy change times the lowest operating temperature of the problem. So work unavailed is equal to 1.09 times 10 to the 31 joules per Kelvin times 3 Kelvin. The lowest operating temperature would be the temperature of space. That's the cold reservoir temperature. Work unavailable, work energy made unavailable to do work every single day because of the sun radiating is going to be a whopping 3.27 times 10 to the 31 joules. And that's part B. This is part A. All right. All right. Let me talk about, well, let's see. Let me talk about one more topic quickly, and that is, I've talked about how to calculate entropy change. The question is, no, and I talked about, that there is a second law of thermodynamics and that entropy is always increasing. But the thing about it is, now that we understand statistics, now that we understand that all bodies are made of atoms, the question really comes down to is, why does entropy increase? I mean, what is really the rationale or the reason behind it? And the reason is all about probability. All right, and so the thermodynamics, we have an entire field called statistical mechanics. This is the area of that I do research in. And statistical mechanics looks at systems, at thermal systems, that contain many atoms statistically. You cannot do Newton's second law for 10 to the 21st, atoms. There's no way. So the question is, well, how would you go about doing something like this? And the answer really comes down to is probability. I'm going to talk a little bit about, for instance, that like why do systems always tend to disorder? Well, they tend to disorder because there are many more ways in which a system can have disorder. So let's imagine coin tosses for a moment. So I look at coin tosses, and let's imagine 5 coins. So how would I get five coins? What situation might I get? Well, I might get 5 heads and 2 tails, or sorry, 5 heads and 0 tails. I could have 4 heads and 1 tail. 3 heads, 2 tails. 2 heads, 3 tails. 1 head, 4 tails. or 0 heads, 5 tails. So if I were to take 5 coins, 5 quarters, for instance, and just throw them down, those are all the possible results that I'll get. Now, it is safe to say that a system that is lined up with 5 heads or 5 tails is the most ordered system. And a more disordered system would be one that's more mixed up. Now, all of these possible states of the system, without regard to how the states occur, are called a macro state. All right, and so a macro state, again, this is about mechanics language. A macro state is an overall property of a system. Does not specify the details of the system, such as the order in which the heads and tails occur. So all the outcomes that I wrote down are macro states. Again, when I say, 4 heads, 1 tail, that could be, head, tail, head, tail, head, tail, head, or tail, head. I mean, there's all kinds of different ways I can do that. All I said was I gave a description of 4 heads and 1 tail. So again, those descriptions that I just wrote down are called macro states. All right. Now, that's a macro state. Again, an overall statement of the system, not specifying how that occurs. The possible sequences of heads and tails are called microstates. Okay, so for instance, if I'm talking about, so let me show you a situation. Let me pull up a table that discusses the macrostate versus microstate concept. So we'll talk about the 5 coin tosses. Let me go to the textbook real quick, or the OpenStax book, and bring up some tables that talk about the coin tosses. I'll share my screen in a minute. All right, so I wrote up all the possible macrostates. Let me share my screen here. Now, for the given macrostates that I wrote above, there are, so you look at the, you look at the very far left column, where those are all the macrostates I just got done writing. The middle section talks about all the ways that this can happen. So there's only one way, and then of course the right column talks about the number of ways that can happen. So there's only one way that I can get 5 heads. However, there are 5 ways, as you can see, to get 4 heads and 1 tail. So again, the far left column, the second row, the macro state is 4 heads and 1 tail, and there's 5 ways of doing that, and the middle section delineates all those 5 ways. And then the next row is 3 heads, 2 tails. And we find out there are 10 ways to make that happen. Next row down is 2 heads, 3 tails. There are 10 ways to make that happen. And then you have 1 head and 4 tails. We see 5 ways to make that happen. Finally, there's only 1 way to make 5 tails. And we see there's a symmetry. 1, 5, 10, 10, 5, 1, like Pascal's triangles, there's symmetry. Now the total possible ways, total possible outcomes, if you add up all the microstates, is 32. But you look at it and say, well, the most ordered microstates or the most ordered macrostates are the ones that have the fewest microstates. So the most ordered macrostates, I think it'd be arguable that 5 heads and 5 tails would be a statement of the greatest order. The statement of the greatest disorder would be the most mixed up cases, which would be the middle ones. There's 10 ways of that happening. So again, if I were to start off with all 5 heads and I throw down the coins, I would find out that I'd have much better chance, a much greater chance to get a more mixed up state than what I had before. Now again, so that really is telling you is that in general, I would expect, if I'm starting from a high ordered state, I would expect from a throw of 5 coins, I'd expect to get into a much less ordered state. I would expect a state of much greater disorder. Okay, that's for 5 coins. What happens now if I go to 100 coins? So let me go to the next table and show you 100 coins. Now it becomes incredible. Now I have 100 coins. The grand total of ways, you look at the very, very bottom, here's all the possible outcomes. The total number of ways, the total number of microstates. Again, these are all the macrostates. On the far left column are all the macrostates of the heads and tails. Again, I mean, not all of them are delineated. 100 heads, 0 tails, 99 heads, 1 tail, 95 heads, 5 tails, so on and so forth. If you look at the total number of ways, all the possible microstates I can ever see in the throw of 100 coins, you'd see there's 1.27 times 10 to the 30 of them. And you notice incredible numbers for the ones with the greatest amount of mixing up. So there's only 2 ways out of that 1.27 times 10 to the 30 that I could possibly get perfect order. If I throw coins, it is much greater chance. The numbers are incredible. If you look at 50-50, for instance, 1.0 times 10 to the 29th, it is much greater possibility that there's many, many more ways, many more microstates that correspond to the most mixed up macrostates. So the system will tend to a more disordered state just because there's way more ways of doing this. So how does this correspond to a gas, the disorder of a gas? So again, this is for throwing coins. We see how incredible the numbers are for just 100 coins. That second table was 100 coins. What about a case of a gas? So for the disorder of a gas, so you see the fantastic growth of just 100 coins. Well, let us now approach this a small sample of gas. So let's consider a small sample of gas. But if I think of a small sample of gas, the macro states of the gas correspond to its macroscopic properties. Such as volume, temperature, and pressure. Right? The microstates of the gas correspond to the detailed description of the positions and velocities of the atoms. All right, so you have a whole bunch of first of all, a whole bunch of atoms in the first place. Then you have a whole bunch of different ways they can have positions and velocities, and all that combined is going to give you the various possible macroscopic details of the gas. So we give an idea of this. You know, we say that so the disorder of a gas again. So, for instance, you know, even a small amount of gas is a huge number of atoms. So even a small amount of gas has a huge number of atoms. So, for instance, 1 centimeter cube of ideal gas. So, as an example, 1 centimeter cubed of an ideal gas at 1 atmosphere and 0 degrees Celsius has about 2.7 times 10 to 19 atoms. Okay. So each macrostate has an immense number of microstates. All right, and so So there is an immense number of ways. There is an immense number of ways. All right, which the atoms in a gas can be arranged. And still have the same pressure, temperature, and volume. All right, so again, and of course, what do you normally see? You know, when you look at a vessel of gas, you're normally going to see, you know, again, you're talking about incredible numbers. You know, each gas has got 6 possible components of position and 6 components of velocity. Multiply that by this incredible number of atoms. And so when you see the most probable macrostate is going to be the one that corresponds to the Maxwell-Boltzmann distribution. So the most likely conditions the macrostates for a gas are those we see all the time. And what do we see all the time? A random distribution of atoms in space with a Maxwell-Boltzmann distribution of speeds. That's what we see. All right, and so if we're looking at a situation where, we talk about the puff of gas, like okay, so we have a distribution of the green smoke all throughout the room, and how does it go into a corner? Well, the corner would be a very small number of possible positions. It'll be very, very few ways of doing that. Or if you were to say, for instance, have all the atoms flying in the same, parallel to each other. Very, very few ways of doing that. Again, you're talking about very, very unlikely situation. Not impossible, but just highly, highly unlikely. So again, that tells you why you don't see, the distribution of green, the green smoke that goes throughout the room suddenly gets sucked into the corner of the room. There's very, very few ways for that to occur. Now, I want to kind of finish off this lecture with what has been oftentimes called the most beautiful equation in all of physics. All right, so Maxwell and Boltzmann. Connected statistical mechanics. and thermodynamics by following equation. S equals K as a natural log of capital omega. Okay, K is the Boltzmann constant. We've seen this before. 1.38 times 10 to the negative 23 joules per Kelvin. Omega is the number of microstates for a particular macrostate. S is the entropy. So literally, you can characterize, like Claude Shannon was a mathematician who did this. You can characterize a system by pure statistics. Pure statistics. That's it. You take the logarithm of, you say I have a particular macrostate. It has this many microstates. You take the logarithm, natural log of the number of ways that a macrostate can happen, multiplied by the Boltzmann constant, and now you're in thermodynamics. You're in the entropy, the same entropy that we talked about earlier in thermodynamics. Literally, there's a direct connection between pure statistics and pure thermodynamics. This is in fact, Boltzmann put this equation, this particular equation on this epitaph. This is considered one of the most beautiful equations in all of physics. All right, so this is the reason why entropy always increases. I mean, again, the number of microstates, for the most probable macrostates is the most mixed up system. So again, you're always going to be tending toward disorder. You see it here. So I'm just going to work a couple of problems here for Cisco mechanics. So we'll call it a done deal. So again, you'll see how statistics beautifully works into entropy. All right, so a couple of problems, and we'll call this a done deal. Mac OpenStax 15.57. Again, I'm going to state that you're going to have to look up in the book yourself to look at the tables. I mean, I don't want to go through the process of looking at the tables, but they're going to depend on a lot of these tables of the coin flips. So again, using OpenStax table 15.4. Verify the contention that if you toss 100 coins each second, you can expect to get 100 heads or 100 tails once in 2 times 10 to the 22nd years. Calculate the time in 2-digit accuracy. Okay, so using OpenStax table 15.4, verify the contention that if you toss 100 coins each second, you can expect to get 100 heads or 100 tails once in 2 times 10 to the 22nd years. Calculate the time in 2-digit accuracy. Again, the universe is only 13.8 billion years old. So we're talking many times the age of the universe to just throw 100 coins until you ever see is so much order as 100 tails, 100 heads. Okay, so let me get some real estate here. So the probability of 100 heads or 100 tails is, again, look at the table. So looking at the table, the probability of 100 heads or 100 tails, again, total perfection, is 2 out of the total number of microstates. If you look at table 15.4, you see that the total number of microstates for the toss of 100 coins is 1.27 times 10 to the 30th. I mean, crazy number. Okay, so that's going to equal 1.575 times 10 to the negative 30. Okay, that's basically, this is 1 in, and flipping this number, 6.35 times 10 to the 29. Incredible odds. All right, so basically, if we toss a coin 1 second, if each coin toss takes 1 second, so if each coin toss takes 1 second, we need 6.35 times 10 to the 29 seconds. What's that going to be? Well, 6.35 times 10 to the 29 seconds times, let's see here, 1 hour has 3,600 seconds. Okay, and then 1 day has 24 hours. Okay, so now we have days, and 1 year has 365 days. And if you do that, you find out that you get 2.0 times 10 to the 22nd year. So basically, the universe could never live long enough for you to do that experiment if you're so inclined. All right, we're going to do 2 more problems. OpenStax 15.58. So again, this tells you this is just 100 coins. Imagine the order in a gas that has so many atoms in it. OpenStax 15.50. Well, let me skip this one. I'm gonna do 1 more problem. OpenStax 15.60. Last problem. I mean, the previous one I want to do would rely too much on the table. All right, so again, this is going to be you looking at the table. So part A, what is the change in entropy? If you start with 100 coins, in the 45 heads and 55 tails macrostate, toss them and get 51 heads and 49 tails. So again, I'm gonna do these problems one step at a time. So, so let's just do this. Let's just do part A first. So again, if you look at the table, you look at that table and say, how many ways can I get 45 heads and 55 tails? Okay, so 45 heads and 55 tails. How many ways is there to do that? If you look at the table, that would be my number one. So the number of ways, the number of microstates corresponding to this particular macrostate, looking at the table, is 6.1 times 10 to the 28. That many ways to get that particular macrostate. And I want to get to the macrostate of 51 heads and 49 tails. That's omega sub F, final. Looking at that table, I get 9.9 times 10 to the 28th. That's how many ways, how many microstates correspond to that macrostate. So again, there are 6.1 times 10 to the 28th ways with 100 coins to get 45 heads and 55 tails. There are 9.9 times 10 to the 28 ways to get 51 heads and 49 tails. And this is more mixed up, so there's more ways to do it. What's the change entropy in this process? So again, delta S is K natural log of omega final minus K natural log of omega initial. And again, when I can pull the K out, I have K natural log of omega final minus natural log of omega initial. And of course, if I have a subtraction of logarithms, I can write this as delta S is K natural log of omega final over omega initial. Which will be 1.38 times 10 to the negative 23 joules per Kelvin times the natural log of 9.9 times 10 to the 28 divided by 6.1 times 10 to the 28. Again, literally pure statistics in the omega. The number of ways to make things happen. How much entropy increases that? It's literally K times the natural log of omega. It's a difference of those two. I come to find out that when I do this calculation, the delta S, I have enough room here, is going to equal 6.68 times 10 to the negative 24 joules per Kelvin. That is the entropy change if I do that. Okay, so part B now says, I want to find out, I'm going to go from 75 heads, I'm going to go to 75 heads, 25 tails. So part B is going to be the same thing, except I'm going to start off with 45 heads, 55 tails, but I'm going to toss them, I'm going to get 75 heads and 25 tails. So what I'm going to do is part B is going to be a rare case where I'm going to go to a more ordered state. All right, well, we'll see what happens now. So this is the same. Now I got to look up in the table, 75 heads and 25 tails. And I look up omega sub F in that situation. I come to find out that it's going to be 2.4 times 10 to the 23. So I did the same mathematics as before. Delta is K natural log of omega final minus K natural log of omega initial. Same thing as before. except now what I'm going to do is I'm going to replace a different omega sub f up here. So that'll be 2.4 times 10 to the 23. And then I come to find out that I get a negative value. So now delta S, or part B, again, this is part B now. Delta S, or part B, I'm going to a more order state. Order is going to be a negative. So I mean, of course, a decrease in entropy because I'm going from more disordered to more ordered. Negative 1.72 times 10 to the negative 22 joules per Kelvin. Okay, and so now you ask yourself the question, okay, well that's part B. Part C will then say, well, how much more likely is 51 heads and 49 tails than 75 heads and 25 tails? Okay, so let's kind of remember these numbers. And here I have a decrease in entropy. Well, let's look at the likelihood. So now part C says how much more likely is 51 heads and 49 tails than 75 heads and 25 tails. Well, again, you look at that table, and so essentially 51 heads so essentially omega for 51 heads, 49 tails divided by omega, 75 heads and 25 tails. You look at that, and you're looking up at the table, you get 9.9 times 10 to the 28 divided by 2.4 times 10 to the 23. And you get that it's 4.1 times 10 to the 5 times more likely. Way more likely to get the much more mixed up state of 51 heads, 49 tails than the 75 heads and 25 tails. Okay, so the final part of this then says, okay, well, we see that it's possible to go to a state of greater order. So part D says, does this outcome violate the second law of thermodynamics? All right, so, and the answer to that is no, it does not. Entropy decreases are possible. But unlikely, highly unlikely. I mean, it could happen, but again, all the air in the room can actually get sucked into the corner of the room. I mean, that's possible too. highly, highly, highly unlikely. You'd have to wait for many times the age of the universe to see that happen. So essentially, that's all it really tells you is that, you know, so also, you know, in the case, in the case for part B, you know, delta S is a small negative number. That indicating that a spontaneous fluctuation in the system, the decrease in entry is not is highly unlikely. So again, it's all about likelihood and probability. You know, entropy decreases can happen. They're just very highly, highly unlikely. So again, that is, you know, so statistical mechanics is a very beautiful subject. That is my area of expertise. I particularly do to quantum statistical mechanics. That's, you know, where I have research papers. And so again, this is something that's near and dear to my heart. And this sums up not just thermodynamics, but thermophysics. So we have now in this course completed both the theories of mechanics and the theory of thermophysics, and we've also treated waves. All right, and so that's all I have for this particular lecture.